Není zvuk, Martina. Okay, sorry, just a second. We have some problems with sound. It will be solved immediately. And
the following message is best viewed on an oscilloscope.
okay, so welcome everybody. Thank you very much for joining this session. This is the fourth session of parallel session of track 12 of the ICHEP 2020 online conference. I'm very happy that you joined this session. We have a very dense agenda. So today, the first part of the session is dedicated to the muon detectors. We will hear about the Atlas muon identification performance, also about CMS muon detectors. The second part and the third part then will be focused on the jet reconstruction, heavy flavor tagging, triggering, and at the end of the session, we will hear also something about the DAQ system. So I think that it is a very interesting program, and I hope that we will all enjoy it as much as possible. So yes, I will, as I mentioned, I will chair the first two parts, and the last part will be chaired by Anne. So I think that we can start. So the first talk will be given by Rustem, and it will be on the muon identification and performance in the Atlas experiment. So Rustem, if you can try to share, yeah, we can see your slide. Of course, all presentations will be 12 minutes plus 3 minutes discussions. Thank you. Yeah, you
Hi,
can
good
start.
morning. You can hear me still,
Good morning.
right? Yeah, thanks. So I would like to start maybe by thanking organizers for preparing this unusual conference this year. We all wish to be in person in Prague, but things being what they are, I think we should take an advantage. And I think organization communication was very nice. Today I will talk about the performance of Atlas muon construction identification. Here you see an event display which shows it's an action. So it's an event display with the highest invariant dimuon mass recorded by Atlas detector with a mass of almost 3 TeV and the lead lepton approaching 2 TeV. Muon signatures, of course, are important for Atlas program. There are hundreds of results that use muons, including the Higgs boson measurements. So on the bottom left, you can see here the search for, or the measurement of the Higgs boson decay to 4 muons, which is very clear resonance peak 125 GeV, which requires a very efficient selection because there are 4 muon events are very rare. There's also searches for the resonances. So here's a search for the Z prime resonances decay into 2 muons. And then this last data point is the event display you saw on the previous page, which requires now muon performance in a very, very, very high PT regime. And in order to understand muon performance, we use Z and J psi events. There's almost 210 million events of Z decays to muons recorded. And this resulted in improvement of the calibration by a factor of 5, both in statistical precision as well as systematic uncertainty. And there on the right side, you can see Z peak used for the previous calibrations. Now we have much more data. So Atlas muon spectrometer, which is used for muon measurement, consists of fast detectors for the triggering and precision detectors, which reconstruct muon tracks with high precision and high efficiency. There are 2 precision detectors for Atlas. One is so-called muon drift tubes, which cover a fiducial volume of pseudo-rapidity up to 2.7. and a position resolution of 80 microns per single measurement. There's also cathode strip chambers, which are used in most inner area of a detector where the backgrounds are too high for the MDTs. So these 3 precision layers provide up to 20 measurements per muon spectrometer track. These detectors are embedded in a magnetic field, which is provided by 3 superconducting air core toroid magnets with a field integral between 2 to 6 Tesla times meter. And muon reconstruction starts typically within a detector, which is in a more sparse of Atlas detector, which reconstructs charged particle tracks, both muons and hadrons. Then we have a colorimeters and shielding material, which stop nearly all hadrons from reaching muon spectrometer, and typically only medium ionizing particles with momentum greater than 3 GeV will reach muon spectrometer. So this already gives you an idea of how the reconstruction works in Atlas. For these calibrations, we use a full Atlas dataset recorded as 13 TeV, which is about half of originally planned integrated luminosity. So first I will talk very briefly about muon reconstruction, and then so-called tag and probe method. Then about muon identification, isolation, as well as showing some results for efficiency measurement and talking about systematic uncertainty and stability of these measurements. Muon reconstruction starts by studying several sources of muons and LHC collision. So typically there are 3 main sources of muons. There are so-called probe muons, which produce in the case of Z and W as well tau leptons. And those are identified by having a muon track which which reconstructed both an in-detector and muon spectrometer. There are also non-probe muons producing in the case of heavy flavor hadrons, but lifetime is still sufficiently small where you have a muon track both in detector and muon spectrometer. And also non-probe muon produced in the case of light hadrons like pions and kaons, where then there is a pion kaon track will create, pion kaon particle create a track in detector, and then we have a muon track and muon spectrometer. Typically there's a mismatch in the momentum. Then these 3 types of muons then lead to several types of reconstructed muons. There are combined muons, which are created by matching inner detector muon spectrometer tracks, which are most of our muon candidates. And then you have extrapolation of muon spectrometer tracks back to collision point where in-detector's track is missing in areas where there is no full in-detector coverage. And also in-detector tracks, which extrapolate outside to the muon spectrometer colorimeter. And this is primarily in regions where muon spectrometer coverage is limited. So there are 5 identification working points for the reconstruction. So they're called loose, medium, and tight, and also low and high PT. And here is just an idea of an efficiency of this working point. So they're quite high, for example, above 20 GeV. They go from 99% efficiency to about 93% efficiency for tight. And high PT really becomes efficient above 100 GeV. And you can see also differences in rejection of hadrons, which here hadrons means the case of pion and kaons primarily. And then that the looser working point have a larger backgrounds, but differences are not very big. In order to measure efficiency, we use a so-called tag and probe method, which many of you are very familiar with, so I'll be very brief. So they use decays of Z and J size to dye muons. A tag muon typically fires a single muon trigger, and then has to be very high quality. And the probe muons is loosely reconstructed muon candidate. In our case, it's either in a detector track or muon spectrometer track, or in a detector track tagged with a colorimeter cluster. And then you require that 2 muons are consistent with the decay of Z or J psi boson. The backgrounds are measured from data from sideband feeds, and then it's a slightly different strategy used for Z and J psi. Then efficiency measured as a number of the probe muons that satisfy the target working criteria. For example, loose, medium, and so on. And then the denominator, of course, are the all muons. And so the critical part of this measurements are this new tag and probe procedure, which I don't have time to explain, but this efficiency measurement has been improved, leading to a factor of 5 small systematic uncertainty, being as low as 0.1% in the central region of a detector. Also, using JPSI, the measurement of efficiency were extended down to 3 GeV. Now, summarize very briefly different working points, so loose, medium, and tight. So medium is a sort of a default working point, which selects combined muons in a detector muon spectrometer. And then we add muon spectrometer track in the forward region where there is no full ID coverage. Loose muons start with medium and then add in a detector track tagged by colorimeter or muon spectrometer segments. And tight muons then require at least 2 precision hits, stricter feed quality criteria compared to the medium muons. And then low PT I will discuss about later, but optimized for muons below 18 GeV. And here you can see comparison of efficiency as a function of transverse momentum of muon, and a medium and loose are comparable, and tight, of course, has a smaller efficiency. Also, a function of eta, and see here in the central region, the medium and tight have lower efficiency compared to loose, because here we have a limited coverage for muon spectrometer. Also, you see at the low PT, this special working points with shown as circles improve something like 10–15% compared to the medium working point, while having the similar or even small in some cases amount of background. The high PT working point was optimized for measuring muon momentum precisely with transverse momentum greater than 100 GeV. And here we require muon spectrometer tracks with 3 precision layers or 2 precision layers, but then selecting best quality track, which really have, say, for example, very small alignment errors and small other errors. And then what this allows us is to improve the resolution by almost factor of 2. So here on the right side, you can see the improvement of momentum in high PT working point as a function of transverse momentum of muon. And here on the left, you can see the efficiency in the 2D detector plane, phi and eta. And compared to the medium, which is on the left, the high PT working point excludes some areas we can see in a darker color where we have, for example, insufficient precision of alignment constants. In addition to the selection, we also employ isolation. So isolation works by selecting prompt muons from WZ and tau decays. And the background are non-prompt muons, which are decays of heavy flavor hadrons containing B and C quarks, and typically is embedded in a jet of hadrons. So in order to remove this background, we require muons to be isolated, and this is done using so-called track-based criteria, which use in the detector tracks, or colorimeter-based criteria, which use topological colorimeter clusters. There's also a new particle flow isolation, which matches in the detector track with clusters. That helps to remove contributions from additional collisions in event, because typically we have an order of 30–40 collisions per beam crossing. There are six isolation working points using simple selection criteria, and the 2 multivariate working points as well, which use boosted decision tree and isolation impact parameter measurements in order to improve the selection. You'll see it later. On the right side, there's a distribution of isolation variables for colorimeter and detector tracks. You can see that divided as a function of muon, so divided by muon momentum. You can see the prompt peaked around 1, and then non-prompt peaked on the right side. So there's an overflow beam, and this means they're not isolated. Really, there's a lot of activity around these muons. So just very briefly comparing the different working points. On the left side is the loosest isolation working point, which has a reasonably high efficiency, going almost 100%. On the right side, this what's called prompt lepton BDT, which has a lower efficiency. But if you look at the table, for example, above 20 GeV, it provides something like a factor of 10 improvement in the rejection of the heavy flavor background. Now, very briefly, I'm going to talk about the results of measuring muon efficiency. So efficiency is measured independently for every step in selection, which typically there are 3 steps. Identification selection, which is tight, loose, or, for example, medium working point, associating a muon track with a vertex, and then isolation selection. So here on the left side, you can see the 3 different selections shown separately in the colors, and then in black is a combined efficiency. You can see that overall efficiency is dominated by the isolation selection, because typically that's one of the stringent criteria. Then the simulation is corrected by using the scale factors, which is just ratio of data and Monte Carlo efficiency, which measured as a function of several variables. Here in the middle is shown that, for example, efficiency as a function of distance to the nearest jet. And you can see that there is some variation in efficiency, and typically there's uncertainty on order of 1%, which is projected to the 1D, because typically it applies a function of 2D. So for example, if you look as a function of muon momentum on the right side, in some region of the phase space, we have an uncertainty reaching as low as 0.1 or even lower uncertainty for this particular selection. And systematic uncertainty typically comes from a tag and probe method itself, or modeling nearby jet for isolation selections. Also, here is a summary of the measurements of the JAPE size. So here's the measurements which summarize different eta regions of a detector, as well as in each beam it shows different momentum beams, and you can see overall there's a good agreement with some variations. And if you look at the systematic uncertainty on the right side, it reaches 10% at the very, very low momentum, but typically another 1% for momentum beams above, let's say, 4 or 5 GeV. And then the final word before concluding, we also check stability of muon efficiency calibrations. So for example, it's been measured as a function of number of interactions per event or as a function of integrated luminosity. So the number of interactions typically we have an order of say 36 collision per event in 2018 for Atlas and CMS. And if you plot efficiency function of number of collisions, which of course extends to higher values due to fluctuations here, in this case, up to 80 collisions per event, there's a small data Monte Carlo difference due to normalization, but it's a very small because the axis is very zoomed. And it's, if you compare data Monte Carlo ratio, it's very stable as a function of a number of interactions here for the median working point. Also the same as a function of integrated luminosity, which basically is a function of time, which is quite stable. And there are some variations, for example, vertex association, and that's due to the fact that there is a different data Monte Carlo modeling, but that has to do to different amount of interactions per event, because in different years we have a different amount of so-called pileup. And this leads to still very small and systematic uncertainty of less than 0.1%. Now to conclude, I've presented new measurements of muon reconstruction identification efficiency measurements, which used a large number of Z and J psi events. We have also optimized new working points. We provided new isolation new isolation selections and working points using both multivariate and particle flow algorithms. And this measurement is already used, so will be used for a large number of upcoming Atlas results that use muons. So here is a link to the conference report note, which was just released yesterday for this conference, in case you're interested. And thank you very much for your attention.
Thank you very much. Very nice presentation. Please, questions. I will also check the Mattermost. Okay, so maybe I would ask, what are your expectations for the high luminosity for example, 200 or even more pileup?
Yeah, it's a very good question. Unfortunately, I don't have these results. So you can see here, for example, that I mean, this is a current detector, but even going up to 80 interactions per event, we have a quite good model and also good stability. Of course, for the high luminosity LHC, we're going to have a new inner detector, significantly improved with entirely new silicon detectors. And also we're going to have additional layers in the muon spectrometer for triggering. So overall, we expect similar performance. Of course, for the isolation selections, which are more dependent on pileup, we're going to have slight degradation, but I think at the moment I don't recall exactly what will be, but I think that it's still sufficient for the physics program.
Okay, can also the upgrade of the calorimeter somehow help you? For example, the higher granularity of liquid argon calorimeter.
I would say not, because typically for the tagging this. For construction itself, we tag the muons with the last layers of calorimeters, right? Okay. Which, for example, in the barrel region is primarily the tile calorimeter, especially in the region, in the central region where we lack muon spectrometer coverage. I would help with triggering, because I think going to be more sophisticated use of calorimeters for triggering muons, and so there I think we expect to see some improvements. But again, I think it's going to be small, and I don't recall the exact details.
Okay, thank you very much. Thanks. So we will go to the second talk, and it will be for CMS, performance of the reconstruction and identification of high momentum muons collected with CMS in 13 TeV data by Carlo. Yeah, if you can try to go to full screen.
Okay, can you see it?
Yes, it's good now. Okay,
so my name is Carlo Battilana, and on behalf of CMS, I will talk about the performance of reconstruction and identification of high-energy muons with run-to data. So just a few words about detection of muons in CMS. Muons are, of course, tracks with a curved trajectory because of the magnetic field, which get reconstructed both in the silicon inner tracker, consisting of pixel and strip detectors, and in the muon system, which consists of different types of gaseous detectors, which equip different regions of the detector. For example, we have drift tubes in the barrel and cathode strip chambers in the end caps. They both serve as a tracking detector and have trigger capabilities, and we complement the two with resistive plate chambers, which cover the end cap up to eta 1.9 and are mostly used in the trigger. Now, a few words about the importance and characteristic of high momentum muons. why it was critical to study those muons over run2? Well, essentially, the first point is that LHC increased the center of mass energy in proton-proton collision from 8 to 13 TeV, and this brings a large increase in the cross-section of hypothetical high-invariant mass resonances like Z' and W'. So it was a must to search for high mass resonances over run2. And we collected a huge statistics of more than 140 inverse femtobarn, which was good for physics, which allows to probe corner of the phase space like high momentum muons with high accuracy. Essentially, how those muons on the other end different from the lower energy ones and why they need dedicated reconstruction and studies. The first point is that the muon curvature and the multiple scattering along the trajectory of high momentum muons get reduced. So the muon system contributes to the measure of the PT. You can see it in the bottom plot. But this also implies, on the other end, that we must know accurately the alignment of tracker and muon system to get the best out of the PT measurement. On the other end, the iron yoke of CMS is indeed iron, and the critical energies of muon in iron is around 350 GeV. This means that for high momentum muons, radiative contributions become important in the counting of the muon energy loss. This implies that muons can develop some kind of showers, and we developed showers method to tag the showers in the muon system based on it and segment multiplicities. All the results I will discuss in the following slides are documented in this paper I'm linking below. And if I made you curious about performance of high momentum muons with CMS, please have a look at the paper after the talk. Okay. Getting to the details of the reconstruction. The reconstruction of the muons starts in the muon chambers, where we have clusters of RPC rekits, and out of the multiple layers of DT and CSC, we build straight light segments. We combine all of them in the muon system to build a so-called muon system standalone track. In parallel, the tracking does its jobs and we get inner tracker tracks reconstructed. Then the muon reconstruction tries to combine the inner tracker and the standalone tracks to refit them all together using all the hits that it founds to build a so-called global muon. Alternatively, we propagate the inner tracker tracks to the muon system, and if we find a match with the DT and CSC segments, we build what are so-called tracker muons. Plus, there is more. We have dedicated IPT refits, which I will discuss more in the next slide. Then muons are included in the CMS particle flow event reconstruction, though it's not a topic for today. And as for Atlas, we have muon identification and isolation variables we use for ID and isolation. Okay. What about these dedicated IPT refits? For muons with at least few hundred of GeV, we say that the muon chamber contribute to the PT measurement. But what practically happens is that in some cases, the out-of-the-box PT from global muons might be suboptimal because global muons are tuned for high efficiency, and at times, for example, in presence of showers, they can retain spurious hits that can spoil the PT measurement. Therefore, we have different track fit strategy to achieve an optimal performance. The first thing is we can use the fit from the inner tracker only, or we can combine the fit from the inner tracker with the one of the innermost muon station, which is the one bringing more information about the PT. Or we can be picky. Starting from a global muons, if we see chambers with many hits per layer pointing to a shower, we reject the hits that are less compatible with the muon track. Or we can start from the inner track and extrapolate to the muon chamber and associate the segments that are compatible and refit every time. And if we see that at a certain point onwards, the segment falls away from the extrapolated trajectory, pointing to a kink because, for example, showering in the iron that caused the large energy loss, we can truncate the extrapolation with the dynamic truncation approach. Of course, we have many refits, but we have to serve just one to the muon reconstruction and to the physics analysis. And the choice is given by the TuneP algorithm, which at low momentum takes the inner track because of the multiple scattering, whereas at higher momentum looks the quality of the tracks from the IPT refits, for example, the chi-square or the sigma PT over PT, and selects the best track candidate. Just a plot to convince you that we need TuneP, which is comparing the performance on global in pink and green with the one of TuneP in blue and red, respectively for events with no shower and with one shower tagged in the muon system. The metric I show is the fraction of events where the curvature measured in reconstruction is more than 20% away than the one measured at generator level. And you see that UMP clearly outperforms the global reconstruction. Now, getting to the performance of the physics object, starting with scale and resolution. As we say, the IPT muons have a small curvature, so little distortion in the estimation on curvature can induce large biases in the PT. And what we mostly fear at high momentum, it's a constant shift in the curvatures due to residual misalignment of tracker and muon system. To measure the consistency of the scale between data and Monte Carlo, we use a method, which is called generalized endpoint method, that works as follows. We plot the curvature, the Q over PT distribution for IPT muons for data and simulation, as you see in the bottom left plot. And simulation has no scale bias because we build it like that. And we inject an artificial curvature bias in step to the original Q over PT distribution. This shifts to the left and to the right the V-shaped distribution of the simulation. For each injected bias step, we perform a chi-square test to compare data and the distorted Q over PT distribution of simulation. And we decide that the curvature bias in data is the one minimizing the chi-square distribution function as a function of the injected curvature. In the bottom right of the slide, you see a plot that run these methods in being of phi and eta, and you see that the bias is overall small, less than 10%, and mostly consistent with 0, with the exception of the very high eta region. Once we are sure we have no scale bias, we measure the resolution either using cosmic muons. Cosmic muons are traversing CMS from top to bottom, and if they pass close to the interaction point, they essentially leave two muon tracks reconstructed, one on the bottom half and one in the top half of CMS, and out of the Q over PT relative residual between the upper and lower leg, we have a direct measure of the momentum resolution. Cosmics have a rather high PT spectra, so they allow to prove rather high PT, but they mostly illuminate the barrel. So we complement this method with a method that it's using boosted ZDKs and plots the width of the Z peak as function of the PT of the leading muon that you see, for example, in the right plot. And we use this method to study the end cap and to complement the barrel measurement. The data Monte Carlo agreement, it's in general very good, with the main exception, which is a discrepancy around 15% we found in the ITA region for the 2017 dataset, which was due to a non-optimal alignment of the tracker and the muon system. Getting to the other side of the performance measurements, the efficiency. So in the Atlas talk, you heard about the tag and probe to a very good level of detail, so I will not spend further words, but I will say that we use what is called an extended tag and probe technique, where we mostly tune the selection, adding cuts like PT balance to select the non-resonant tail of the Rayleigh events, and we apply tight isolation cut both to tag and probe and proximity cuts about the proximity to the vertex, so that we clean up the sample and we can afford the cut and count tag and probe approach instead than a fitted one. And in this way, we measure both the reconstruction and identification efficiency. You have plots for reconstruction and ID in the bottom left and bottom right part of the slides. For the reconstruction, we see a mild dependence on PT for large eta, which is of the order of 3%, whereas the efficiency in the barrel is flat with PT with the data Monte Carlo scale factor, which is larger than 99%. For the ID, the overall efficiency is 98% in data with a 1% data Monte Carlo discrepancy, flat as function of PT, both in the barrel and the end cap and in each given bar eta beam that we probed. We also measure with the extended tag and probe method the trigger efficiency, but in this case, we can also profit of datasets which were collected with non-muonic triggers, like gamma triggers, that have inside a well-reconstructed muon passing reconstruction ID and isolation criteria. The two methods, as you see in the top left, give a very good agreement. We measure the efficiency with those two methods in data and Monte Carlo, and we see that the overall efficiency varies with PT between 92 to 82%, and the scale factors vary depending on PT and eta between 98 and 90%. The inefficiency, the data Monte Carlo scale factor, and the PT dependence of the level 1 plus ICHEP performance are mostly due by the level 1 trigger. Okay, this gets me to my summary. I hopefully have convinced you that high momentum muons have peculiarities, which imply the need for dedicated algorithms for construction and identification, and that run 2 provided the ideal scenario to probe the high energy regime. Based on these 2 information, CMS has studied the performance of high momentum muons using run 2 data, and the results are documented in the paper I'm linking. Overall, we see a very good performance. I will not repeat all the metrics the figures that I already discussed, but I will just highlight that the work we performed also highlighted areas where things can be further improved, and we are working hard to prepare for run 3 and achieve even better performance. Thank you.
Thank you very much, Carlo. Very nice presentation. Please, questions. I will check also Mattermost. Okay, I think that CMS in general is like a detector that is very much optimized for the detection of muons. But you still mentioned that high PT muons are problematic, of course, because the slight difference in the curvature can mean a lot of difference for PT. So what would be the changes, or what you plan to upgrade actually to increase your efficiency and
well, efficiency it's already rather high for the ID and the isolation. For example, the ID, you see, it's more than 98% in the MCAP and 98% more or less in the barrel. We have some features, for example, this inefficiency above eta 1.6 for the reconstruction, which is a 3% effect, which is mostly algorithmic. We have inspected the inefficient events, and in principle, the information to reconstruct the muon is there. So it's tuning of the algorithms, the thing that we need to do. For yes.
Okay, and the effect of high luminosity LHC, what you plan for this?
For the luminosity LHC, we don't have specific plans for the IPT. In the barrel, the occupancy even at high luminosity LHC is not so high, so the performance of the existing detector is gonna work fine. In the NCAP, of course, we are complementing the existing detectors with gems in the forward region and with IRPCs, so we will have more points along the muon track. The resolution of the gem is such that they can improve the measurement. So we expect some improvements because of gems, but not dramatic ones. Whereas the RPC, it's mostly, as I said before, a triggering device. We not change the story.
Okay, and will the new inner tracker of the CMS that is under preparation for high lumi will help you with this?
The inner tracker, as far as I recall, the metrics that were shown in the various TDR, it's improving the momentum resolution. Yes, so we will have some improvements from the inner tracker, but it's inheriting the detector improvements. It's not that we are RICO-wise thinking of dramatic changes on the side of high momentum muons for a luminosity.
Okay,
can I ask a quick question? Sorry.
Yes, sure.
On slide 12, maybe.
Yes.
So I was wondering, what is that drop in efficiency above 400 GeV on the left side?
So the drop is mostly due to the level 1 trigger, especially in the barrel and in the overlap region. There are a few things that contribute to the drop. The fact that we start showering and we lose efficiency to build the trigger segments in single stations, so we lose some efficiency in that sense. And this is important in the barrel, in particular, where we have less coverage of the muon stations because we have cracks between the detector, and also as the level 1 trigger needs to measure the momentum of a muon in case of showering and in case of missing layers. The resolution in the momentum might be reduced, so the PT cut that you apply at level 1 can also bring a few percent inefficiency at high momentum.
And will this get fixed with maybe, as Jerry was asking, high luminosity LHC in a new trigger system?
So with the new trigger system, this will change, yes, because you move from a paradigm where the muon system needs enough stations to build a track and needs to measure the momentum. If the momentum is measured by the inner tracker, the inefficiency due to the momentum measurements will get significantly reduced. Plus, we are also developing track plus segment trigger. So it means that you don't need many stations of the muon system to be involved to build the track plus segment trigger. So the trigger should significantly improve in this respect at high Lumi LHC.
Okay, thank you.
Thank you very much. Thanks a lot. And we will go to the third talk. So it will be Giovanni and will inform us about the GEM stations for CMS.
Yeah, hello everybody. I'm Giovanni. Let me share in a second the slides and go to full screen. Okay,
Yes,
can you
perfect.
hear me well and see?
Yes.
Okay, good. So let me start. I will present to you the commissioning and the prospects of the first GEM stations at the CMS experiment on behalf of the CMS collaboration. So starting from what Carlo already explained to us, the present CMS Compact Muon detectors are CSCs plus RPCs covering between eta regions 0.9 and 1.6, but we only have CSCs that cover down from 1.6 down to 2.4. From 2027, we're having high luminosity LHC, and the instantaneous luminosity will grow up to 5 times 10 to the 4 hertz per centimeter square. And this will be an increasing luminosity greater than 5 times the design. So we need an upgrade of the current muon forward system in order to increase the redundancy in the end caps. We want to improve the momentum measurement in such a low region of magnetic field. And we want to control the increased trigger rate and to sustain higher particle flux. The installations that we're going to have are GEM in the first and the second station of the end caps and improved RPCs in the third and the fourth. We could hear more about this in Daniele Fasanella's talk on the CMS muon system upgrade that took place on Tuesday. So let me go to GEM. Now GEM is an acronym that stands for Gas Electron Multiplier. And the key element is the GEM foil, which is a 50 microns thick copper-cladded polyimide foil. And you can see from the picture that it has holes etched in an hexagonal pattern with a pitch of 140 microns and a diameter of 70 microns. So out of foils, we build GEM chambers, which are gas detectors. So ionizing particle traversing the detector ionizes the gas. And via high voltage, we have amplification process inside the GEM holes where the electric field is around 60 kilovolt per centimeter. And out of 3 foils, we make triple GEM chambers in which we have 3 amplification stages. The performance of these detectors are rate capability on the order of megahertz per centimeter square. GEM chamber efficiency is greater than 97% for MIPS. And we've seen no aging effects after the foreseen integrated luminosity of high luminosity LHC. So this makes GEM chambers perfect candidate for the CMS muon end caps. Now, how we're going to integrate this technology into CMS as a first implementation is the GE11 chambers. 11 because it's the first station and the first ring of the CMS muon end cap. They're going to cover between 1.5, 1.6 to 2.2 eta region. They're triple GEM chambers. We use argon CO2 70-30% gas mixture. And they, for the first time in GEM technology, they cover a large area of the order of the meter square. Out of 2 single GEM chambers, we build the super chambers, which are 2 coupled chambers. And in total, we're having 72 super chambers, 36 per end cap, each one covering 10.15 degrees. And this accounts for overlaps between neighboring chambers. We have a digital readout and 24 readout sectors per single chamber. So now the integration plans of GEM in CMS, we started early in the days of 2017 with the slice test, which was commissioning of 5 GE11 detectors in CMS. Basically, today we're having the installation of the GE11 chambers during this long shutdown 2. And then by the end of long shutdown 3, we're having GE21 and ME0, which I call the expansion pack of GEM. More about this, we could hear On Wednesday, the Elizabeth Starling Stock, Electrical Discharges Mitigation Strategies for Future GEM System GE21 and ME0. So starting from the early days of GEM in CMS, so the slice test was a demonstrator with 5 super chambers installed in 2017, which was operational until the end of LAC REN 2. And it had the goals of acquiring installation and operation experience and to develop the integration with central CMS online systems like DCS, DAQ, and DQM. You can see here an event display of muons that cross the end cap of CMS. And in green, we have CSC hits. In red, the muon track, and in blue, the GEM associated hit. Some results from the slice test. The first one I can show is the efficiency of one of the chambers that we had installed, namely the 28 layer 2, as a function of the eta partition. Eta partition are just the eta regions in eta in which we divide our readout of the GEM. We have 8 of them. So you can see the efficiency starting from the first one, which is the largest one, and down to the 8th one. Okay, so this data was taken in run 2, 2018, and the cuts on the global muons that were applied were transverse momentum higher than 20 GeV. Then we took the tracks and we extrapolated them to the GEM GE11 chambers installed. So you can see that the efficiency was greater than 90% basically in all the eta regions, but not in all of them. And this was due to inactive strip fraction, and I will tell you more about this in next slide. So here you can see that we experienced during the slice test some damages to our front-end readout channels. These were due to high voltage discharges that we had across the GEM foils, that each one of them has a chance to propagate towards the readout. And the energy that the discharge has can damage the front-end electronic readout channels. And in the slice test, we saw that we had a probability higher than 90% to have damages after a propagation of discharge towards the readout. You can see on the left the plot for each of the chambers installed, and you can see that it's very dependent on the single chamber. And for some of them, we reached, well, only like per mil of channels lost, and for others more than 10%. So this was triggering a study to minimize the probability of the discharges that could propagate to the front-end channels to damage them. So it was studied some additional resistors or diodes to be applied to our front-end chips, which are the VFAT3 hybrids, to improve their characteristic of sturdiness. So you can see that we have studied many solutions, and the best one we found was to add 470 ohm at the input of the channels as a protection to have a damage probability below 3%, coming from 90% that we saw in the slice test. So now that we know that we have all the components to build the GEM super chambers, I will briefly go through the process. So initially we have the assembly of a single triple GEM chamber. We go to the quality control tests that are there to ensure the gas tightness, the high voltage stability, and assess the gas gain performance. Then we install the electronics on the detectors, and we check to ensure the proper functionality of them. Then we take the 2 single chambers and we couple them, matching their gain into a super chamber. Then we have a final QC for the super chambers, which is a cosmic ray test. You can see on the right the picture of our test stand. It has 15 super chamber slots, and top and bottom we have seen the layers as triggers. And all services are like in CMS. And there we fully configure the detectors, and we take cosmic muon track, reconstructing them and checking many performance parameters of our chambers. So one of the results I will show you is the efficiency of the chambers in the 24 partitions of the readout. And you can see that basically for this chamber, which was a long chamber CERN 35, we have all the 24 partitions above 94, 95% of efficiency. and which is uniformly good efficiency. On the right, you can see an event display in the cosmic stand for one muon that was crossing chambers that were installed there under test. And apart from what we can see as uniformity, we can also study the average efficiency per chamber versus the high voltage working point. And on the left, you can see the plot of the sigmoid of efficiency against high voltage applied. And to the right, you can see the spatial resolution versus the high voltage. And we have seen basically for all the working points, a spatial resolution that's below 200 microrads, and what has been required to improve the trigger performance was 300. So we're well within specs, and especially at the working point, we are basically around 150, which is half of the requirement. The average efficiency is above 98%. So we have defined the optimal working point of our chambers. Now, I will give you an overview of the GE11 status and some conclusions. So GE negative 11 negative end cap, we have installed all the 36 super chambers, and it has been completed in September last year. You can see on the right a picture taken during the installation of the negative end cap chambers. And the pre-commissioning phase has been done. All the signals from the 3072 channels of each of the chamber has been recorded, and the noise level has been assessed, and it's well under control. But then unfortunately, the commissioning was delayed due to COVID stop. For what regards instead the positive end cap, we're validating the 36 super chambers, and it's on its way to completion. Indeed, the installation is ongoing, and we will be finished by September of this year. And the plans that we have for commissioning is then the complete integration of the DCS, the DAQ, and the DQM in the central CMS systems, the full configuration of the front end and back end electronics, and high voltage training of the chambers, and finally latency and efficiency scans to determine the optimal working point. Thank you.
Thank you very much. A nice presentation. Questions? I can see Ruston.
Yes, hi. Thanks for this nice talk. I have a question on this damages, maybe on slide 8. The first question is, so I think it seems to be there are differences among chambers and whether or not they're susceptible to damage. So I was wondering, do you understand what is it about the chambers that makes some of them more likely to have this damage compared to others?
Right. So this is the total fraction of channel lost. Now, I told you that the chance that we had to lose channels was more than 90% after the discharges propagated to the front end. But now, of course, one important parameter that plays a role is the rate of discharges that you have and the rate of propagating discharges. So for some of the chambers, you can see we had a larger one. So more discharges and more channel loss. And for others, they were basically cleaner as chambers, so less chance to have discharges and therefore safer electronics.
But do you understand why some of them were cleaner or not during the production?
Well, not really. Now we cannot really record the number of dust particles that we get inside of a chamber, and also it depends on the gas. If it is perfectly clean, it depends on the pipes that give the gas to the chambers and so on. It's really, really hard to track down all the different steps that led to this. But for the production, we're making sure that the chambers are really well treated, let's say.
Okay, thanks. And maybe just one follow-up question on this. So you mentioned on the next page that it's 3% probability for the damage to impact it. But let's say if you integrate it over the 15 years and 3,000 or more femtobarons of hydrogen steel HC, what will be the total probability for having a chamber damage with this, even after this improvement in your front ends?
Yeah, right. So it's really hard to foresee like the fraction of channels lost because it's basically random events, and it really depends on the cleanness of the chambers. We're having, therefore, the high voltage training and the cleaning of the foils after installing the chambers in CMS. So we're not going straight to operations, but we're doing all the preliminary steps to ensure that the chambers are well cleaned and to reduce the chance of having discharges in the first place. Now we know that if we're having some discharges, we have out of those the 3% of chance of damaging channels. But the rate has to be assessed during the operation, and especially with highly ionizing particles that cross our detectors that might trigger discharges. So it's, well, I think it is something that we have to assess during the operations. So
okay.
Sorry for not having a full answer to this, a number, but this is to be seen.
No, I understand. I think if it's okay, Jerry, maybe I can ask one last question. I don't want to hug the mic.
Sure, you can, yeah.
I guess then I guess there's a chance that some of these chambers will get damaged in situ, right? Do you have a capability of, say, during a winter shutdown to go in and remove the damaged chamber and replace them? Or this, once you put them in, it's not possible to replace them?
So what I can tell you for sure is that all these chambers will be installed now, and then they will be unmounted from CMS during the long shutdown 3 for sure. Because we're having the upgrade of the HG-cal on the end cups. So the hadronic calorimeter would be completely substituted, and it's a major piece in the what we call nose of CMS. So let me go to the first slide. Maybe you can see it better. So it will be in front of GE11, and therefore the chambers has to come down. And we will be able to act and react on such experiences.
Okay, thanks. And then just again to say good luck. I know from other talks that how much work it was in the past couple of years to commission this. So I wish you good luck to complete this project despite the situation. Thank you.
Yeah, thanks a lot.
Thank you very much again for nice presentation. And we will now move to the fourth talk. We are going back to Atlas, and we will hear something about new small wheel. Dimitri?
Yes, hello, can you hear me?
Yes, we can hear you.
Okay, let me share the slides. Do you see it?
Yeah. Now
Okay.
it's perfect. Thanks.
Okay, so I'm going to discuss today about the large size multi-gap resistive micromegas which are going to be used for the new small wheel of Atlas experiment. After a small introduction, I will concentrate more on the construction of the chambers, their installation, and the quality assurance of them and the commissioning. You see here in the blue areas that the new small wheels are going to change the small wheels that they exist at the moment. The photograph with the 2 sectors installed. Right now, as we are talking, a third one is going to be installed. The new small wheel is going to have 2 technologies, the Micromegas, primarily for tracking, and STGC, primarily for trigger. It is the main Atlas upgrade of phase 1, but it is designed also to operate at a high luminosity LHC. As you can see, it covers half the angular space in durability, and it has 10 meters in diameter. The main motivation for changing the existing small wheel is to reduce substantially the single muon trigger fake rate at high rates, maintain the excellent efficiency and resolution of the tracking at these very high rates up to 15 kHz per centimeter square, and also having 16 inactive layers in order to have enough redundancy for tracking and pattern recognition. The geometry of the new small wheel is going to be similar to the geometry of the current small wheel, so there are going to be 16 sectors per wheel, 8 small and 8 large sectors. Each sector is composed by 2 micromegas wedges with a multi-layer, 4-layer each in each wedge, which are going to be placed on a support aluminum structure, which we call the spacer frame, and 2 STGC wedges on the sides to make the complete sector. Concerning the Micromegas Operational principle, it's a micropattern gas detector which has 2 gas gaps. One is the drift gap, which is 5 mm in wide, and the other is the amplification gap, which it is 120 microns in height. They are divided by the metallic micromesh. The new small wheel Micromegas are resistive for spark protection. That means that the readout strips, which are they are here, they are covered by a resistive layer with also resistive strips placed on it, and the high voltage is applied on the resistive layer. The pitch is either 425 microns or 450 microns, and the nominal high voltage operation in the amplification is 570 volts, which gives an electric field of the order of 45 kilovolts per centimeter. The baseline gas mixture, which is foreseen for their use, is 93% argon and 7% CO2. Now, there are 128 modules, or quadruplets, as we call them, of 4 different types to build new small wheels. You see here large sector, large module 1, which is produced in France, LM2, which are produced in collaboration with Greece and Russia, a smaller module 1 in Italy, and a small module 2 in Germany. The surface of each module per layer is 2 for the small layers and 3 square meters for the large layers and modules. And the total area, though thus covered by the Micromegas, is larger than 1,200 square meters. Now, concerning the construction, in order to build a quadruplet, that means a Micromega with 4 layers, there are needed 3 drift panels. 1 is double-sided, and 2 readout panels, which are both double-sided, one having the ETA strips for the precision coordinate, and the other inclined strips for having also the second coordinate. And these are put together to make a 4-layer Micromegas quadruplet. Start to finish, the building of one of them is take 10 to 12 weeks, but as you can see in the workflow, there are also a lot of processes that can be done in parallel. Now, there is a very strict quality control program that is followed in all construction sites, also per panel and also of the whole quadruplet. The thickness, the planarity, the gas tightness, the alignment between different layers, the high voltage stability, the efficiency, and the gain homogeneity are measured. So here you see 4 examples of this kind of measurements from the 4 different construction sites, but similar results can be obtained from all of them. So here you see the gas tightness for the SM1 type of modules, the thickness of the SM2 with an accuracy of 200 microns, the panel-to-panel rotation of LM2, which does not go above 0.1 millirad, and the measurement with transform of the alignment in the LM1 with accuracy of micrometers. Now, you all probably know that the first prototype was having high currents and charges, so there was a very dedicated and focused R&D program to find out solutions about this and mitigate the effects. And as you can see here, the outcome of this was a detailed quality control of the PCBs, targeting imperfections. This was the theme of the poster by Luigi Longo. Thorough cleaning and drying of all the panels prior to assembly, polishing of the mesh in order to minimize impurities, and also reduce the relative humidity inside the chamber by gas flushing. It was also found at early 2019 that there is a sufficient spark suppression due to low resistivity in localized spots exactly at the edge of the active area, and therefore a passivation technique was applied from a point on to all the modules. But you can see all the details about this in the Lorenzo stock just later on. At CERN, the integration and the commissioning activities are performed in two laboratories, 2 buildings. One is the integration site where the components are tested, the mechanical assembly taking place, the integration and calibration of the electronics, as well as the final cosmic ray test to get the response of the whole detector. And in the building 191, when the sectors are installed, after joining with STGC, they are installed on the new small wheel, the services are connected and the final surface commissioning takes place. all about the integration activity you are going to hear Theo talk, and all about the G++ study and activities you are going to hear from Lorenzo talk. Now, concerning the performance and the commissioning of the high voltage, the nominal high voltage, as we have said, is 570 volts for the Micromegas. 128 high voltage sections are existing per sector. Each one of them is tested for the current and the spark rate. If a section is not able to be stable at the nominal high voltage is connected to a hospital line with reduced high voltage values. And you see here the experimental results of the efficiency as a function of the layer efficiency of the module produced so far as a function of the high voltage value. From the sectors that are built so far, 90% of the high voltage sections are set to nominal value, 9% at reduced value, and less than 1% are disconnected. Now, concerning the installation, probably it's easier to see it in pictures. There is a grappling tool designed especially for this purpose, which is grabbing the sector. We'll then adjust the center of gravity of the whole system, move towards the wheel with the crane, with the help of the crane, adjust the orientation according to the particular sector which is going to be installed, insert it in the position in the new small wheel, fix it in 3 places, and then the sector is ready for survey and alignment. As soon as the sector is installed on the wheel, all the connections and their validation take place, and you can see here some examples of measuring the humidity at the exit of the detector gas lines, which is adjusted according to the flow of the gas. You can see here that we measure all the temperatures of the detector, an example of opening and turning off the electronics and the difference in the temperature of the input and output lines. And also, of course, all the electronic components are monitored. As soon as all this is established, we check out each one of the more than 65,000 readout channels per sector, both in what concerns the readout part through the L1 UDCs cards, and also we check the readout of the high luminosity LHC working, and also the trigger path. Now, the first test is to measure the baselines. This is very important because it can, in the integration side, it can check for misalignments with the electronic strips and the actual detector strips, which are fixed as if we see them. And also because with the baselines, you can have the possibility to identify pathological channels, dead or noisy. A comparison of the baseline reading is done between the integration and the installation site in order to establish a well understood level of the noise in the 2 areas. After that, we set the thresholds in each of the VMM, which is the basic readout chip, and each channel inside each VMM. And then we check the electronic response and the detector performance by doing various kinds of runs. And you see here some examples of the occupancies in a pulse run, where almost all the channels are responding, a random noise run, and a cosmic run. In particular, the cosmic data are used also to make efficiency map of the different layers, and this was also reported in Gabriel's talk, but I just flash it here. In this way, we can identify the areas which are set to reduced high voltage, as the one you see here. And from the 48 layers from the 6 micromega sectors that they have been signed off so far, 80% has efficiency above 90% layer efficiency, and 20% have efficiency above 80%. The last test is the trigger path test, where we configure all the ARC chips on the ADDCs, the cards which are responsible for transmitting the trigger signals in the micromegas. Then we perform connectivity tests between all the channels and the art chips. And as a third step, we validate the coincidental logic by Tel's pulses. Further on, this will be combined with Micromegas SDGCs to be applied. This gives me to my summary. I would like to stress that NSW is the largest Atlas Phase 1 upgrade, but also the largest Micromegas project so far. Considerable effort has been invested to understand and mitigate the high voltage stability problems, leading to significant improvements in the behavior of the large area resistive Micromegas. The construction and integration of Micromegas detectors continue at full speed after the restrictions due to coronavirus were relaxed. The average layer efficiency of all sector builds so far exceeds 90%. Most of the commissioning procedures are finalized and are performed in routine mode, and the level of dead or noisy electronic channels is well below 1% and 2% respectively. Most of the modules, the quadruplets for the electronic and all the electronic components of the 16 sectors of Trident A are available. 2 sectors have been already installed and 1 is being currently installed and are currently commissioned. Therefore, we believe that the goal of having Site A ready in spring 2021 is achievable. However, the successful accomplishment of the second site, the Site C, in time depends also on the situation of restrictions due to COVID-19. Thank you very much for your attention.
Okay, thank you very much. We have time for 1 or 2 quick questions, please. Okay, maybe I would like to ask, you mentioned that you have a problems with the humidity. So is it like you have a problem with the humidity in your gases that you are using, or is it surprising, or you have expected this?
Okay, the chambers that have some imperfection are more vulnerable to humidity, but humidity is a problem up here because we're in both the labs we're using for the integration of the installation, the humidity of the atmosphere can go up to 70%. So it is a problem that we mostly face here and not the cover. Okay.
And you mentioned that you are somehow cleaning the PCBs. What is the method that you use for cleaning PCBs and meshes also?
Okay, there is a very strict protocol for the cleaning procedure. At the moment, most of the sites they use sieve for cleaning, and after cleaning with a very soft material, they are also drying the PCB in order to not to have material humidity inside. And for the meshes, we are using brush in order to make them as flat as possible, in not to have something extending out of them.
Okay, thank you very much. Are there any other questions?
Yeah, I have a quick question. Is it correct to assume that these high voltage instabilities are the main reason for the delay in the new small wheel installation? And is it now under control, and from now on you can just move forward with a stable plan?
It is true that it was a part of most of the delay, that we had to do several tests and understand the situation.
Okay, but from your talk, I had the impression that now you think you have understood enough and it's under control and you can move forward.
That is true. That's why we are
already
finished most of the small sectors on Site A, and all the modules for most of the modules for the large sectors are there.
Okay,
waiting.
Thank you. Thank you.
Okay, thank you very much again, and we will go to another talk which will inform us about the radiation and gas studies of these micromegas. So Lorenzo.
Hello, so let me share my screen. Okay, I should be sharing now.
Yes, perfect.
Okay, so I will go on talking about the Atlas New Small Wheel, and in particular this time I will focus on irradiation and gas studies on Micromegas production chambers for the Atlas New Small Wheel. So just a very quick introduction, as you have already heard the project from the previous talk. We are talking about the Atlas small wheels, which are the first stations of the Atlas forward and backward muon spectrometers. So the new small wheels are actually completely new detectors provided with new electronics, and the main reason is to be able to cope with the high luminosity that is going to be provided by the high Lumi LHC operation. And this is one of the biggest upgrades of Atlas during the long shutdown too. So the new small wheel substructure is depicted on the left of these slides. We have 2 wheels, and each wheel has 8 small sectors and 8 large sectors, so for a total of 32 sectors. And what actually a sector is what is depicted in the center of this slide. A sector is composed of 4 different detectors. We have 2 internal Micromegas detectors dedicated mostly to tracking, and 2 external STGC detectors dedicated mostly to triggering. And if you take a single layer of Micromegas chambers, they are actually composed of 2 detectors. So for a small sectors, a small layer is made of an NSM1, standing for small module 1, and NSM2, and the same is valid for large modules. They are divided in LM1 part and LM2 parts. So the Micromegas detector production is an effort going on in 5 different countries: Italy, Germany, France, Greece, and Russia. So the Micromegas detector technology was the one chosen for the new small wheel, for the tracking part of the new small wheel. And here perhaps I just want to add and specify a bit better that we are talking about resistive Micromegas. So actually the charge that is collected at the avalanche amplification gap is collected through resistive strips. And below resistive strips, there is an insulator, and below the insulator, there are readout strips that are copper, so copper based. So the signal is actually capacitively coupled to the readout strips. For each, we want for a double wedge, 8 tracking hit provided by the Micromegas. So this means that each layer of the Micromegas detector should provide 4 tracking hits, and this is done with the scheme that is depicted on the right part of the slide. Each detector is made of 2 readout panels, and each readout panels is a readout both on the upper part and the lower part. So at the end, we managed to have 4 tracking hits per Micromegas detector. So the quadruplets construction is a very delicate procedure that goes from a readout panel assembly to drift panel and mesh panel assembly, and eventually they are integrated in the detector, and then chambers are sent to CERN for integration. And please refer to Dimitri's talk about this subject. Once they arrive at CERN, they are integrated, and the integration workflow is a quite long procedure that goes from HV and irradiation testing to alignment platforms mounting to detectors integration and eventually cosmic ray testing. And please refer to Theodoros' talk immediately after mine about this subject. Instead, I will talk about the irradiation and gas studies. So here a key facility is the gamma ray irradiation facility, also known as GIF++. It is an irradiation facility situated at the CERN Prevesen area. And inside the bunker, we have a 14 terabecquerel cesium-137 source that basically provides a spectrum of 662 keV photons. And the very nice thing about GIF++ is that it provides a set of filters that are lens-shaped. So the irradiation field is constant per planes that are perpendicular to the source. So it is a facility dedicated to large area gaseous detector testing. So the irradiation test goes from the conditioning that takes about 24 hours for a complete refill of the chamber, and we have to keep the relative humidity below 12%. We have a dedicated detector control system to monitor and power each sector, and we have 40 sectors for type 1 modules and 24 sectors for type 2 modules. And the very first step was to actually be able to understand the photon flux within GIF++. So here the best knowledge comes from simulations of the GIF++ facility. Here you have a reference for it. You see that the maximum radiation can go up to 10 to the 8 photons per centimeter square per second. And we actually performed a real rate measurement at a distance of about 1.5 meters from the radiator walls. We use an auxiliary TGC detector because Micromegas chambers are only tested HV-wise. We don't have the final electronics to read out the chamber inside GIF++. And the results that we got in 2019 are quite interesting. If the source is not attenuated at all, we have a rate measured with a TGC of 16.8 kilohertz per centimeter squared. And if you take into account the sensitivity of the chamber, which is a bit technical, but you can think of it as the probability of a photon to interact in the chamber and being detected, then we can expect a real photon flux of 7.7 times 10 to the 6 centimeters squared per second. And this is in very good agreement within GIF++ simulations. And if you scale up these numbers measured with the TGC for the sensitivity of the Micromegas chambers, we have estimated an effective rate of 37.6 kilohertz per centimeter squared. So we actually demonstrated that at GIF++, it's possible to bring chambers to radiation fluxes that are up to a factor 2.5 higher than what is expected during the high Lumi operation stage of Atlas, which is roughly 15 kilohertz per centimeter squared. So here you see a typical result of our testing. We expose the chamber at different radiation fields, meaning that we filter the source with different filter values. And we monitor and register the current at the amplification step. You see that a filter clearly has an impact of what is going on at the avalanche stage. And you see that on the right, sometimes it happens that we have some severe spiking problem overimposed to the current baseline. And as was said before, it's not a secret that this project suffered during 2018 of severe HV instability problems. Here is an example of what we found during the first months of 2019. This is an example for an LM1 chamber. You see that indeed there is the baseline following the attenuation factor, but it can be completely masked by spiking problems and streaming of currents inside the chamber. So this spiked a lot of investigation on the problem because these were the largest area Micromegas resistive chambers ever built. And the very first strong sign of indication of what was going on came from an SM1 type chamber that was left spiking at GIF++ for about 2 months. Then it was brought back to Frascati and reopened. And we found on the PCB, readout PCV, very strong sign of deterioration due to spikes. And they were all collected very close to the HV distribution line. So this spiked the intuition that the spiking problem and HV instability was related to the resistance of resistive strips. And indeed, we found that if we go very close to the border of PCB, you have the yellow histogram on the left part of the slide, which is the resistance that you measure very close to the border of the PCB. And you see that this resistance can go very low and actually below 1 mega ohm, which is a bit too low from what from our requirements, a bit too far from our requirements. And then we performed some correlation plots of what was going on HV-wise related to the resistance of the PCB. And you see on the right that the sectors that could not actually reach the working point, that for us is 570 volt, were actually the detectors with the lowest resistance measured during the electrical tests. So this was the smoking gun of the problem. So we decided to apply, since the first months of 2019, a new technique that is called passivation. Basically consists in insulating the borders of the PCB, of the readout PCB, and be sure that the minimal resistance seen everywhere in the detector is above 0.8 mega ohm. And this technique had a very impressive effects on the chambers. It is an example of an SM2 sector before passivation. On the left, you see that the current was completely masked by spiking and streaming problems. On the right, you have the same sector irradiated after the passivation technique that was completely recovered. So very recently, I could compute some statistics on the effect of passivation. This is done with all chambers that have been integrated on Muon wheel side A. You have all four kind of chambers, so SM1, SM2, LM1, and LM2. And you have the percentage of good sectors passivated, the blue one, against non-passivated, which is the orange one. And you can see that after the passivation, we reached about 95% of good sectors for production chambers. We are also investigating the possibility of the chambers. Our baseline gas mixture is argon CO2 93.7, but we could use argon CO2 8020 or argon CO2 isobutane with a 2% enriched volume of isobutane. And on the left, you see some results from GIF++ irradiation. You see that changing the gas has the effect of changing the voltage range and the current range, operational range of the chamber. And you see the lines, the colored lines that are actually exponential fit to data performed up to the working point minus 20 volt and then extrapolated to higher voltages. And you see that we have an effect of saturation of the current with respect to the predicted current value by the fit. And this is known as a voltage drop, and it is a known effect for resistive MPGD. So the effect of having isobutane is quite dramatic. Here is an example from a spiking sector. When you change the HV value and you don't expose the chamber to radiation, you see that this sector actually starts spiking quite a lot. But when you flush it with the 2% isobutane enriched mixture, the current is completely flat. And this is a known effect of isobutane acting as a quencher within the chamber. So it's very, very promising. And again, this is true also when the chamber is exposed to radiation. If you look at the right part of the plot, you see that you see the monitored current for about 20 hours when the chamber was exposed to a very high rate of about 27 kilohertz per centimeter squared, and the voltage was the working point minus 20 volt. You see that blue and green distributions, which are actually argon CO2 based gas mixtures, have a very long tail of high currents value, which are actually D spikes. And if you use the isobutane enriched mixture, then the current stays stable for about 20 hours with no recorded spikes at all. So again, isobutane seems to be a very good candidate for improving the HV stability of the chambers, even though it's not chosen yet as the baseline. And we should perhaps add that isobutane kills the spikes, but sometimes if you increase too much the voltage, then you have a single catastrophic spikes that is so high that it actually permanently damages the readout panel. So there are pros and cons in using isobutane. So this brings me to my conclusions. The Micromegas chambers integration proceeded smoothly during 2019 and the beginning of 2020. The HV and the spikes issue that we experienced are considerably reduced now thanks to the passivation technique. And the isobutane enriched gas mixtures are a good candidate for the Atlas Muon wheel for further spikes mitigation. And at present, as you can see in the image below, Muon wheel side A is close to full integration. So thank you.
Thank you very much. Questions? So maybe I would ask, of course, probably the GIF++ facility is the only facility where you can actually position your such a big detector. But aren't you worried a bit that in Atlas there will be also different kinds of radiations, and what will be the effect?
Yes, I know in Saclay they have done some tests with neutrons. But yes, it's true that for irradiation testing at CERN, the only facility is GIF++. But it's true that the particle spectrum in ATLAS will be different. So we will see signals from neutrons, from MIPS, from muons, from pions. So we can expect some differences there.
Also, the material that you have used for this extra passivation that was so much helping you, is it proved that it is radiation hard?
Well, we use araldite that is guaranteed to be radiation hard,
okay.
And it was used also for MDTs. So yes.
Okay, perfect. Any other questions? If not, thank you very much again, and we will go to others. New Small V talk. We will hear about the commissioning of the detector with electronics at CERN. So please, Theodoras. Yes, we can see the slide.
Hello, can you hear me now?
Yeah, we can hear you now.
Right.
Yeah, now it is full screen. Thanks.
Hi, I'm Theo. I'm going to talk to you about the integration and commissioning of Atlas new small wheel Micromegas detectors with electronics at CERN. This is the outline of my talk. I'm not going to go through the motivation. It was covered by Dimitris. I'm going to dive into the new small wheel project, the Micromegas for the new small wheel. And I'm going to focus on the Micromegas integration and the workflow we have established. And I'm going to flash some pictures of the integration with STGC and the integration on the wheel. And I'm going to conclude with the status and the planning of our activities. So, as it was mentioned from both speakers, this is the new small wheel project. It consists of 2 wheels that are 10 meters long in diameter. It is an enormous project which has over 2 million channels. Each wheel has 16 sectors, and each sector has 16 detector planes in 2 multi-layers. The impressive thing is that in all this enormous structure, we need to know the precision of each detector with the position of each detector with a precision of better than 30 microns. Again, this slide was covered. I'm just going to show that we have here, there is a picture of 2 adjacent sectors, so 1 large and 1 small. And the reason we have two designs is for obvious reasons of coverage. Each sector comprises of 4 modules and 2 different types, so type 1 and type 2. And each module is a quadruplet, which means that it has 4 detection layers. As Micromegas integration, we define the assembly of 4 modules, 2 type 1 and 2 type 2, with a support structure in the middle that we call the spacer frame, the installation of the services and the front-end electronics, their testing of all the components and the full functionality of the Micromegas sector finally, and then the documentation and its sign-off. The integration takes place in this facility you can see here. That is a large hall that is fully equipped and clean, and we can work with ease there. And here is a sketch of the workflow we have established to organize these activities. I'm going to go into detail right after, just to say that first we receive the detectors and we perform the first tests and the first preparatory stages. And at the same time, we prepare the spacer frames, the support structures. And when these two components are ready, we mechanically integrate them, we install the services, and afterwards, the detector goes for the installation and connectorization of the electronics, the cosmic test, and then the final check, the storage, and the transport to the facility where the new small wheel is currently located. Going into more detail, the reception of the detectors is done in close to the entrance of the building. And then when we receive them, the first thing to do is to flush them with the nominal gas, argon CO2, and do the first leak test. Later on, we perform the high voltage, we ramp up the modules to high voltage and do the first mapping. And some of the detectors go to GIF++, as Lorenzo has explained just before. When this step is passed, then the detectors move to the alignment room, where the alignment team is installing the little bases for where the alignment fibers, the fibers for the alignment system of the final sector will be installed. At the same time, we prepare the spacer frame, and this is a quite lengthy preparation stage where we have to install the gas distribution system that is housed there. We also need to install 272 cables that allow the front-end boards to communicate with themselves. And also we install these precision pins that will define the position of the modules on the spacer frame. So as I mentioned, when these two stages are passed, we move on to the mechanical integration. Of course, there is a preparatory phase before the actual integration, where we have to install some cooling pipes, some grounding strips, standoffs, screws here and there to be able to do the mechanical integration smoothly. And finally, we move on to the actual integration, where we lay on a flat table one type 1 and one type 2 module. We interconnect them with the gas and cooling pipes. We install the services in this little cooling pipe region, this gap here, and afterwards we install the spacer frame carefully, and we repeat the process for the two modules at the top of the spacer frame. You can see here, for example, how cramped the services are inside this cooling channel. And here on the bottom, you can see the final product at the end of this stage. Afterwards, we finalize the installation of the services with some cables at the outer planes, namely some cables that would simply not fit inside the spacer frame, the fibers of the alignment system, and the temperature sensors. This concludes the mechanical integration. Now, the new small wheel, as I mentioned before, has over 2 million channels that are read by the front-end analog cards, which are called the MMFE8. Each MMFE8 has two satellite cards, which are called the L1DDC and ADDC. And all these boards are housed on the Micromega sector itself, and they are powered by low voltage distribution boards that are also housed on the Micromega sector. In total, we need to install and test 176 cards per sector. So the main player of the data acquisition system of the Micromegas is the VMM chip, which is housed on the MMFE8. Each MMFE8 has 8 VMM chips, and the VMM transmits the data both through the trigger path and the readout path through the ADDC and L1DDC cards respectively. Prior to the installation of the electronics, again, some preparatory work needs to be done. So we need to install cooling pads for better thermal contact of the cards to the cooling channel. We need to install the connectors to the strips, which are a very delicate process. And also we need to test the pre-installed services on the spacer frame and on the cooling channels. So the work is organized in a way that we have set up 3 stations that we can do the work in a sliding mode, so we can work at 3 sectors at the same time in different stages. So in rotation station 3, in rotation station 2, and the cosmic ray stand is where the final tests are done. This is the sense of the work. So in rotation stations 3, we install the front-end boards, and you can see at the bottom how cramped the cards are. The services, the abandon of services does not make it easier. So once the cards are installed in rotation station 3, the sector is moved to the rotation station 2, where a full readout system has been installed, and the first configuration of the cards takes place, and also the alignment of the strips of the MMFE8s to the strips of the detector is done with the help of these custom-made boards, where each LED corresponds to one channel. You can see here on the left side the situation of a misaligned MMFE8 that has been recovered with the help of this board with with the help of this board. Although this is one step, it's a very long process. And when this is done, the sector is moved to the cosmic ray stand, where we do an internal pulsar run to identify the dead channels and to validate the readout path. And afterwards, we do baseline and noise measurements for the VMM chips. Final step of the electronics testing is the validation of the trigger path, where the objective is the confirmation of the electrical and optical connectivity of each channel. All the VMM channels are pulsed sequentially, and we receive the data. So normally we should have a uniform picture here, one color, where each channel should respond one-to-one to the trigger. But the fact that we don't means that we have some channels that are dead and possibly some noisy channels. The final step of the validation of the sector is the cosmic ray test. Of course, the trigger comes from scintillators, which have a full coverage along the precision coordinate and partial coverage along the phi coordinate. And we validate the Micromegas detector and the electronics with this procedure. So the first step is to the finalization of the high voltage setting. So we ramp up the Micromegas sector for the last time. And here you have an example of the final mapping that was done in one of the in 4 layers of one of the sectors, A16, where 95% of the high voltage sections are in the nominal high voltage. At the same time, once this is done, then we perform the cosmic test, and we check obviously for the efficiency of the detector. And you can see the efficiency of one of the layers that we have of A08, where it's practically almost 100%. And this is the time to check for the first time the characteristics and the detector parameters like charge, cluster size, and efficiency. You can see here the turn-on curve of all this one full layer of all the Micromegas sectors that we have tested versus the high voltage, and also the cluster size at the same measurements. So when this stage is passed, then it's time for the final inspection, where we test the alignment corridors, the envelope, that we respect the envelopes that were imposed by the technical coordination, and the labeling and parenting of all the components of the detector. And finally, we produce a document that this is the certificate that will follow the detector for the rest of its life. Then we temporarily store the detector, the Micromega sector, until it can be moved to the new small wheel facility. Here you can see some pictures, and here the storage, how the storage is of the sectors, and to be integrated with the STGC. This is the workflow, and finally on the wheel. So coming to my conclusions. So what is the status? As you've seen, sectors 12 and 14 are installed and commissioned. And in terms of Micromegas integration, we have mechanically integrated 12 out of the 16 sectors. And in addition, we have signed off, meaning that they are ready to be integrated with STGC, 6 small sectors, and 2 will follow in the next with a rolling 2-week scheme. So the new small wheel A is previewed to be ready by spring 2021. And what about the new small C? As during the situation that we are facing, there is not going to be a winter shutdown at the end of 2021. And the baseline that we are working on is that it should be ready by October 2021. So is this feasible? I would say yes, for the time being, with a current rate of 1 Micromega sector, signing off 1 Micromega sector every 2 weeks, we are on good track. And here I would like to close with this graph that shows that CERN has given high priority to the new small wheel. And we were one of the first activities to start during the lockdown. And you can see here how our personnel in the integration facility has ramped up over the months of the lockdown. It's a challenging project in challenging times. Thank you.
Thank you very much. Questions, please? Yeah. Maybe I would have a question. You mentioned that you have the readout electronics, of course, in the active volume of the detector, or not in the active one, but in the Atlas. So have this electronic been tested for the irradiation harness?
Yes, yes, of course, of course.
And what are the expected fluencies in the position of this readout electronics, especially for the high luminosity LHC?
Oh, wow. Yes. Apart from the 15 kilohertz per centimeter squared, I don't have any other number.
Oh, okay, okay. Yeah, because I would expect that the total fluence at the position of this readout electronics will not be negligible, definitely. So
No,
probably
definitely
test
not.
it. Yeah.
Yes.
Okay. Okay. Also, I would like to ask you, what is actually the timing of the readout time of the detector? Because this detector will be definitely the part of the hardware trigger for the run 3 and 4, I would expect.
Right. So for phase 1, we expect a rate of 100 kilohertz, and the latency is of the order of 2.5 microseconds. And for phase 2, the level 0 is 1 megahertz expected with a maximum latency of 10 microseconds. But its subsystem is designed to handle dual level hardware trigger. So for level 0, it's going to be of the order 4 megahertz, and for level 1, it's going to be of the order of 600 to 800 kilohertz with a latency of 35 microseconds.
Okay. Okay. Thank you. Thank you very much. So we will go to the last presentation of this part of the session. It will be Shara, and we will hear about the simulation and reconstruction software for new small wheel.
So can you see the slides?
Yes, yes.
Okay. So hello, everyone. I'm Hara. I'm a PhD student at the National Technical University of Athens. And the topic of my talk is on the Atlas New Small Wheel Simulation and Reconstruction software. And I will also show some of the detector performance studies. So the outline of my talk, after a short introduction, the new small wheel upgrade, I will give the overview of the common software used for the simulation of the Atlas detector, and I will go through the details on the new small wheel detector description. Then I will move to the status of the digitalization and reconstruction, and I will show some results we have from simulation on the trigger. I will also report some of the results from the performance studies with Cosmix we are about to use for tuning and validation of the software, and I will end up with a summary. So the LHC upgrade aims to increase its potential discovery by the gradual increase on its instantaneous luminosity. And for this reason, also the experiments required to follow an upgrade plan. So one of the major Atlas upgrades is the new small wheel, which is about to replace the innermost forward region of the muon spectrometer. And the task that has to accomplish is to reject the high rate background on the forward region we are facing with the current small wheel. So as it is shown on the distribution here, the end cap region is dominated by high level of triggers, which is in the end suppressed as it does not match to actual tracks that are reconstructed offline. The new small wheel will be occupied by the two gaseous detector technologies, the resistive strip Micromegas and the small strip cap chambers, following the existing small wheel orientation, meaning that each wheel will have 16 sectors, 8 small and 8 large. Each sector consists of 8 layers of Micromegas being mounted between 4 layers of STGCs on each side, forming altogether a sector. Both of the detectors have been chosen and promise to provide both tracking and trigger information. So now just a few words on how these detectors are working. Once a particle traverses the system, ionizes the gas, and the free electrons ejecting along the track drift in the electric field. Once they approach the region where the electric field increases, they gain sufficient energy to further ionize the gas in an avalanche process. And the motion of the charges in the gas induces signals on the readout electrodes. And for the two technologies, we have different readout elements, with Micromegas having layers of strips, while STGC has 3 different such layers consisting of pads, wires, and strips. So page 4, it is vital for all the studies to have in place a robust system to simulate the experiment conditions and get Monte Carlo samples for real data comparisons. So the first step of the simulation is to generate all the desired particles and simulate the physics processes in the sense of the interaction of particles with the detector materials using XEAN4 and having, of course, a well-defined geometry description in place. After this step, all the information collected is about the type of the particle, its energy deposit, and its position and direction in the different geometry volumes. By using this output, we can translate the detector's electronic response into electronic signal based on Monte Carlo or other techniques and end up with reconstructing the tracks. So here about the detector description, one of the most crucial constituents of the simulation is to well define our geometry. For the new small wheel, we have collected all the useful parameters from the design files in the what so-called parameter books, and these are translated into XML format, which can be easily read out and stored in an Oracle database. We use external tools to produce displays, and some of those are presented in the pictures on the rightmost side, where you can see the 2 scenarios we have accommodated for the Atlas detector. So given that the Atlas upgrades are staged into 2 steps, depending on the construction status of the wheels, we will be ready to run our software, the coming run period, either with one new small wheel at the one side or the 2 new small wheels at both sides. The most important aspect in the geometry is the need of the detailed description of the readout geometry, which is the area where the interactions happen. It is the base and directly affects the digitization that does a consequence reconstruction. So due to the different technologies and the different design followed for each of the chambers, even of those of the same technology, makes the implementation quite challenging. And I show here an example of a Micromegas layer, which has its strips tilted by a small angle with respect to the other layers. So willing to fill the area with as many strips as possible, in principle, at the corners, we will have some strips that will be shorter in length, which means that they are not connected directly to the front-end boards. And instead, we route them, and this results to regions of reduced acceptance that we need to take into account. So except of those special characteristics, we have also to consider the special conditions in the cover that can cause all the possible geometry imperfections and that are measured by the alignment system. So the new small wheel alignment system is a complex optical system which attaches the new small wheel to the existing alignment system and establishes a grid for the new small wheel to this coordinate system. So special tools are mounted on the sectors, and through measurements that will be performed online by the alignment software, we will have in hand all the useful parameters to determine the realistic detector conditions. These parameters are referring to translations and rotations with respect to the nominal positions, or even though to deformation or expansion states. All this information is about to be stored online in a database to which our common software will have access to. And here on the picture, I show an exaggerated example of all these deformations caused on STGC wedge. So in addition, we have another set of parameters which accounts all the permanent deformations, and we can translate them into detailed models, and we can also introduce them in the software. So having everything in place, the goal is to produce amps with realistic conditions to allow the performance studies. After running the simulation, the information we get is very limited, so the translation into the actual measured well-known quantities is required. We use results from analytical simulation or test beams, and we parameterize. By sampling from these distributions, we are able to model the detector. So the energy deposits in the sensitive gas volume is used to simulate the ionization along the particle tracks, and the drift of electrons is calculated taking into account the drift velocity, the transverse and longitudinal diffusion, and Lorentz angle using parameterization of simulation results. And the gas gain is modeled according to the Polya distribution, and given the charge and the time, we can also simulate the front-end electronics and introduce thresholds, dead times, and similar. So the last step is to collect results from cosmic data and tune the parameters to match the real data. About the track reconstruction, we have in place all the different methods adapted from the test beam analysis. So for the small angles in the Micromegas case, or for the full angle range for SCGCs, we use the charge centroid method. For inclined tracks in Micromegas, the charge centroid method is not able to provide the precise heat position reconstruction with the required resolution. So we have as an alternative the micro-TPC method, where the drift time and the drift velocity enables to assign to each strip a track point. Then we reconstruct the track by combining the neighboring track points of the layer, and finally, the best position measurement corresponds to the track fit at the center of the gas cap. So in addition, we have the cluster time projector method, which is also in place and is a combination of the other two techniques, where we build the centroid in both position and in time. So now the time for some results on the trigger. So the key to suppress the fake triggers is by finding the coincidences between the big wheel and the inner station detectors. So the plot on the left side shows the muons transfer momentum using a trigger for muons of 20 GeV. And looking on the distributions taken by the coincidences between the big wheel and the new small wheel, we see an effective reduction of all the fake candidates below the threshold compared to the random 2 configuration. So on the right side, we see in blue the distribution of trigger muons, which we expect to get in run 3 after passing the various rejections we estimate from a different subsystem. And we see that this results to a perfect matching with the offline reconstructed muons, which are shown in red. So now the time has come for the real detector results. So before placing everything on the wheels, we have the detectors under testing with cosmic muons. Here I show the setup of a Micromegas double wedge on the cosmic standard share. We have placed scintillators on the top side of the chambers to trigger the muons. And we have several plots that validate that the system works within the specifications. So as a reference here, I show the cluster charts as function of the angle for different Micromegas layers and different electronics configuration. And as expected, the charge is increased for large angles. And of course, we can take the efficiency plots that prove at the nominal voltage point, the working point, the detector performance is very good. So for the STGCs, we have similar studies at the construction sites. The chambers are placed horizontally between two layers of scintillators to trigger the muons. And some of the results we get are about the charge and the expected number of strips in a cluster, and of course the efficiency plots. So all of these results will be collected and are about to be used as input to comparisons with the simulation. So coming to the summary, the common software with a new small wheel in place is advancing well. We have in place the nominal geometry for both scenarios, and we are able to produce samples, test the detector behavior, and debug. We are on the way to insert all the geometry corrections to reflect all the possible realistic conditions. All the clusterization algorithms are already in place and under testing. And finally, we have also developed calibration tools, which are ready to use the configuration of the cosmic test results. So that was everything from my side. Thanks a lot for your attention.
Thank you very much for a very nice presentation. Questions? I see Rustem. Please.
Yeah, hi, sorry. I should probably know answer to this, but when you show the triggers, I think on page 12, the distribution, there's a small asymmetry between eta and phi side. And I was wondering if you maybe recall what causes this difference?
What? Which one? Sorry.
On the right side, it seemed to be on a positive eta, there are slightly more fake triggers compared to the negative eta side.
Here?
Yes, here, and also I guess the integral of the yellow.
Okay, well, I don't have an answer right now for this.
Okay. Any other question? Maybe I would ask, are these Jean-4 simulations implemented in Athena already? Is it a part of the global Atlas simulation framework?
Yes, we use Jean-4 libraries.
Okay, and other question, how you are implementing the, let's say, electrostatic field or the field inside of the chambers? Is it like produced by Jant, or you are using some other software to simulate the shape of the field?
We use results from other simulation frameworks as ANSYS.
Mm-hmm.
And we parameterize these results and give them as input there.
Okay. And what is actually the spatial resolution or the space resolution of your detector, of the new small field in general? And is there a difference between Micromegas and TGCs?
So the resolution for Micromegas is expected to be below 100 microns. And for the STGCs is about 1 millirad.
Okay. Are there any other questions? Okay. If not, thank you very much again. This was the last talk of the first part of the session. So thanks a lot to all the speakers. Very nice presentations. And now we will have like 5 minutes coffee break. And we will start. So let's meet here at 10:05 a.m. of Prague time, and then we will continue with the jet reconstructions and other similar talks. So thank you very much again. Of course, in the during the break, coffee break, you can try to check your screen sharing. Okay, does somebody want to try to share?
Yes, I can try.
Okay, please.
Okay, let me see. Can you see them?
You can try full screen.
Yep. Let me see. Full screen. You know how I do that?
The green button works.
This.
The normal Mac full screen button.
Like this?
Yes.
Yep. Nice.
Thanks.
Sure, thanks. Should I just keep them up, or do you want to try some more?
Yeah, you can stop sharing. Maybe somebody else will try also.
Right, I would use this opportunity.
Mm-hmm.
Does this work?
Yes. Mm-hmm, perfect.
All right, okay. Thank you.
Thanks.
Hi, I may also want to try share my screen.
Sure.
Can you see the slide?
Yeah, we can try full screen.
Okay. Do you see full
Perfect.
screen? Okay,
Yes.
thank you.
Thanks. Okay, we have already 10:05, so I think that we can start. I will be the chair of this, also of the second part of the session, and we will start with Eva, the jet reconstruction and calibration in Atlas.
Yes, thank you very much. Let me just start by reminding everyone why it is we think jets are an interesting final state. To look at it because it's useful as probes of QCD at both soft and hard energy scales, but also jets are produced in various interesting final states. So for example, in Higgs decays and decays of new heavy particles in standard model extensions. However, jets are also an abundant final state in uninteresting processes, which means that they come with huge backgrounds and lots of pileup. And that means that detailed calibrations are both important and quite challenging. So in Atlas, we're able to reconstruct and identify most standard model particles using the different layers of subdetectors, and the calorimeters provide the principal signal for jet measurements. However, the inner detector can add precision PT and direction information on the charged particles, which help with vertex reconstruction, pileup mitigation, and also refinement of the jet reconstructions, as we will see in this talk. The workhorse of the Atlas jet reconstruction is the anti-KT algorithm, which is free of divergencies coming from soft and collinear splittings, which means we can use it to make theoretical predictions to compare with our data. And we use this algorithm with mainly two different radius parameters. So smaller jets, we call the ones with a radius parameter of 0.4, and those contain most of the radiation from quark and gluon jets and are sort of our generic most common jet definition. We also use R equal to 1.0, called large R jets, which can capture the hadronic decay of heavy boosted objects such as WCs and TOPs. It also matters which inputs we feed to these jet algorithms, since we cannot just give the full calorimeter readout. We use mainly two input definitions. One is called topoclusters, which are just clusters of topologically connected calorimeter cells with the signal above some threshold. The other is called particle flow or P-flow objects, which combine tracks and topoclusters. And there are many benefits to combining tracks and calorimeter clusters, since the trackers have better resolution for low PT particles and better angular resolution, can also trace individual particles to either the hard scatter interaction or to pileup. Whereas the calorimeters have better resolutions for high PT particles and can also capture neutral particles. So combining this information improves both the energy and angular resolution and also reduces pileup contributions in our jets. And this energy resolution improvement can be seen on the plot on the right, where, just as a side note, the green band here is called EM plus jets, since topo clusters can be weighted according to two weighting schemes. So EM means just that they're weighted by the electromagnetic calorimeter calibration, but we also use something called local cell weighting, which accounts for the different response to hadronic interactions of the calorimeters. And this is mostly used for large radius jets. But after the reconstruction, we also need to calibrate the jets in order to correct for various different detector effects, such as, for example, energy deposited in passive areas of the detector, or pileup, or it could be showers that extend beyond the calorimeters or beyond the jet cones. The calibrations are derived for several different jet definitions. I will focus mostly here on smaller jets, which are reconstructed from either P-flow or EM topo clusters, or larger jets reconstructed from LCW topo clusters. The calibration is then carried out in several steps in order to correct for all the effects mentioned above. These differ slightly for the two jet definitions, but the principles are the same, and I'm going to sketch them here, trying to highlight with a little label on top which applies to small r and which applies to large r, or both cases. So starting with the pileup mitigation for small r jets, this is done in two steps. The first is based on the area of the jet, which is a measure of how susceptible the jet is to pileup. And the second step is based on the number of primary vertices and the average mu, which can measure the in and out of time pileup. And as you can see from the two plots on the bottom, with these two corrections applied, there is next to no pileup dependency remaining across the detector. Here, that's the red line that has the pileup dependency for the two in and out of time pileup. For large R jets, the pileup mitigation is done slightly different. We use a class of techniques called grooming that reduce not only pileup, but any soft and wide angle emissions. And this improves the PT and mass resolution, but also make the measurement of substructure variables better, which is important for tagging and identifying the origin of the large R jets. So detailed calibrations in Atlas are provided for the grooming technique called trimming, trim jets, which goes so that we reconstruct a large radius jet and then recluster it into subjets with a radius parameter of 0.2, so smaller subjets, and then remove all of the subjets with a PT less than 5% of the original jet PT. So in this case, there are three energetic subcomponents remaining in the end, so could be, for example, a top candidate. Then there is done a Monte Carlo-based calibration of the jet energy scale, the rapidity, and the mass in case of large R jets. And this is because the detector response differs across the detector, especially where there are boundaries between different calorimeter technologies and granularities, as you can see in the plot on this slide of the jet energy response for small R jets. And this calibration is done by matching reconstructed jets to truth jets in Monte Carlo, and then deriving these corrections as function of both the energy and rapidity of the jet. Another Monte Carlo-based calibration is only applied to small R jets. That's the global sequential calibration, which is aimed to adjust for both the non-compensation, flavor dependence, and punch through, which was mentioned in the list of detector effects that we're trying to correct for. This calibration is done in 5 or 6 steps that all use observables that are related to these to these detector effects, such as the energy deposited in the calorimeters, or the track information in the jets, or the activity in the muon chambers. Finally, we do an in situ calibration, which is the last step of the data of the calibration, and it is data driven. And the intention is to correct for any potential differences between the data and the Monte Carlo. So for the jet energy scale, we use 3 different methods that all rely on the jet we want to calibrate recoiling against some well-calibrated reference object in the event. So for example, that could be a forward jet recoiling against a central jet to get the relative jet response across the detector, across different rapidities. We call it the eta intercalibration. We can use jets recoiling against a gamma or a Z boson, since those are usually better measured. Or to calibrate large PT jets, we can use an energetic jet recoiling against a system of multiple low PT jets to constrain the jet response at high PT. In every case, we define the response as the Gaussian mean in a bin of PT or eta of the jet PT over the reference object PT. And then we measure this in data and in Monte Carlo to provide a correction factor. Now, the different in situ methods have to be combined somehow. So first we apply the eta intercalibration before anything else is done. Then the Z jet and gamma jet balance are derived and applied to calibrate the low PT jets up to about 1 TV. And then with low PT jets calibrated, we can derive the multi-jet balance to constrain up to about 2 TV. And these this gives us 4 sets of measurements across as function of PT, jet PT. And these are combined in order to give a smooth and continuous calibration curve across the full range. And all the uncertainties from the individual measurements are propagated to this final calibration curve. Similarly, we calibrate the jet mass scale for large R jets, where we use 2 different methods. One is called forward folding, that uses semi-leptonic TT bar events with a hadronically decaying W or top. We then fit the mass peaks to get the mass scale and resolution, which has very small uncertainties. But we can then use the R-track method, which takes the tracker information as a proxy to independent measures of the mass scale and extend the calibration both in the lower and higher PT range. And this is done in 2 separate mass bins, as you can see in the plots here, one using mostly top decays and the other one Ws. Finally, we also need to calibrate the jet energy resolution. Here, as an example, I show how it's done for small R jets. And this is important in order to both, of course, measure jets precisely for searches and standard model measurements, but also to get a good measure of the missing ET in the events. The resolution is important. And it's defined as the width of the response distribution rather than the mean, which is the energy scale. And this energy resolution can be parameterized with 3 independent terms, 1 noise term and 1 stochastic term and 1 constant term. The noise term is then measured individually or independently with a method called random cones in minimum bias data. And then the other terms can be measured by fitting the jet energy resolution from dijet events while holding the noise term fixed that has already been determined. And that brings me to my summary, which is that jets are interesting, abundant, and challenging signatures at the LHC. From small R jets, we've seen that there is lots to gain by combining tracking information with the calorimeter signals. And this is going to be especially important in the high pileup era that we're now entering. In large R jets, I've shown The calibrations are entering or have entered the precision domain for both the jet energy scale and the jet mass scale. Thank you very much.
Thank you very much. Very nice presentation. Please, questions. I am, of course, not an expert to this field, but you mentioned a lot of, it is very, very complex process and procedure. And you mentioned that you basically use all the detector components of the Atlas experiment. So
yeah, more or less, yeah.
Yeah, you even mentioned the muon chambers or
yeah.
the muons. So actually, of course, the natural question is, how are you preparing for the high luminosity era? And you certainly are doing the extensive studies of this. What will be the effect?
What will be
the effect actually of the higher pileup and also the upgrade of Atlas individual detectors?
Well, for the calorimeter, there are some upgrades plans that's going to improve much on the triggering on large radius jets or like triggering on heavy boosted objects. This GFX module, but in general, this adding the tracking information for the jet reconstructions for both small and eventually larger jets is going to have a big improvement on the resolution in the high pileup era, where it'll be much better, give much better pileup mitigation.
Okay, so you think that for example, now going up to pileup of 200 or something like this will be completely covered by, for example, the increase of the channels in the tracker, which will be like 10 times compared with inner detector, the current inner detector. So it will be even better in the future.
Oh, I'm not sure if the resolution is going to be exactly as good or better at a pileup of 200, but there are definitely a lot of improvements to be gained in resolutions from these measures that we have now taken.
Yeah. Okay, but what about run free, when you will have higher pileup than now, very probably, but still the same inner detector? So it will be more problematic conditions probably.
Yeah, but I don't think. Well, you're right. At the trigger level, we're not going to have any big improvement at the run 3. But the resolution of the offline calibration is going to improve with this using P-flow or these other reconstruction methods that combine tracking and calorimeter signals.
Okay. Yeah, it makes sense. Thank you very much again. Are there any other questions? If not, thanks again, and we will go to the second presentation. Carlo?
Yes. Let me share. You should be able to see it.
Yeah, you can go to full screen maybe. But it's good enough, so yeah, now it is perfect. Thanks.
Okay, great. So I will give you a brief overview of the flavor tagging in Atlas, and also a few insight into the tracking within jets. So I will first start with a very quick introduction about what flavor tagging is, and why tracking is so important for flavor tagging performances. Then I will go a little bit in details on these aspects, starting from tracking, of course, and then I will move fully on flavor tagging, discussing also the algorithm that we do have. So flavor tagging is basically a tool that allows us to identify the flavor of the pattern that originated a jet. In this way, you will be able to identify light jets, B jets, or C jets, and so on. And to do so, you are actually exploiting the property of a heavy flavored hadrons, which basically means a long lifetime, which brings to a displaced vertex, but also large impact parameters, as well as possible semi-leptonic decays that you may have, for instance, for the hadrons. And you can well imagine that within Atlas, there are a lot of analysis that having the final states B or C hadrons. So this tool is quite important for this analysis. But tracking actually is a pivotal point in flavor tagging. This is because tracks are basically the inputs to our flavor tagging algorithms. So precise measurement of track qualities, in particular impact parameters of tracks, but also secondary vertices or length of flights are extremely important so that you can actually have an efficient flavor tagging algorithm, which basically will provide you a single output discriminant that analysis can use for these studies. So talking about tracking, how it works is the following, basically. You first start with a cluster creation, starting from the raw measurement, and then you will start doing some computation, starting from an interactive track finding, then move into an actual pattern recognition, which is divided into different stages. The first loose track candidate search, followed then by a stringent selection, which is the ambiguity solver. However, you can see from the bottom right plot that this is quite a challenging task. You can see that the majority of tracks within a jet are actually very close to the jet axis. So the closer you go to the jet axis, the more particles you have. So that's quite a dense environment that you have, meaning highly collimated chat particles in a very small area. And this may lead to several problems that may affect tracking efficiency. In particular, charged particle separation and multiplicity are the key points here. If you have a dense environment, which it means that when crossing the detector, then you have the cluster deposition of energies, and these clusters are actually overlapping. So you have these so-called merge clusters, and identifying them is quite paramount for an efficient charged particle reconstruction. And you can see in the bottom, for instance, some plots that basically shows you that the efficiency decreases the closer you go to the jet axis, which is where the majority of tracks is. And this is due to this fact that you have too many tracks in very close to each other, which means merge clusters, and this leads to this drop of efficiency. Also, you can see from this other slide that the efficiency drops with PT, and this is due to the fact that tracks are more collimated. So again, the same concept applies here, merge clusters once again, but also with the production radius. In this case, there are two different effects actually. First thing is that the particles that are created after the first active layer creates a few clusters that you can use for reconstruction, but as well, you have a shorter flight length between particle creation and the detector itself, which means that particles are actually not well separated yet, which brings to, again, merge clusters. So the effect is basically the same. This is why you have this drop of efficiency at large radius. So you have tracks. At this point, basically, you have the inputs to flavor tagging. Flavor tagging is not one single algorithm. It is actually made of several different specialized algorithms. So you actually start with low-level algorithms, which are specialized in different things and use complementary or bit correlated information. So you do have algorithm, for instance, RNNIP and IPXD that takes tracks, look at the D0 and Z0 significances and their correlation as well. But you also have algorithm taking care of the secondary vertex reconstruction. This is SD1, but you also have algorithm like JetFitter that takes care of reconstructing the complete bihadron decay chain. These are low-level taggers. They produce their outputs, but the analysis will use one single output discriminant. So you have to put somehow these outputs together, and this is done using so-called high-level taggers. So historically, we had so-called MV2, which was a BDT-based algorithm. But then we have moved to deep learning. So you will now have a DL1 algorithm. And according to what lower level tagger information you're using, then you have different variations. So DL1 actually uses IPXD SV1 JetFitter. Then recently RNNIP, which is a recurrent neural network, was introduced. And using also this input, then you have the so-called DL1R. which is actually the recommended tagger right now in Atlas. And it brings some advantages together with it. And in particular, conversely to what MV2 actually does. I recall you, it's a BDT, so it produces only one single discriminating variables for analysis to use. The other one actually produces 3 different outputs. That's a neural network. And these 3 outputs correspond to the probability of a jet to be a light jet, a B jet, or C jet. And you have to put all of this together, and you do it with by defining a simple likelihood ratio, which is on the bottom. You put this probability together and introduce this so-called charm fraction, FC, which is basically a number. It's a free parameter that you can actually tune in order to have optimal trade-off between the rejection of charm and light jets. So if you want a different trade-off, then you simply change this number. That's quite easy. You don't have to retrain your algorithm. While MV2 is not so flexible. If you want a different rejection, then you need a different tuning, which is quite a long process. So extremely versatile. And also, if you want, for instance, charm tagging, then you have basically to do nothing. You simply define a new likelihood ratio. That's on the one on the bottom. In this case, you are actually introducing the B fraction instead of the charm fraction, and that's it. You have charm tagging at your disposal. You can use it in your analysis. That's quite easy. And here on slide 10, you can see a few performance plots. Basically, I'm comparing the old high-level taggers MV2 with the new taggers DL1 and DL1R. You can see that DL1R actually outperforms the other taggers. So you can see the light jet rejection and the C jet rejection on the top. And also we do provide scale factors, obviously, for analysis. And you can see that this is for DL1R. These are compatible with one for different working points on the left and for JetPT on the right. So that's extremely good. But what if you want to go higher in PT? Then at that point you have problems. High PT means boosted regimes as well. And in that case, you can see on the top right plot, this is the double subjet belabeling efficiency. So the ability of labeling both subjects in a large radius jet. Then you see that the red curve actually has a huge drop in efficiency. So at a certain point, you're not able anymore of tagging the subjet searches. And this is because conventional flavor tagging and jet reconstruction actually use a fixed radius approach, which is not appropriate in case you're going too high in PT. In order to recover from this inefficiency, then you have to introduce variables radius track jets. In that case, the radius of the cone is actually dependent on the PT of the jet, actually the inverse of it, to be honest. And by doing so, then on the top right plot, you can compare the red curve to the blue curve, and you can see that you're actually recovering quite a lot from this inefficiency that you have. So of course, you're still dropping in efficiency a little bit, but it is not as bad as it was before. And obviously, our flavor tagging algorithm have been optimized in order to use this variables radius structure, so they are available. Also, another thing that can be done is use flavor tagging for an X to be B tagger. For instance, an Higgs to be B tagger, which is what is shown actually on the bottom. These are some ROC curve and efficiency, multi-jet rejection actually versus the jet PT. And you can see that these are quite promising results and also quite recent. You can see that in the publication, which is 2020. So if people is interested, can follow this link and get all the information they need. A last thing before closing is something that has been developed during Run 2, which has not yet been used by any analysis, will be used in the future, and is DIPS. So DIPS is basically a low-level taggers. It's very similar to RNN-IP. RNN-IP, I recall you, is a recurrent neural network that requires a sorted track collection as input. But DIPS actually doesn't require any kind of sorting. So it uses the same inputs as RNN-IP, but it's more flexible, let's say, and it can be parallelized, not a sequential operation. And as you can see from the bottom and plots and from the right plot, then it actually outperforms RNNIP, even though the same inputs are used. In addition to that, actually, it is even more easier to train to validate. So this brings any much improvement also from this side at low-level taggers. So in conclusions, and I have shown you a very brief overview of flavor tagging, and hopefully I convinced you that tracking is an important piece of information for flavor tagging. And in particular, you can see that tracks has been quite a challenging task. Tracking is quite a challenging task within JETS, since you have a dense environment. And obviously, flavor tagging algorithm, which is a very complex set of different algorithms, makes use of tracks. So an efficient tracking brings also to an efficient flavor tagging. And flavor tagging algorithm can be used also for cham tagging, and this is already used in different analysis. So basically, this is the overview I gave you, and it's everything from my side.
Thank you very much. Are there questions? We heard very nice overview of different algorithms. You mentioned, of course, and you mentioned also in these conclusions that the tracking is absolutely critical for this. Of course, if I understood correctly, so you would basically need, from the hardware point of view, you would basically need to move to much higher granularities of the tracker, or be, of course, significantly closer to the vertex, or so it would definitely help. But of course, these changes are extremely expensive. So the other way how to progress is, of course, improving the algorithms. So are you preparing also already for the high Lumi era with this? You are certainly doing some simulations of what it will be.
Yes, there are studies underway, hyper up, but the development goes into this DIPS and also using deep learning for flavor tagging. So this is where we are actually going for the future.
So what is the what is your feeling about the, let's say, run 3 and especially then run 4 with high Lumi LHC? Will it be the problematic environment for you, or with the, for example, with the upgrade of the inner tracker, it should be okay or even better than now?
We have performed some tests. We are still work in progress, and honestly, from my side, I'd say that at least for run 3, we will have similar performance. Hopefully, we will try also to outperform what we had in run 2. So, yes.
Okay. Okay. So, and also you mentioned these boosted decision trees and neural networks. So is it like a common approach that now everything is moving to these, let's say, neural networks algorithms?
Yes, we are moving to deep learning, so neural networks. In the past, we had PDTs, but it is not as flexible as neural networks, as I mentioned before. So we are doing it, first of all, because we are outperforming our previous performance with BDTs, and also it proves more flexible. So that's a win-to-win situation.
Okay, thank you very much again. So we will move to other talk. It will be Lin, and we will hear about the boosted object identification in Atlas.
Okay, I'll share my slide.
Yes, it's coming. Yeah, please go to full screen if you can.
Yeah, sorry. Okay, can you see full screen?
Perfect. Yes.
Okay, thank you. Hi everyone. Today I'll talk about boosted object identification and their usage in search for new physics in Atlas. So first, top core W and Z boson can decay hadronically, so their decay product can deposit the energy on the detector. The angular separation can be approximated by 2m over pt. So as a plot shown on the lower side, if the decay product from the boosted W boson, it can be reconstructed as one larger jets. And the tagger using the jet substructure information are used to separate the synchronous jets from the QG jets, which is a background jet. And these taggers are calibrated with longitude data. So people working on the search for new physics can use the taggers. So next, I will briefly introduce the large jet reconstruction. There are different input types for the large jet reconstruction, like topo cluster, track halo cluster, and particle flow object, and also the unified flow object, which is the new definition. And the particle flow object is only used for the small object. Topo cluster is the cluster from the colorimeter cell signals with local hadronic cell weighting, which we use LC. And we usually use the R equal to 1.0 and apply the trimming to the jets. And you can see the advanced talk for more detail about training. So next is the track color cluster TCC jets. TCC object is the other combination of tracks and topo cluster with delta matching. You can see the schematic shown below. For example, the number one shows the one topo cluster match with one track, and the number two shows a cluster with no track matching. So tracking provide a better spatial resolution, so we can have better mass resolution in high PT range, and also the D2 resolution across full PD range. And I will introduce D2 later. So the last one is unified flow objects, and UFO. Oh, sorry. The UFO is the combination of PF4 and TCC. PF4 is the particle flow objects, and the plots show lower side are the W boson performance of W boson in LC topo and TCC P flow and UFO jets. And the purple dashed lines show the performance of the UFO jets, and you can see the PF4 has the best performance in the low PT range, which is shown on the left-hand side, and the high PT range, which is shown on the right-hand side. So yeah, the UFO has the best performance. So next, I will talk about jet substructure, and the feature inside a jet depending on the originating particles. And the most important one is the jet mass. And we use combined mass for the LC topo jets. And the combined mass is the combination of color mass and also the track assist mass. And track assist mass is derived from the mass of track mass. Yeah. And the other ones are just substructure moment, like unsubjectness and splitting scale and energy correlation function. And you can see the D2 is one of energy correlation function ratio. And the plots show below shows the data MC agreement, and you can see the mass distribution on the left-hand side, and the D2 in the middle, and the tau 32 on the right-hand side, and the matching is, looks good. So next I'll talk about boosted jet tagger. Oh, sorry. The first one is WZ taggers, and taggers are defined by the implicit cost on various substructure variables. For the LC topojets, we use 3 variables, the number of track and combined mass and D2. And we derive 50% and 80% efficiency for both W and Z taggers. And the plots on the upper plot shows the background rejection of the W taggers, and you can see the highest background rejection is around 1 TeV. For the TCC jets, we use 2 variables, mass and D2, and we derive a significant space efficiency for W and Z taggers. They are mainly used for the heavy diboson resonance search in the semi-electronic final states. And due to the low background in analysis, we enhance the signal efficiency. So the plots on the lower side shows the signal efficiency and the background rejection for the taggers, and you can see the background rejection is not high here. So next is top taggers. We use the deep neural network DNN algorithm, and 13 jet moments of LC topojets as the inputs, and we derive 2 types of top taggers, inclusive top and content top. The content tab includes most of decay products. The plots on the left-hand side shows the data and the MC agreement in the DNN score for the content top taggers. And on the right-hand side, the plot shows the background rejection of the inclusive tab and the content tab. You can see the content tab has better background rejection in low PD range. So next is calibration in data. We derive the scale factors for the calibration of tagger performance. And for the synchronal jets, we use the semi-electronic TT-PAR events. And if the delta are between the larger jet and the B tank jet is smaller than 1.0, and we use the jets for the calibration of top taggers. If it is larger than 1.0, we use the jet for the W taggers. And for background jets, we use 2 different samples, multi-jet event and the gamma plus jet event. And the gamma plus jet event is for the low PT range, and the multi-jet is for the high PT range. So for the synchronal scale factor, the data efficiency are derived from the simultaneous feed to the tank and the not tank leading jets for each PT bin. As you can see, the plots on the left-hand side shows the tank distribution in the combined mass, and in the middle, this is the not tank distribution. And you can see there's a much more TT signal in the tank distribution. And for the PT range, is up to 1 TeV for top tagger and 600 GeV for the W tagger. And you can see the plot on the right-hand side shows the signal efficiency and the scale factor for the content top tagger, and the scale factor is close to 1. And since there's a lack of statistics in high PT range, we use different MC sample to derive the uncertainty for up to 4 TeV for top taker and 2.5 TeV for W takers. So for background scale factor, the scale factor are derived as as a function of PT and log m over PT, and the data will be subtracted by other MC sample. And for the PT range, is up to 4 TeV for top taker and 2.5 EV for the W taker. And you can see the plots on the left-hand side shows the background rejection and the scale factor in multi-jet sample. And on the right-hand side is the results of gamma plus jets. Yeah. So next I will show an example for the application of top takers. And this is the analysis for searching for the TT resonance in 4 hadronic final states. And since we are searching the Z prime mass in the high mass range, the boost top will be produced and it can be reconstructed as larger jets. Here we use the DNN content top taker with 80% efficiency. So as the plots on the left-hand side shows, this is the upper limit of Z prime mass, and the black line shows the original method, which is use the likelihood ratio based on the tau 32, and the blue line shows the method with DNN top taker, and you can see the significant improvement from the DNN top taker. And the green line just show the results with 4 round 2 data, which is up to 4 TeV. And on the right hand side, I show the mass distribution of top resonance, and you can see there's no significant excess in the distribution. So the summary, and we have LC topo jets, TCC, and UFO with R equals to 1.0 for the identification of boosted objects. We currently have a WZ taker for LC topo and TCC jets, and the top taker for the LC topo jets, and these are calibrated and can be used for the physics analysis. And I also show an example for physics analysis, which is TT resonance, and yeah, it has very good results for using the DNN top takers. Okay, this is all my talk. Thank you.
Thank you very much. We have still time to quick question. Please. It was a very nice overview of the techniques used for the boosted objects. You also mentioned this Z prime to TT bar, so definitely something that will be probably heavily studied during the high luminosity era. So is there, like for the high lumi or for the run free, are you especially focused on the development of the different algorithms, especially these neural networks you mentioned again? Or is there also something from the hardware point of view that can help you with this, or something that you would like to wish the detector would be that can significantly help you with these boosted objects?
For the hardware side, I'm not sure, but we are trying to use the new jet definition for the, I think for round 2 from round 3. So yeah, it's already approved. We can have many improvement on these techniques. Yeah.
Also, the higher granularity of, for example, the new inner tracker that will be for high lume, do you think that it can help you, or the higher pileup will degrade this advantage?
For the high lume, I'm not sure. Yeah, but yeah, I can. Sorry, maybe I'm not sure for that. Yeah.
Yeah, I think the higher granularity of the tracker is probably going to be sufficient for us to retain our performance because it will help us to avoid the vertices merging and so on. But most of the time, what we're seeing with this new jet definition is we take the scale from the calorimeter, which will remain pretty similar in high PT for these boosted jets, and the angular resolution of the current tracker is already giving us about the best that we can have there. So I think it's more that the ITK and similar tracker upgrades will probably allow us to continue to have similar performance in a higher pileup environment.
Okay, that's nice. Yeah, thank you very much, and we will.
Hello?
Yeah, hello. We can hear you.
I cannot hear Yuri anymore.
Sorry, I was muted.
I think
sorry. we can. Sorry, we can hear you, of course, and you can try to go to full screen.
Okay.
And start. Yeah, sorry.
Let me check. It's working now.
Yeah, looks good. Looks good.
Okay, so I'm Arantxa Yanguren from IFIC at Valencia, and I'm going to talk on real-time alignment, calibration, and software quality assurance for the LACB experiment. So the outline of the talk is the following. So I will talk briefly about the LACB detector. I think this is the only talk on LACB in the session. So then I will talk to you about the trigger and how we perform real-time analysis and the importance of alignment and calibration. And then we'll give some prospects for the next run. So the LACB detector, I think you know, but in case of you are not very familiar, it is a single-arm forward spectrometer dedicated to the physics of beauty and charm hadrons, and this is why it has this shape. So it has different subsystems. You have a very good tracking system with a vertex detector, the bellow, and then the tracking stations, TTs, what it is called here, Ts. And then you have also a very good particle identification system, which consists of 2 rich detectors and calorimeters and muon chambers. So the LACB has very good performance. So the tracking resolution for low momentum tracks, it's about 0.5%. And also it has a very good efficiency for tracking and PID, which is larger than 95% in general. And to achieve this high performance, what it is very important, it is, of course, to have the detector properly aligned and calibrated. So let me explain briefly the trigger system at LACB for run 1 and run 2. So we have proton-proton collisions at 40 megahertz, as you know, and we had for run 1 and run 2 a hardware trigger, what we call L0, which use information from the calorimeters and muon system. This reduced the rate to 1 megahertz. And then the events are built and sent to about 27,000 CPU cores, where we perform 2 software trigger stages. The first level of the trigger, it is a fast tracking with inclusive selection. So that means high momentum tracks and displaced vertex and reduce the rate to 100 kilohertz. And then a second stage of the trigger, of the high level trigger, which is about 500 dedicated lines and reduce the rate to 12.5 kilohertz. So the important thing from run 1 to run 2, it is that during run 1, the alignment and calibration of the detector was performed offline, and it took several weeks after data taking. And for run 2, what we do, it is to add a buffer in the way that the alignment and calibration is performed in real time before it goes to the second level of the high level trigger. And this real time means that it could stay, I mean, the capacity it was until a few weeks, a couple of weeks. And with that, we have been able to increase our bandwidth for the trigger to this data processing in real time. to explain you the importance of this real-time processing. As you know, our storage capacity for the trigger, it is limited. The bandwidth of the trigger, it is given by these two quantities. One, it is the trigger output rate, and the other, it is the event size, or the average event size. This is in the case of LACB, as I have told you, since the raw data size, it's about 0.1 megabytes. At the end, it is quite light, the bandwidth. And of course, it is increasing in the next periods of data taking with a higher luminosity. And the main problem that we have, it is that the trigger rate saturates. So if you look at this plot in the bottom, if our signals, the signals that we are interested, the events that we are interested are shown in green and in blue. These are the beauty and charm hadron candidates. And this shows the rate, the y-axis is the rate of the trigger. And in the x-y-axis, what you have, it is momentum cuts. I mean, when you apply tighter cuts, what you see it is that the rate, it is not being reduced because we are selecting all our signals. So we are not reducing any kind of background. So that means that all what the trigger is selecting and pressing, it is what we want. It is our interesting signals. And the only way that we can do to reduce the bandwidth, it is to reduce the event size. So instead of taking the raw data, what we want to do it is to just take the relevant information of the event. And this is what it is based, the turbo model at LACB, which is working from 2015, which saves only a subset of the objects which are relevant for the analysis. You can see here, for instance, in the case of charm physics, we will be interested for charm candidates for this D0 meson, which goes to these two different tracks, a kaon and a pion. So what we do it is to save, to persist the object information of these tracks, which are at the level at the trigger level. So then with that, if you compare, you can have different levels of persistence, so you can save more or less objects, but in general, you can reduce your event size by a factor 10. So if you are saving the events in that they are selected, I mean, if you are selecting the events to be saved, what it is really important at this level is to have a detector very well aligned and calibrated, also in real time. So as you know, the alignment provides the best known positions and orientation of the detector elements, and the calibration applies the necessary corrections of the detector element response. So at LACB, all detectors are aligned and calibrated online at present, using a selected set of events from the trigger output, from the first level trigger output, and storing the buffer before they go to the second level of the trigger. And this buffer has 2 weeks of contingency. So in this schematic view, what you can see it is the alignment and calibration procedure. The time where the tasks are performed, so they are starting at the beginning of each field, and how much it takes of any of these alignment and calibrations to be performed. So you at the beginning you have the velo alignment, the tracking alignment, then you have the reach and the Cherenkov and the muon alignment, and then you can see also the calibration. The calibration for the reach and the calorimeters, and the tasks they do from 7 minutes. It takes from several minutes to several hours. So a bit more about this. For instance, in the case of the velo detector, so our first vertex detector, it centers itself around beam at the start of each field, so it is separated and centers again to avoid to be damaged. And then since it is moved, it has to be aligned each time at the beginning of each field. And it is done with a Kalman filter using drag heat residual with primary vertex constraints. So you can see here in this plot how it is when it is not aligned and then after alignment. And in this plot, here what you can see it is the stability of the alignment constants of this velo detector. So that means that the alignment constants are checked, and if they are very different to the previous one, they are updated, and you can see that the variation in general with the alignment number it is very small. After the velo, what we do it is to have the alignment of the full tracker system, so all the other tracking stations and also the muon chamber, and also you can see here the stability one of these trackers. And at the end, what we have, I mean, the output, what we have it is that as compared to when the detector is not aligned, the mass resolution, for instance, in these plots for the muon resonances, it is improved a factor 2. So you can see for the epsilon 1s how it is varying when the detector it is aligned in this and well calibrated in this plot. So for the rich detector, the refraction index of the radiators change with temperature, pressure, and composition, and it has to be calibrated. And it is done by fitting the difference between the reconstructed and expected Cherenkov angle. This is for the calibration, and also in addition, the rich mirrors, which are 20 segments for one of the rich and 96 for the other, are automatically aligned using rotations around local axis and fitting the variation of the Cherenkov angle. So you can see which is the variation in this plot before alignment, and you can see the variation of the Cherenkov angle as function of the azimuthal angle. So you can see the effect of this. And also in the plot in the bottom, you can see that the alignment constants are also quite stable in time. So this was for the rich detectors. For the calorimeters, we also are calibrating them automatically. So at the end of each field, you have LED pulses, and the LED amplitudes are compared with the references, and if needed, the high voltage are accordingly updated. This is the relative calibration, and also we have an absolute calibration once per month. We perform a pi0 calibration with large data samples. You can see in the plot in the left, this is the mass of the pi0 going to 2 photons, which is the calibration for the pi0 and LED calibration. And in the right plot, what you can see is that for one of the channels decaying to photons at the B meson decaying to a cluster and a photon, how it is the resolution, how well we can measure the resolution thanks to the calibration of the calorimeter. And it has improved, in fact, as compared to run 1, a factor 5%, the resolution thanks to this automatic calibration. The importance of this can be seen very well in this example, the outcome in physics. This is for the search for the muon resonances or new spin zero bosons, which are predicted in several beyond the standard models. So you can see these are just the d muon mass, the d muon invariant mass, and this is what it is obtained from the data. And you can see that you can have very different resonances with have very small width, and if you have not very well calibrated and aligned your detector, you will not be able to detect them. So this is what it is important. In addition, a fully aligned and calibrated physics objects in real time allow to perform analysis at the same time that the offline level. And then the data reprocessing, it is not needed. So you have a very fast and fresh analysis, and the results can be delivered in a few days. And also the importance of have this proper alignment and calibration on real time, it is that you reduce the systematics when you are going to the second high level trigger. So for the prospects for run 3, we expect, we are going to run for the next run times 5. We will have a higher luminosity, a factor 5. We are having new vertex locator and outer tracker, so we will have a complete new tracking system. And one of the main changes is that we are going to have the full software trigger at 40 MHz. So we are suppressing, we are removing the L0. Another important change is that we have decided to have our first level trigger selection on GPUs instead of CPUs. So then we will reduce the data transfer, and we will have also improved physics performance. And we are adding also an improved buffer, which will reduce the time for analysis and calibration. And this is very important because, in fact, for run 3, what we have realized is that we will have to have a large part of the physics program in real time, we will have to move to this new turbo model. During the run 2, it was just less than 20%, but now it is going to have to be, if we want to have to continue our physics program at LACB, this model of real-time analysis has to be about 80%. So this is very important. Just very briefly to comment about the software quality assurance, that this is very important also for the run 3. So we are, for sure, we have to have a proper online integration and monitoring, which is essential for the trigger operation, mainly now that we are moving to GPUs. We are developing the software infrastructure and improving the workflow. And we also are planning to have a distributing software maintenance based on as if based system. And just the conclusions of my talk is that at LACB we had an excellent performance in reconstruction at LACB during run 1 and run 2. This comes largely from the full alignment and calibration of the detectors, now are online and entirely automatized. And the alignment and calibration is crucial for run 3, since a large part of the physics program will be processed in real time. So this is really important. It is going to be more and more important in the future. That's all. Thank you very much.
Thank you very much. Very nice presentation. Questions? Yes, Tadeash?
Hello, thank you very much for this presentation. My question is, once you align the tracker or wheel, do you repeat the alignment during the fill?
I think, no, I don't think so. I think you just take it and that's all. Take the constants you can see here.
So it seems,
I think so, but I'm not so sure.
Stable.
It is quite, it is not, sorry.
So you check it's stable, so you don't need this more frequent.
Yeah, it is stable. Yeah, you can see.
Thank you.
Okay, any other question? Maybe I would have a very stupid question. You mentioned that alignment and calibration is going online, but of course there is still some time needed to apply changes when you will find something. But you also mentioned that you are using it for this topo trigger. So actually, how quickly you are able to apply changes, because then you would be excluding, for example, good events, or? No,
the thing is that they are buffered. So all these events are buffered.
Okay.
So then it is at the same time that you are doing the alignment the alignment and calibration at the same time that you are selecting the events. So everything is buffered there.
Okay. So you have these 2 weeks of.
Yeah, and then you have a 2 weeks on contingency, so you have some time to process the data and then to decide to have the decision. So it is not.
Okay, I now understand you. Okay, thanks. Okay.
Maybe I just have a quick question regarding the hardware of the farm, the CPUs and so on. Did I understand correctly that for run 3, you will add these GPU cores, but you don't increase the number of CPU cores? Is that correct?
Yeah, I mean, for the first level, I mean, we will have for sure a CPU farm for the second level of the trigger, but for the first level, for the HLT1, it is going to be processed on GPU. So we are going to add, this depends a bit of the throughput, but I think it will be less than 300 GPUs if they are, for instance, RTX or Quadro GPUs. But yeah, for this part, we will have GPUs for the HLT1, and then for sure we are going to add also CPUs for other parts of the farm.
Okay, thank you.
Thank you very much again. We have to move to our other presentation, which will be triggering in the Atlas experiment by Javier.
Hi, can you hear me?
Yes.
I hope I'm sharing my screen now.
Yeah, looks good. Thanks.
Great. Then thanks for having me here. As introduced, I'll be discussing a bit triggering in the Atlas experiment. So starting with the context, why do we even need a trigger system? So At a Hadron Collider, it's completely unfeasible, but also uninteresting to reconstruct and store every collision. But we, of course, want to store the interesting physics. So if you see the plot on the right, there's basically 6 orders of magnitude between the total cross-section and the, for example, W cross-section. And again, 6 orders of magnitude down to, for example, TTH, one of the kind of interesting processes that we want to store. So to make sure we have enough space for all this interesting process, we need to first reject a lot of soft QCD. So the Atlas trigger system has a 2-level system, which basically reduces starting from around 40 megahertz of collision frequency down to 100 kilohertz after level 1, and then about 1 kilohertz on average after the high-level trigger, and that's what goes to storage. And to put this 1 kilohertz into context, so at 13 TeV and peak luminosity, so we expect 600 hertz of leptonic Ws and way below 1 hertz of TTH. So in order to basically take this decision, the trigger needs to decide below 2.5 microseconds at level 1 and on average below 500 milliseconds at HLT, which events to store and which ones to reject. And to compare this, and offline reconstruction can take up to 30 seconds. So of course, we can't run the full offline reconstruction here. So starting with the first part of the system, which is appropriately called level 1 trigger. This is a hardware-based trigger. It reduces from 40 megahertz down to 100 kilohertz. And this 100 kilohertz is limited basically by the detector readout. So the level 1 trigger uses coarse information from calorimeters and muon systems to define some regions of interest that will be further scrutinized. And the selection at this point is quite simple. It selects on muons or calorimeter energy, which are consistent with electron photons, taus, jets, met. And despite being this a hardware trigger, there were several improvements in the logic introduced in run 2. For example, there was this muon end cap and calorimeter coincidence, which is shown in the top right, which helped to reduce the muon rate. But also there was updates in the filters and the noise cuts of the calorimeter hardware to cope with the higher pileup. So there's one additional piece of hardware, which is the L1 topo system, which basically takes the candidates from level 1 and is able to provide a bit more sophisticated selection by cutting on angles, masses, and those kind of 2 object variables. And this is critical for some triggers such as di-tau and B physics. And you can see here in the plot on the bottom right, basically you see a factor 4 reduction on the B physics, on one particular B physics rate, while after applying some mass and delta R cuts for only a few % inefficiency, which is of course not shown here. The second level of the system is the high level trigger. This is a software-based trigger, which brings this down to 1 kilohertz on average. And at that point, the full granularity of the data is available. Most of the times only in this region of interest defined by level 1, in some specific cases also for the full event. And here the selection is very close to offline. This includes also multivariate selections, which are crucial for B tagging and tau identification. The latency is order seconds, but on average, the maximum processing time should be below 500 milliseconds. So at the high level trigger, we have around 1,500 selection chains defined, out of which kind of 300 are the physics primaries, which is the backbone of then the Atlas physics program. And one of the highlights of the high level trigger is that we managed to keep the same or roughly the same kinematic selection or thresholds on trigger candidates throughout run 2, despite the increase in luminosity and pileup, thanks to many improvements that went in, and I'll be discussing in a minute. So after this, of the system, we need to take a decision, and this is what defines the trigger menu. Is basically the set of conditions that define when we store an event or not. So the trigger menu is documented in this pub node, and this I encourage you to read. There's a lot of detail here. It defines also which are the triggers where we invest most of the rates. So the highest rate goes at HLT for single lepton, of course, followed by tau, missing energy, and then single jet, single photon. One of the design choices in Atlas, which is actually different from CMS, is that we went for having same PT thresholds for an electron and muon at HLT, which of course has also implications at level 1. You can find also here the dedicated menus for heavy ions, low mu data set, all the special runs, and very nice tables defining all the rates and thresholds that we apply. So how we come actually to this trigger menu design. So designing the menu is basically finding a balance between the analysis requests, which essentially want to store absolutely all the events, and the system constraint. And those system constraints are then the main limitation for many signatures. For example, the level 1 constraint is then the limitation for di-tau, multijet, and B physics. This is essentially signatures with a very high cross-section or a very high fake rate at level 1. Then at HLT is the limitation for single jet, single photon. This is also what then defines why those goes into a trigger level analysis to overcome this limitation. And then the available CPU in the HLT farm is a constraint for some signatures like multi-B jet, low PT electrons, where there's simply not enough CPU to run all those expensive algorithms at low PT. And related to this third point, but a bit different, is that at the end we want to store events that we're actually going to be used and not thrown away. So we want online and offline reconstructions to be as close as possible. This, of course, not possible due to CPU. And this kind of resolution effects then become the main limitation for other triggers like missing energy or multi-jet triggers. Okay, then once we have this kind of trigger menu design, we of course want to make changes. And in order to do so, we need to be able to predict the trigger rates and the CPU. And to do this, we make use of the enhanced bias dataset. This is a dataset of roughly 1 million events, which is enhanced in high PT objects, which were selected only using level 1 triggers. And by knowing the level 1 prescale, this kind of selection bias can be removed by using by applying some event weights. So at the end, we have an unbiased sample, which has enough events in the high PT, high multiplicity regime to give good predictions for what you expect from a new trigger menu. And then reprocessing this data set with a new trigger menu can give us some rate and CPU prediction for all the triggers in development. And this is essentially how the trigger menu is able to evolve in real time and deploy without having seen it online. So moving to some performance highlights of Run 2, starting with the missing energy trigger. So despite a massive increase in luminosity and pileup, we managed to keep the offline missing ET threshold roughly at 200 GeV across Run 2, thanks to different improvements. And here I want to focus on the 2017 algorithm, which was essentially the one that changed most. Here, so the idea was to reconstruct missing energy from hair scatter clusters, and those are separated from pileup after doing a fit to the event, to the total energy, and extracting a per event threshold, which separates the hair scatter from pileup. This makes the algorithm very pileup resilient and allowed basically this constant threshold across Run 2. Then in 2018, this was combined with a previous algorithm, basically because background is is not so correlated across the meta reconstruction algorithm while signal is. So combining different algorithms gives even more pileup rejection. One other very nice addition to the Run 2 menu was an improved tau identification. So the algorithm moved to a recurrent neural network, same as offline, with some additions. It includes, for example, a zero track mode to recover inefficiencies from track finding in the first pass of tracking. This, of course, doesn't mean that there are no tracks. It's just that the zero tracks identified as tau core candidates. So there's still tracks being fed into the neural network. So if you see the plot on the bottom right, this is the difference between red and blue. You see a massive increase in efficiency, while the improved performance allowed to keep the rate constant. Another set of triggers that was introduced in Run 2 were dedicated B to K star E triggers, targeting different topologies with resolve or also merge dielectron final states. So here we use different strategies. So at level 1 was the possibility to define either 2 resolved electron clusters with some mass cuts, or merge, where there's just 1 electron close by to a jet, which basically doesn't allow the 2 electrons to be reconstructed separately. But these two have too high rates, so make use of the fact that of the correlated b-hadron pair production and require 1 muon on basically from the other b-hadron decay, or 2 muons with a lower PT, and this increase the purity, but at the cost, of course, of some inefficiency. And then there's a third strategy, which is run the HLT algorithm completely unseeded, so it runs on every level 1 accepted event. Then at HLT, the algorithm selects 2 electrons coming from a common vertex and with some mass cut. And this was quite some challenge, because those low PT electrons running on every level 1 accepted events makes it very CPU demanding. So this algorithm had to be slightly per scale at the peak luminosities, essentially due to the CPU constraints. But besides this small prescale, this was able to run unprescale for most of the run. Now some words about run 3. So we had, of course, an excellent system in run 2, but we want an even better one for run 3. So there are 2 upgrades which have the most impact on the expected trigger performance. One is the calorimeter upgrade. So there's a new readout that will allow for improved granularity in the trigger. So in the top plot, you see basically how the granularity improves from the left to the right. This is the run 2 compared to run 3. So essentially where there was 1 tower before, we have now 10 what we call supercells. So this improving granularity brings then the largest gain into the reduction of isolated electron rates and also a much better turn on. Then on the muon side, the upgraded NCAP can reduce by up to 40% the muon rate. This now will allow for spatial and angular coincidence, which wasn't the case in run 2. So this is the plot on the bottom right. You see all the yellow part, all the yellow stack is what the new upgrade will be able to reject in order to basically reduce the rate and be allowed to cope with higher luminosities. So this brings me to my last line. I hope I showed there was an excellent performance of the trigger system across run 2. This allowed us a very stable data taking. And this kind of apparent stability was just thanks to constant evolution and improvements, which made this offline stability possible. For run 3, the trigger system, both hardware and software, is being upgraded. And at the end of the day, what matters is that all this work into the trigger made possible a whole lot of physics result. And I'm showing here 3 particular ones which were only possible thanks to very creative and custom triggers that were introduced. Thanks.
Thank you very much. Questions? So you basically, you already mentioned run 3, where definitely the new small wheel will be the let's say biggest player now.
Yeah.
And it will be a big improvement. Of course, how is it for run 4? Is there still a plan that in tracker will be the part of level 0?
Right. I'm afraid I can't answer that. I don't know the details about run 4.
Okay. So is there something, because definitely triggering is simulated and solved also for run 4 and also for run 3. So is there something that you are especially like scared of, something that could be really problematic for higher pileups?
Well, for run 4, Atlas still has the internal decision on what kind of architecture to use this in terms of tracking, if there will be a level 0 or level 1 tracking. And this right now, I think it will be the decision that will have the most impact in the future in the trigger. But as I said, this is still an open decision.
Okay, so it is not decided. Mm-hmm. Okay, other questions?
Perhaps a small question. In LHCb mentioned that they will have a certain number, 300 GPUs for run 3. Do you have any plan for that for Atlas?
Yeah, so there are studies on the how to cope with tracking. Originally, Atlas had the FTK project, which was canceled. But there was a lot of kind of interesting lessons learned. And now there's kind of different alternatives on the table. One would be go completely for software tracking, but also kind of CPU. I think GPUs are being considered for run 4, not for run 3. But so far for run 3, this will mostly be dealt with software.
Okay, thank you.
Okay, thank you again. So are there any other questions? If not, thank you very much again. And we will move now from Atlas to CMS high-level trigger. So Federica. Yeah, we can see the slides. If you can go to full screen.
Yes, can you hear me also?
Yes, we can hear you.
Okay, good.
Looks good.
So, good morning to everybody. I'm going to talk about the high-level trigger of CMS, focusing on the performance that we achieved in run 2 and about new developments for run 3. Let me just remark what has been introduced already in the previous talk about the RAN2 LAC data taking conditions. So basically, as you can see in the two plots on the left, both the luminosity and the pileup condition became more and more challenging during RAN2, delivering up to about 40 million of events with, on average, 40 pileup. So in this environment, the CMS HLT rate is limited to just 1,000 of events per second. And this, as you can see in the plot on the right, can allow to assess a lot of physics signatures, but also rare, but not without posing a big challenge in the online data taking. CMS, as Atlas as well, adopted a two-level trigger system where at level 1, the rate is reduced from 40 megahertz to 100 kilohertz, performing an hardware decision using the calorimeter information and the muon system information. Then the following decision is taken at the high-level trigger, which is a farm of about 30,000 cores of GPU, which runs a sort of simplified version of the offline object reconstruction. In order to satisfy the CPU time limitation, the HLT is organized to run first the faster algorithm to make a first intermediate filter. And then the idea is to run the more time-consuming and the more complex algorithm only on a limited rate of events. This delivering at the end about 1 kilohertz of rate, covering a broad range of physics signatures that you can see in this plot on the right. The limitation to 1 kilohertz is mainly due to the CPU time which is available for the offline reconstruction. But on the other hand, thanks to the fact that the transfer bandwidth and also the space on tape would allow us to keep the rate higher. Basically, if we skip the offline reconstruction, we can overcome this limit of 1 kilohertz. And this is basically done doing data scouting and data parking, where the data scouting means that we only save the HLT reconstructed objects after doing a bit of analysis at high-level trigger. And this allows us to cover a mass range, for example, as you can see in this plot of the muon scouting trigger, which would allow to cover a mass range which would be uncovered by the normal trigger path with an high rate. This is the plot for the 2018 data. And the same is done, I mean, the same overcome of this limit is done doing data parking, which basically means to reconstruct the events when the CPU is available, for example, in shutdown periods, or basically when the prompt offline reconstruction is not run. And this is typically applied to the physics which needs of a very high rate like the physics. This was in general the strategy of the HLT of CMS, but now I want to show you the performance of the object reconstruction. Let me start from the tracking, which is at the base of the reconstruction of the other object. So tracking is running the same algorithm used offline, but just performing a reduced number of iterations for the overall track finding. All the iterations are seeded by the pixel it, where the pixel detector is the innermost one. In the 2016, we had the three iterations seeded by the pixel triplets. And then in the 2017, after the pixel upgrade, which consisted in the addition of one more layer, as you can see in this sketch, in both central region, in barrel and in the end cap, the three iterations were seeded by pixel quadruplets, being much faster and also more efficient. But unfortunately, due to an issue which happens to the pixel detector, basically we got some dead pixel modules, two more iterations were added and they were seeded by triplets and doublets. Then in the 2018, thanks to the new electronic readout system of the pixel, this kind of mitigation has been applied in a dynamic way, and this allowed to gain timing. What I told is basically summarized in this efficiency plot, which is measured on the 2018 simulation with respect to the Monte Carlo truth. You can see in the upper plot, sorry, in the different colors, the contribution of each iteration. And you can also see that the overall performance is quite close to the ideal condition, which is represented by the red line. It's also interesting to see that the dynamic recovery in purple brings at the plateau region, when it is applied above 1 GeV, about 10% of efficiency. But this does not affect significantly the amount of fake rate that you have in this bottom plot. Tracking is also at the base of the electrons. Actually, the pixel seeding is at the base of the electron reconstruction, which starts when a supercluster in eagle is matched in phi with the pixel hits. Again, in the 2016, the supercluster were matched to pixel doublets, and then after the pixel upgrade, they were matched to the pixel triplets, where the doublets were just for recovery. This brought a gain in efficiency, or let's say a gain in efficiency with a minimum increase of rate. Then the electrons are reconstructed with the same algorithm used offline, and in the years, the identification criteria has been developed in order to keep the efficiency stable or higher. Stable mainly in the central region of the detector, as you can see in the plot on the left, and even higher in the most forward regions. Let's move now to the muons, which are reconstructed in two steps. There is a first reconstruction happening in the muon system, seeded by the level 1 muons, and then these level 2 muons become seeding to trigger the level 3 reconstruction, which happens in the tracker detector. Level 3 is also able to combine the tracking information to the muon system information, forming at the end the level 3 muon candidate. Level 3 is also the algorithm which has been changed multiple times during run 2. At the beginning, up to 2016, there were two separated algorithms that were used in OR. One seeded by the level 2, performing two kind of outside-in pattern recognition, and one inside-out, the opposite pattern recognition. And then another algorithm seeded by level 1 muons, running the standard iterative tracking. The OR of the two algorithms, as you can see in the plot of the pure HLT efficiency over level 1, in the plateau region was basically fully efficient. Then, in the 2017, in order to profit of the new pixel upgrade, the algorithm has been, the level 3 reconstruction has been moved to use the standard iterative tracking algorithms that combines the 3 iterations, basically the outside in and the inside out seeded from the level 2 muons, and the inside out seeded from level 1. In the 2017, this inside out from level 1 was performed only for recover the events where no muon candidates were built in the previous step. But this was not too much efficient, even due to the pixel issue that happened. Then in the 2018, to cope with this issue, muons decided to add one more step in the inside-out iteration, and also to switch always on the inside-out iteration seeded by level 1. The idea was to be as much efficient as possible, but then a muon identification filter has been added to keep the rate under control. And you can see the recovery in the 2018 data plot of the pure HLT before and after the recovery. So the overall trigger efficiency for muons during the 3 years has been generally stable at 90% in the plateau region. Basically, it is higher in the barrel in the central region than in the end cap due to the level 1 limitation. The level 1 has been improved during the 2017, but despite that, due to the issue happened at level 3, the efficiency of 2017 was not too much improved as the one reached instead in the 2018, thanks to the recovery that I have described before. Moving on to the taus. Basically, the hadronic taus are reconstructed using the particle flow algorithm, which is one of the most time-consuming. And indeed, this algorithm can run globally only for the E tau or mu tau triggers, while it runs regionally around the level 1 tau candidate for the D tau triggers. And also it runs only after applying a first pre-selection based on a reconstruction done at the calorimetric level and an isolation at the tracker level. Then the level 3 tau candidate is reconstructed, and this algorithm was updated during REN 2. First, level 3 was based on a cone algorithm, and after it has been aligned during the 2018 to the offline reconstruction using the hadron plus strip algorithm. In this way, it has been possible to separate the two tau hadronic legs, and this reduced a lot the rate, basically of 10% per leg. Thanks, of course, to the improved momentum resolution, as you can see in the plot at the bottom right. So the overall performance of the tau trigger developed during the years. You can see here the mu tau, E tau, and the D tau trigger in the 3 plots, where the main difference are due to the level 1 seeding, basically, especially in the shape of the mu tau and the E tau trigger case. While the fact that we had a higher efficiency in the 2016 is mainly due to the better pileup conditions. Then, JET and MET are also reconstructed at HLT, and this is performed in 2 steps, first using the calorimeter information, and then running the particle flow algorithm regionally for jets, and globally, of course, for the math, where the two main updates regarded the calibration to cope with the noise and also the application of the jet energy correction. Then the jets are also identified as B-jet. This is done using the same algorithm which is applied offline, and the algorithm was the combined secondary vertex up to 2017 to move to a deep combined secondary vertex in the 2018, which performed more efficiently, as you can see in the plot on the right, where you have the solid line, which basically is able to give a higher B-jet efficiency at same level of the lepton flavor efficiency. It performs better in case of particle flow jets, but it's also true that using the calorimeter jets allow to spend much less time. Let's move now to run 3. Basically, we know already that the data taking conditions should be much similar to those of the 2018. Therefore, we can do better at HLT. So apart to perform some improvements due to the local reconstruction, basically after the updates, the upgrade of the detector after the long shutdown 2. And the main effort that is ongoing at HLT is aimed to get the code running on an heterogeneous HLT farm of about the 80% of CPU and the 20% of GPU. This would allow to reduce the timing, as you can see in the two charts at the bottom, but not only, this would also allow to achieve a better track resolution, and this would be very promising also for the particle flow developments. And in particular, particle flow developments would allow to increase the HLT rate for the scouting. This brings me to the conclusion about the performance of the HLT during run 2 that, as I've shown, has been very stable during the year. And as you have seen, we learned a lot. We have been able to cope with the changes in the data taking conditions. Therefore, for the new data taking, we expect to do even better. As I said, the use of the CPU is crucial to enhance the use of the data scouting, and this would allow to assess many exotic search with a high rate, and this is one of the main goals that we expect for the intense physics program that is going to happen. And that's it from my side.
Okay, thank you very much for a nice overview talk of CMS high-level trigger. Please, questions. Okay, maybe I would have a question. As we heard already from Atlas, there is no like a strict decision on the trigger strategy for high luminosity LHC. How is it for CMS?
For high luminosity, there is, I mean, there are a lot of efforts ongoing, but they would pass before for run 3. Of course, the use of GPUs will be much more intense, let's say. And then we will profit of the tracking. With the tracking is going to give objects at level 1.
Yeah. So
So
that's a point. Yeah. So now for run 3, you will stay with muon and calorimeters still for hardware trigger, and for run 4, you plan to include tracker.
Yes. For run 4, we are going to have the level 1 track trigger. This would allow to skip some time the, let's say, level 2 reconstruction for some objects, or let's say it would allow to do it better in a more efficient way, reaching a higher resolution. All of these cases are under study now for each physics object.
Okay, thank you very much again. Thanks.
Maybe a quick question,
Yes.
Federica, there will be, for CMS, new gem detectors in the forward region for run 3. I'm wondering whether they have any impact on your plot in slide 11, the muon efficiency in the forward region.
Yes, it should be also thanks to the track trigger. This would allow to extend a bit the eta coverage, but just a bit.
Okay.
Because the extension should be up to 2.8 in eta. So combining both tracking and gem, we would expect an extended eta coverage. I mean, it would not be so crucial, but it would, of course.
Okay, thanks.
Okay, I see one raised hand, Javier.
Hi, I had a question from in slide 15 where you show the timing. You have 450 milliseconds in run 3, but at the beginning of the talk you mentioned a limitation of 260 milliseconds. So is this just a kind of a peak event, or is this really the average?
This should be for a run 3 menu. And I'm not sure about this, whether it is a limitation, whether it is an extended limitation due to the extension of the CPU time available for the offline. I would say that it is a peak and not the average, but I'm not 100% sure.
Okay, because the Atlas timing looks a bit more like this 450, and it seemed to me very constraining, this 260 milliseconds, but of course might be different across experiments.
But that is on average.
Okay, thank you very much again. Unfortunately, we have to move. We are significantly late. So, okay, now we are moving from CMS to Bell 2, again, high-level trigger.
Hi.
Hello.
Let me just share my screen.
Yes, you can try full screen.
All right. So I will talk about, sorry.
It's fine. You can start.
Okay, all right. So I'm Marcus. I will talk about the design and performance of the Bell 2 high-level trigger. And yeah, so just a quick reminder, the Bell 2 experiment, you can see a zoom in of our detector here on the left side. So essentially, it's also a 4-pi general purpose detector. We have silicon detectors in the very center, surrounded by a drift chamber. We have 2 PID systems, which are the time propagation detector in the barrel region and the A region in the forward region. We have an electromagnetic calorimeter and a K-long muon system outside of the solenoid. So up to date, we accumulated approximately 74 inverse femtobarn of data. And we did this with the SuperClick-B accelerator. And so things are going well. Just want to mention this here that we actually broke the world record on the instantaneous luminosity on the 21st of June this year, which was 2.4 times 10 to the power 33. So, and the overall aim is to accumulate 15 inverse autobahn in the next 10 years. Essentially, we are currently here, roughly at this point in the plot, and we want to, scale this to here. So there's still a way ahead of us. All right. So now I want to talk about how to actually get the detector data from the electric signals of the front-end electronics to our storage system. So this is essentially a sketch of the Bell 2 data acquisition system. You can see here that the PXD has a special position in this diagram. This is because the readout of a PXD works a bit differently from the rest of the detector. So essentially, PXD creates 1 megabyte of data per event, and this is too much data to actually read out. So this readout of data is buffered on this so-called ONSEN board, and all other sub-detectors have more kind of a regular readout, which is front-end electronics, and then at some point it's sent to the event builder. And this rest of the detector generates roughly 100 kilobyte of data per event. And this 100 kilobyte per event is then distributed to the HLT with a design input rate to the high-level trigger farm of roughly 30 kilohertz in a round-robin way to the individual HLT nodes. And so the purpose of the HLT, for one thing, is actually filtering the interesting physics events from background events. And the other important part of the HLT is calculate the so-called regions of interest for the PXD readout, where we essentially tell the PXD readout, these are the interesting regions on your detector, and we only want to read out this data. And this then reduces this data stream of 1 megabyte per event to roughly another 100 kilobyte per event, which then sums up to roughly 200 kilobyte per event. And this data is then sent to the second event builder, build up, so the HLT output and the ONSEN output are merged together and then distributed to our online storage, and then at some point moved to the offline storage. Another important component on this live reconstruction is the express reconstruction, which essentially, together with the HLT, allows us to do data quality monitoring. And so the express reco is important because essentially here we reconstruct the whole event without the PXD, and this express reconstruction allows us then to have live information on the full reconstruction of the data, including the also the PXD regions of interest. All right, so further I now want to talk about this data transportation scheme, essentially from the first event builder to the second event builder. Just a reminder, so the design components of the HLT is an order of 20 independent HLT units, each containing 12 to 20 worker nodes with roughly 40 to 50 CPU cores on each node. And each HLT node has a dedicated input, output, and storage node. And what we have to deal with is roughly 20 kilohertz input rate from the level 1 trigger, which can peak up to 30 kilohertz. We have this round-robin distribution to the individual HLT nodes, like you mentioned earlier, and then we can have proper load balancing within individual HLT nodes amongst the workers. Average event size 100 kilobyte without the PXD data, which doubles then including the PXD data. And the decision for the region of interest for the PXD readout is per design 5 seconds. Okay, so let me first talk about the pure data transport, so without any reconstruction involved. So this was the old model, which was used during phase 2 of our data taking. Essentially, you get this non-PXD data in the input node, and then you have the distribution among workers. You make your make your reconstruction. You send out to the HLT output node, and this sends it to the PXD readout, and we send the information to storage. So what you can see here is that we have this data flow was based on shared memory ring buffers. These are those circles here. We have quite a lot of them, and the issue was that those shared memories are usually decoupled from specific processes. So in case something crashes, you can have a non-trivial cleanup, which posed some problems. Then the second issue was that this is a quite rigid structure via these ring buffers, and you do not have the ability to send non-data communication among this transportation scheme, and you lack any advanced control features or monitoring features of the connections. And the last part is this was all custom implementation, which actually worked, but this custom ring buffer and TCP implementation were also very difficult to maintain. So what we decided to do is we employ this, I think now widely known framework ZeroMQ, which is an open source library And the idea was to increase maintainability because you have this abstraction of the complicated features into this external library. And we built the core components now based on this CRMQ. And yeah, so if you never heard of it, it's an industry standard for high-performance process asynchronous messaging in distributed applications, essentially exactly what we have here. Okay, then this is essentially the data transportation scheme which we ended up with. So this diagram kind of reduced a little bit. Now the inter and intra node communication is handled via those CRMQ-based TCP connections. You can see here those ring buffer receivers and transceivers are gone, and this buffering of events is now done via a TCP queue, and you don't have those ring buffers, which have proven to be quite error prone in their cleanup sometimes. Additional nice features that you can either pass event data or control messages, and you can have now more advanced features on, for example, load balancing, back pressure handling, and so on. And also this initialization and cleanup of connection is done automatically, so you do not have any residual states of this shared memory, which posed problems in the past. Okay, so this data transportation scheme was, of course, has undergone some stress tests, and the stress tests have shown that those this scheme can handle up to 10 kilohertz input rates per HLT unit. In comparison, this previous implementation based on the ring buffers was able to cope with roughly 1.5 kilohertz. So taking this expected input rate of 30 kilohertz overall on all HLT units, this new data transportation scheme actually is future-proof for any anticipated luminosity from Super KP. Okay, let me come from purely the data transport now to briefly to the reconstruction. So essentially, task of the online reconstruction is pre-scale processes with high cross-sections, for example, Barber scattering, down to reasonable levels. We have to generate those regions of interest for the PXD readout from SVD and CDC tracks. Another task is to tag the actually interesting events. So what do we want to store? And additionally, also tag so-called create schemes for fast offline analysis and also calibration purposes. And the last task is, of course, to provide fast feedback on the data quality via this data quality monitoring. And one important feature of our online reconstruction software that it's actually identical to the offline reconstruction. So we do not have any bias in the specialized online reconstruction. And this also means we have very good control over trigger systematics in the future. Okay, so this is just the HLT processing time because we have this essentially time frame of 5 seconds to reconstruct the event to make this decision for the Onsen board. On the left side, you can see, so this is taken from the phase 3 singular run. So this is actually real processing time on data. And you can see this has it's well below 5 seconds. But of course, this distribution can have a very large tail to the right. But this looks fine. And also the scaling for the multiprocessing is behaving very well. So you can see here, this was tested on the machines with have 20 real cores with hyperthreads. And you can see this first linear scaling until you reach the region of hyperthreading, the second linear scaling until you essentially fill up all your threads, and then you do not gain any additional processing time. So our HLT software, which is essentially also just the offline reconstruction software, shows very good scaling properties and parallel processing. Okay, and if we now put these individual parts together, what can we handle actually from the anticipated input rate from the level 1 trigger? So we are currently, for summer, we are currently reaching this point. So we can handle a sustained input rate of roughly 11 to 12 kilohertz. But if we scale the current setup to the anticipated hardware we will get for the high-level trigger system, we will not reach this 20 kilohertz input rate, which we anticipate from the level 1. So this looks like a big issue, but actually we're currently working on it, and I think this is a solvable problem. So there's work on optimization of the track reconstruction, which will give it will give, of course, some processing time. And then there's also some trivial optimizations you can do, because not the full so we use the same reconstruction as offline, but you do not need every reconstruction step for making the proper filter decision. So you can just start discarding modules in the reconstruction chain, and this will already give you roughly 10% improvement of the reconstruction time. So the overall goal in this optimization is to keep the online equal to the offline reconstruction as close as possible, to try to avoid to introduce any additional trigger systematics. Okay, then let's come to the performance. So essentially we have two HLT operation modes. The one is called filtering. This is what you usually would think about what the HLT is doing. So we calculate the filter decision and either keep or discard the event. And the other mode is called monitoring. So we do the same thing. We calculate the filter decision, but we keep all events which pass the HLT. So all events which arrive on the HLT will also be sent out to storage, but those filter tags are added. This allows very good direct measurements of the trigger efficiencies, as only the level 1 trigger will be applied. And as we currently only have input rates from the level 1 from 4 to 5 kilohertz roughly at the end of our phase 3 run, so this year's run, we were able to continuously run in the monitoring mode, which then allows for very nice trigger studies. So one of those trigger studies I've brought here, this is the trigger efficiency for single photon events. This is important. This trigger is important for searches for invisible decays of a dark photon, and this study was performed on a radiative muon pair control sample. And you can see here distributions of the center of mass energy for two different trigger lines. One is a 500 MeV trigger line, and one is a 1 GeV trigger line. In blue, you see the all radiative muon pair events, and the data points actually are the ones triggered. And you can see that this is a very nice agreement. And if you see in the bottom, the HLT efficiency over the same center of mass energy of the photon cluster, we have a very good efficiency on those. And also what I want to stress is that we can go to very low energies of the single photon, which means we can probe high masses of the dark photon candidate. Okay, let me come to my summary. So the data transport across the HLT is now based on a new framework based on Serum Q. It's shown to be future-proof. We used this in the last months of data taking of Bell 2, and it worked out fine. We study the HLT processing time, shows good scaling behavior. We're not quite there yet to achieve all our design goals, but optimizations are possible and are worked on, and we are sure we will achieve this goal. Okay, and the HLT triggers. So I mentioned that we run on this monitoring mode, so trigger lines are currently intensively studied. Unfortunately, I could only bring one of the study to my talk here, but all those first results show very good behavior, and we are confident that this will work out very well in the future. And yeah, thank you for your attention.
Thank you very much for this very nice overview and the status, current status. Questions, please, to Bell 2 high-level trigger. Yeah, actually, you mentioned that there was a nice plot how it is saturated. The number of CPUs is actually higher. I think yes, that it looks like the much more cores will be not the solution to get to the design.
Sorry, this is. So essentially, if you double the number of cores from here to here, you double the sustainable input rate. This is maybe.
Okay, so does it mean that you, in principle, you would be able to get to the design value, to your goal, with a higher number of cores?
Yes, yes.
Okay, then what is the limit like for this? Why you are planning for 6,000 cores and not, for example, 20,000? Like, is it like?
This is what is currently, I think, I'm not 100% sure, but I think this is what is agreed upon, what is going to be paid for at the moment. So there's no technical issue to just scale this with more cores. We just would need the funding, I guess.
Okay. And what about, we heard today already several times about these GPUs. So would it be, for example, a solution possibility?
So I think in principle it's possible, but I don't think it's necessary to put this work into GPU tracking for the purpose of HRT, because we almost reach the goal what we need to do from our design values, and so I don't think it's necessary, but of course it's interesting approach.
Okay, so you mentioned here there is some trivial possibility to discard reconstruction step. It is like 10% improvement. Are there some other plans or some other steps that we would like to do?
Except of those two at the moment?
Mm-hmm.
No, currently. So I'm not aware of any particular. I mean, in general, the reconstruction will be optimized not only for track reconstruction, but I know specifically that people are working on the optimization of the track reconstruction.
Okay, so you believe that these two things will help you to get to the design, basically?
Yes.
Okay, thank you very much. Are there any other questions or comments? Please. Okay, if not, thank you very much again. Thank you to all the speakers of this second part of the session. It was the last talk of this second part. Now we will have a coffee break, and the next part, the third part of the session, will be chaired by Anne. Is it true? Yes. So Anne, I think that I will give it to you, and it's up. It's yours now. So
okay.
You can define.
Okay, thanks.
You can define how long will be the coffee break. Probably 5 minutes.
Okay, that's fine. We come back at 12:15. Does that sound good with everyone?
Yeah.
Is that okay, Jerry?
Yeah, for me definitely. Yeah. Okay, 12:15 Prague time.
12:15 Prague time. Yeah. Thanks a lot.
Of course, if somebody would like to check the sharing, you can. Yeah.
Hi. May I check my sharing, please?
Yes, sure. Of course, Elena. Yeah.
Thank you. Thanks.
Yes, hi. I would also like to share to check the sharing and the sound.
Okay. And then you want to go full screen?
I think so. I'm on this weird Acrobat reader, and I think this might be the best I could get it to be. Is it problematic?
It's okay. No, not at all. It's good enough. Yeah.
Okay. Sorry about that. Okay.
No, it's fine.
All right. So I guess I'll stop sharing. Thank you.
Okay. To the speakers, if you have sufficient bandwidth, you're welcome to also share your video. If you want, it's up to each person depending on how good their connection is.
Okay, that's something that I will also check right now. Okay.
Okay. Andres, yeah.
With the screen.
Yeah.
Let me just share. Hold on a second. Can you see my screen?
Yeah, that's good. You want to try go full screen?
Yep, hold on. I will try to go in this weird full screen, half screen mode. Let me just try to. Hold on. Can you see the slides now?
Yeah, it looks good.
That's good. And the aspect ratio is okay as well?
Yeah, it looks fine.
Okay, perfect.
You want to share your video?
Yes, let me try that. Usually my connection is pretty bad around here, but let me check if that will work.
Sometimes in the bottom left of the video. Yeah.
You should see my video.
Bottom.
Is it okay? Everything is working? No stuttering? All good?
No, it's good actually. It's not even too pixelized. So yeah, give it a try with the video and switch it off if you have problems. Yeah.
Okay. Thanks. I'm then all
Thanks
set.
a lot.
And I would like also to test the sharing, if it's possible.
Okay. Yeah, sure, Fernando. Yeah, go ahead.
Right. So let's share screen. This one. How would you see it?
I do. Yeah.
Right. If I put full screen, you should be better there.
Yeah, better. Yeah.
Or,
change slides just to check. Yeah, that's okay.
Okay. And then let me just open the. I can't see myself though. I'm sharing the video too.
Okay, we see you. Just a little in the corner, which is perfect.
Okay, cool.
Yeah.
Great. So then I'm
Thanks.
stopping the video and the sharing. Do you see the slide? Do you see completely? Or do you see ICHEP 2020 in the bottom? Or
Yeah,
is it
we
cut
do.
out?
No, we see it. Maybe what you should do is go full screen and then share. But we see it perfectly. There's just this little green
Okay, great.
green thing around. But you
Okay,
want to
great.
go again? Go again. Oh, no, actually, this is fine. Yeah, go full screen
Okay,
again.
great.
Just
Okay,
check.
let me just stop sharing full screen and then screen now.
Yeah.
Yeah.
Yeah, that's even better. That's perfect.
Okay, great. Thanks a lot.
Thank
so
you.
I'm stopping now.
Okay, perfect.
Thank you.
Okay,
Hello,
anybody
can
else?
you see?
Yeah.
Can you share my slide?
Sure. I
Yeah.
can't see yet.
Yes. So this is my display, and then yeah. Okay. Can you see my slide?
Yeah. Change slides.
And
Let's see.
just a moment. Yeah.
Yeah, it's good.
Okay. Thank you very much. I stopped the shared. Yeah.
Perfect. Any of the other speakers want to check?
I can do a quick check, cannot hurt.
Yeah, go for it, Oscar.
This should work, right?
Yeah,
And voice is fine as well.
voice is good. Yeah.
Okay, great, thanks.
Yeah. Okay, well, I think the first speaker, Fernando, you can get set up and we'll start at 12:15.
Okay. I can share then and be ready. So when you tell me to start, I can start.
Okay. Okay, well, perhaps I can just introduce Fernando. You see from the title of his talk, he will present projected Atlas electron and photon trigger performance in run 3. And I understand, Fernando, you're from the University of La Plata.
Exactly, yes, from La
Yeah.
Plata, Argentina, yes.
Argentina, okay. I think, yes, please go ahead. Yeah, thank you.
Okay, great. So let me go straight to the second slide. This has been introduced already by Javier and by the CMS talk, which the trigger system, what is it for? Actually, there's a lot of events and physics being produced in every collision, but what we are interested on is very rare. So we can't, none of them, we can't process everything and we can't store everything. So then we have this trigger system, which basically does an online analysis of the data and only stores whatever is actually interesting for us. So and you see on the right, different cross sections of the different processes as a function of the center of mass energy of the collision. So in particular, I'm going to talk about the part of the trigger that is responsible of selecting events with electrons and photons in the final state. I don't need to tell you that there are many interesting physics in which we have electrons and photons in the final state, and that's why we want to trigger on them, namely standard model cross-section measurements, measurements of the properties of the Higgs, and search for beyond standard model physics.
And then this is challenging because any of these are very rare, like, for example, 3 Higgs for every 10 to the 10 pp collisions. So we need to select them and also just drop everything that is not interesting, which is very, very, very abundant. So we want to select our electrons and photons, keeping our thresholds as low to as inclusive as possible, and then to reduce the input rate of 40 megahertz of collisions down to 1.5 kilohertz of output rates of events accepted, which means and everything we drop cannot be recovered by any means. So for round 3, there are some challenges, including that the increase of the center of mass energy of the collisions from 13 to 14 TeV in the LHC, the peak luminosity would go up to roughly 2.2 times 10 times to the 34 per square second per centimeter per square centimeter per second. And then also we will be leveling, which means that we will stay at peak luminosity for longer, and then the pilot profile will be different with respect to round 2. And also we will double roughly the total integrated luminosity. There will be changes in the TDAC structure for round 3. The level 1 system will be implemented in new hardware. We will give us better granularity and better possibility to identify electrons and photons. And then at the high level trigger, we will be using a multi-threading native software. And then we will be using more offline-like algorithms at the HLT than in round 2. On slide 5, so to trigger on electrons and photons, we have a first level trigger, which is implemented in hardware, and basically selects a region of interest in the calorimeter where we found energy deposit there. So then that position and type is passed to the high level trigger, which is the second stage, which is implemented in software in a rack of computers. And then it has like 2 steps, a fast reconstruction to reject as fast as possible, and then a precision identification and reconstruction, which is offline-like. So basically for electrons and photons, we get tracks in the inner detector and clusters of electromagnetic energy deposit. We match them and we create our electrons and our photon candidates. For us, photons in the HLT is only clusters in the electromagnetic calorimeter, while electrons has a combination of both. And then we use offline techniques for identification and calibration at the HLT. On slide 6, among the improvements for the level 1 for round 3, you see we are moving to something that's called supercells, in which basically we improve our granularity and at the level 1, which means that with this new hardware, we can have finer granularity. We will have better resolution of energy, as you see in the top right plot here, and you see the comparison of the energy resolution for the upgraded system in blue with respect to the red plot, which is the current, or let's say legacy level 1. And also we will have a better efficiencies versus ET, which is called turn-on curves for us, in which with the new system, we can either have the same thresholds and reduce the rate by a half roughly, or keep the same rate of accepted events by reducing the level 1 threshold by a big amount, which is very good. Also, going to the HLT now, in the fast part, we have been using neural network techniques to make an early rejection of electron backgrounds, which is called the ringer algorithm. Basically, we build rings of energy deposit surrounding the hottest cell in the calorimeter, and then we create the discriminator there using the neural network techniques. So even this is maybe slightly slower or slower than previous techniques in which we did a cut-based. Since the reduction is so much for the background, we basically gain CPU demand downstream by rejecting earlier. In round 3, we're planning to use this ringer technique not just only for 15 GeV electrons as we did in round 2, but also for every electron chain and for every electron selection at the HLT. We are also implementing and developing this technique for selecting photons in the high-level trigger. In the precision step, then, we have at the HLT, we combine tracks and extrapolate them to the calorimeter, and then we compute our electron candidates too. Again, as I mentioned earlier, for photons, we only use calorimeter information, but to construct our electron candidates at HLT, we match them to tracks, and then with the combination of both, we apply selections on the tracks, on the calorimeters, and the combination, and we create our electron candidates. Once we have our candidates, we need to identify them. And for that, we use what we call shower shapes, which is deposits in the in depth and width in the electromagnetic calorimeter. We create different observables we call shower shapes, and with applying selection of them, we identify our electrons and photons. For photons, we use cut-based selection, which means we cut on rectangular cuts on each of these variables. And then for electrons, what we use is likelihood-based identification on the selection of shower shapes and track variables. And we define different working points with a better background rejection and better purity, namely loose, medium, and tight selection and identification working points. And for electrons, as I mentioned, we not just only use these shower shapes on the calorimeter, but also observables built from the tracking, namely also the TRT and number of hits in the inner detector. So let me, so let me show you here some performance we obtained in run 2 for our electron and photon triggers. So for this here, I'm showing the performance of electrons, in which you see on data, we make this technique, which is called the tag and probe, in which we take a Z decaying into 2 electrons. We trigger the event with 1 electron, and then we look for a second one. And then if the second one is close to the Z mass, we take that as an electron, and then this is our probe to test the efficiency of our trigger. These plots show here the performance of the electron triggers during run 2. And you see that the performance is very good with the very sharp turn-on curves, which is efficiency gets very high, and the efficiency versus the pileup is also stable. You can see the full details in the paper there. Then on slide 11, you see that for photons, we also use a data-driven technique to get the performance of our photon triggers. And then for that, what we do is to take the relative decay of the Z. So we take the Z, then one of the leptons, which is either an electron or a muon, just radiates a photon, and then we trigger on the dilepton event, and then we take the photon as a probe to get the probe to measure the efficiency of the trigger. And then you see here the performance of the photon triggers and as a function of ET in the left, which is a very sharp turn on, and then gets very high efficiency, and then as a function of mu on the right. And I think I skipped a slide. Okay, no, I didn't. Okay, sorry. It's too early here, I'm sleepy. So if you go to slide number 12, then among the improvements we are planning for the run 3, and we are actually implementing right now in our software, you see on the left and on the right, the schematic diagrams of the sequence of algorithms we are going to implement, or we're implementing right now in the run 3 implementation of the electron trigger and photon triggers. So basically, one of the things we're doing is in the precision step, we are using exactly offline algorithms, not just offline-like algorithms. But we take the offline electron and photon reconstruction and identification, which will make our trigger better synchronous with the offline than it's now. Then we are also improving by doing this, the calorimeter reconstruction, because by using offline algorithms, we are using superclusters to seed our electron and photon candidates instead of a sliding window-based algorithm we used in the past in run 2. So this will give us a much better resolution of energy at the HLT than before, which makes, we will make our efficiencies as a function of ET sharper and better. And also we are improving the tracking by implementing at HLT for the first time, which we call the Gaussian sum filter, which has been used for brand recovery at the offline since 2012, but has never been used in the HLT. And we are planning to use this, and we will make our electron resolution in PT much better at HLT than what is now in, or has been in run 2.
2 minutes.
Yes, so then in conclusions, I don't know how, I think I'm time. Then it's, okay, so as I mentioned, the electron and photon triggers are key for the Atlas program in terms of many physics channels. Challenges for run 3, the operations will be harder, the instantaneous luminosity will be higher, and our center of mass energy will be higher, making the QCD background more abundant. And then among the improvement in performance, well, we're going to use keep the rates low and try to keep the thresholds as low as possible. We are moving towards a multi-threading system in run 3, which will make better use of the CPU of our HLT farms. We are using offline algorithms at the precision steps, which will make our trigger very closer to offline and more efficient. And we are going to use our neural network ringer algorithms in the fast reconstruction for photons and also for every electron selection, not just for 15 GeV ones. Okay, that would be all from our side.
Thanks very much, Fernando. Extremely clear talk. There are questions for Fernando. Please raise your hand. Yeah. So it seemed, yeah, to be very clear. Maybe if I just ask 2 slides before, slide 10, the plot that you have from data for electrons. So if I understand from run 3, you expect the plot on the right-hand side to have a higher efficiency and also to be better behaved with high pileup. Is that correct?
Well, so what we should gain for sure is this turn-ons to be sharper. So as a function of it should be higher, faster, because we are reconstructing the energy in exactly the same way as offline using these topo clusters instead of a sliding window. Then as a function of pileup, well, we perform very good. So we expect in principle to be, let's say, to re-optimize and then still keep, a good performance as a pileup as in the last 2 years of run 2, which is the purple and blue, let's say.
Okay.
So we should be able to keep that at least. But in principle, we will gain in the rise of
in the turn on.
Yeah.
Okay. Thank you very much. Okay. If there are no other questions, well, we can take the discussion to Mattermost if you have more. And you can stop sharing. And we can ask Eleanor to share her screen. And Eleanor will present the performance studies of run 3 JFEX algorithms in the Atlas calorimeter trigger. And Eleanor Vilhauer is from the University of Edinburgh.
Hi, thank you. I'll be discussing the performance studies of the run 3 JFEX algorithms in the Atlas calorimeter. From between run 2 and run 3, Atlas is implementing upgrades for the TDAC, liquid argon calorimeter, the new small wheel, and the level 1 calorimeter trigger. And the reason for the motivation, the motivation for the upgrade is to accommodate increase in luminosity. And at the end of run 2, we had 190 inverse femtobarns. By the end of run 3 in 2024, we'll have 350 inverse femtobarns, and then all the way in 2040 for the HLLHC will be a very large amount for 3,000 inverse femtobarns. But with this increase in luminosity, you also have a whole bunch of pileup, and that presents a lot of different challenges. And so to alleviate those challenges, the upgrade is well motivated, and also the upgrade allows for improved detector performance, which allows for better physics. So in run 2, the Atlas trigger system was comprised of 2 levels, a hardware-based level 1 and a software high-level trigger, HLT. And in run 2, we have the level 1 calo receiving information from the tile and liquid argon detectors. And this jet energy processor looks for missing energy, total energy, and jets. And the cluster processor looks for taus, photons, and electrons. Then the central trigger processor and the topological trigger, L1 topo, receive the information from the cluster processor, and the high-level trigger receives events that pass the selection, and then accepted events are saved to permanent storage. So in run 3, there are 2 major sets of upgrades to the Atlas level 1 trigger system, there's an increase in the readout granularity in the liquid argon detectors. So there's 7,000 towers from run 2 to 36,000 supercells in run 3. And there's also the addition of the feature extractors, effects. So there's the global effects, which identifies large radius jets, the electromagnetic effects, the effects, which finds taus and electrons and photons, and then also the J-effects, which is the jet effects, and it identifies jets and missing transverse momentum and other energy sums. And the J-effects has 6 J-effects modules, and each J-effects module is an ATCA board with 4 processor FPGAs, and it could process a total input data rate of 3.6 terabytes per second, and it has a full ADA coverage of 4.9. So the nice thing about the new JFEX jets are that they have much finer granularity in ADA and Phi than the current level 1 jets, and there's opportunity for pilot mitigation via pilot subtraction, and that would allow for great improvements when we have high pilot in run 3. So in run 2, the level 1 jet was formed using a 0.8 by 0.8 sliding window algorithm with a 0.2 by 0.2 tower and a 0.4 by 0.4 seed. And you can see that this red, one red square is the 0.2 by 0.2 tower, and the full red square is the 0.4 by 0.4 seed. And the full figure, including the red and the blue, is the level 1 jet ROI. So on the bottom left, we can see that the trigger efficiencies for single jet level 1 triggers for 2015 and 2016 are shown, and the data 2016 has a solid circle, while data 2015 is an unfilled circle, and the trigger efficiencies, the jet triggers become fully efficient at the same point. And just for reference, the L1 J100 is the lowest unprescaled trigger. And on the right, you can see trigger efficiencies for single jet triggers with 3 different calibrations applied to jets in the high level trigger. And the offline threshold here is 440 GeV, whereas in the previous plot, you see that the L1 J100 is 100% efficient at 200 GeV. And so you can see that the large HLT rate serves as a limitation. And so there are a lot of physics motivations to getting past these limitations. And so for allowing for better performance of the triggers, one such physics motivation is dark matter, and dijet events serve as a forum for which you could search for dark matter. So single jet triggers are used for dijet events above 1.5 TeV. And one dark matter process is Z prime to quark. And to look at the dark matter summary here, you could see that the jet trigger, like single jet trigger and dijet, they're all above 1.5 TeV, and that's a rather high mass spectrum. But there's this one search, the trigger level analysis, TLA, that actually serves to go and combat the limitation that we saw from HLT and extend the sensitivity to lower masses. And the way it does that is it recovers some events from TLE, the HLT that would have been lost, so it has this data scouting scheme that does so, and it allows the sensitivity to be increased at lower masses, and that combats this HLT limitation that we saw. And so large R jets also are sensitive to low masses currently, and if you have improvements for large R jets, then that would allow for increased sensitivities for lower masses. So having better performance for triggers would also benefit physics in many aspects. Another example is this 4-jet event, allows for potential for dark matter, and we see this in the di-Higgs searches. So the primary decay channel of the di-Higgs is 4B and 2B, so 2 taus, and the di-Higgs to 4B search uses L4J15 and 2B tags in HLT, but you can see that for 15 GeV at L1, we have the 6J15 and 4J15, that correlates to 65 GeV in the HLT and in offline analyses, and so this serves as a limitation, and so there's room for improvement for triggers for di-Higgs searches. So that motivates all the improvements that we're trying to make for run 3 jet triggers. for the run3 JFEX jet algorithm, for small r JFEX jet, it's reconstructed using a 0.9 by 0.9 sliding window algorithm. And there's a noise threshold of 2 GeV that's required for any J tower. If the J tower fails that noise threshold, then noise cut, then the ET of the J tower is set to 0. And so there's this 0.1 by 0.1 J tower, which is seen in blue here, and it's surrounded by a 0.3 by 0.3 seed that consists of 3 by 3 J towers. And the local maximum seed, the local maximum is a seed with a high CT, and it's determined by scanning all seeds that exist within a range of 5 by 5 J towers and find the seed with the highest ET. And so by definition, the small r jet is defined as a cone of delta r equals 0.4, where delta r is the square root of delta eta squared plus delta phi squared. And it's computed with respect to the local maximum. And the jet ET is the sum of the ET of each tower. For the large jet here, seen in blue, it uses the same exact algorithm as the small r JFEX jets, but with an increased cone size of delta r equals 0.8. And so it's just a difference in delta r. You could see the trigger efficiencies in di-Higgs to 4B Monte Carlo samples for run2 level 1 jets, run3 JFEX jets, and the offline anti-KT reconstruction algorithm running over r equals 0.4 J towers. And both the run3 JFEX algorithm and the anti-KT reconstruction algorithm apply a noise cut of 2 GeV to the J towers. And these plots were just created by having the thresholds for all 3 approaches tuned to have equivalent rates. The differences between these plots lies in the multiplicity of online jets required and also the delta R. So on the left, we require 3 online jets, and at least 1 jet has to have a delta R less than 0.6 of the probe jet. But on the right-hand side, we only have 1 online jet that's required, and there's no delta R requirement. So the new algorithm for these close by jets on the left, where you have multi-jet selected as the online requirement, it actually performs better than the run2 level 1 jets, but the run2 level 1 jets and the new algorithm perform similarly for the online single jet events. So there's a benefit for the multi-jet close by jets as opposed to the one online single jet. For the JFEX MET algorithm, this shows the efficiency of the JFEX MET algorithm versus truth MET in a ZH to mu BB Monte Carlo sample. And the way the JFEX MET is calculated is you take the vector sum of all towers with ET greater than an eta dependent threshold. And so there's this noise cut that ranges from 0 to 5 GeV. And this comparison is between the JFEX MET algorithm in the ZH to mu BB compared to the run2 MET threshold in ZMU events. And the reason why the performance is the same is because this is just a proof of principle plot. So it's using the same exact algorithm as in run2, and it's therefore the same performance. But what we hope to do for JFEX MET algorithm is to achieve better pileup mitigation via this row subtracted MET calculation, in which the average energy from in-time pileup is calculated event by event, and then you subtract all the energy, you subtract the energy from all towers, then sum over all towers with positive energy. Another way to go and improve the jets is to go and utilize jet
what 1 minute, yeah.
Okay, sorry, thanks. Other way is to go and utilize jet calibrations. So the Atlas detectors you could see is not uniform in eta, so the response to jets, this energy response of reconstructed energy over true energy, is also not uniform in eta, as you can see from the variance here. But our goal is to go and remove this eta dependence in the energy response to improve the jet resolution via calibration. And so for the trigger, the goal is to go and select all jets that have a true PT above X. And if the response R is uniform everywhere, then that selection would be X times R. But the problem is when the response is dependent on eta, a cut at a single value of X times R will select truth jets at different PT across eta. And so that's why calibration is being derived to go and make calibrated JFX jets have that flat response in ADA. So that's another way to go and improve the jets and jet triggers. So in summary, the Atlas upgrades for run 3 are in full swing. Performance studies have shown improvements for JFX jets over run 2 level 1 jets, specifically for the close by multi-jets, and further studies to help pilot mitigation, the improvements in JFX met, and to help performance with better jets, cows, and photons are underway. Thank you.
Super, thanks so much, Eleanor. There are questions for Eleanor.
Maybe I have probably a very stupid question, but I would expect that for jets, the critical detector is style cal. Is it true? Or not? Or it is liquid argon calorimeter?
Sorry, for multi-jets?
For whatever jet.
Oh, I think it's I mean, I know that for L1 Calo, there's definite improvements for jets, and the specialty of like the JFX jets actually lies in the subleading jets. So that's kind of why you see the multi-jets have better improvements than the single jets at this point, because the specialty really is in the subleading jets here. But also there should be improvements for single jets. So I think there should definitely be power in the L1 Calo trigger for all these improvements.
Okay.
Other questions for Eleanor? Okay, we thank you again.
Thank you.
Yeah, our next speaker is also from Atlas. It'll be the Atlas Muon trigger design and performance. And Yu Nakahama from Nagayo University will present.
Sorry, actually it should be real-time forward tagging.
I beg your pardon?
I think you skipped the Carlo.
I skipped a presentation. Excuse, I beg your pardon. Sorry, Carlo.
No problem.
Yeah, so let's rather do, Carlo, Carlo Varni, from INF in Genova, and he will present real-time flavor tagging selection in Atlas.
Yes.
Thanks very much. Apologies for that.
Oh, no problem. Yeah, I should be sharing now my slides.
Perfect. Yeah, looks good.
So this is going to be a very quick introduction and description about real-time flavor tagging selection in Atlas. So I would first quickly introduce once again flavor tagging, but this time use a trigger level and the improvements that have happened during run 2. So I will start with the ingredients that actually goes into the algorithms, which are tracking jet and flavor tagging. Then I would quickly go through recommendation for analysis, and then a quick description of triggers that I use also in heavy ion data. Flavor tagging, as I said, aims to identify the origin of a jet. So if it is a light jet, to be B jet or C jet, and obviously it can be used also at trigger level, and triggers that use it are obviously called B jet triggers. However, they actually retrieve information from different areas, from different groups actually, and they put that together in a coherent way in order to identify the origin of the jet. And obviously you can see there are many analyses that actually rely on B jet triggers, simply because the physics signatures have B jets in the final state, and some of which actually only have jets in the final state. So B jet triggers are the only way for them to achieve a high enough sensitivity for their purposes. So starting with the ingredients, the most important one and computer expensive one is tracking. And in order to understand how tracking works at trigger level, then there is a quick overview of the super ROI approach, as it is usually called inside Atlas. So the point is that from level 1, you do have different ROIs, but in high pile-up situations, when these ROIs obviously overlap, so it's not a smart idea to process this ROI one by one. because you will end up analyzing the same part of a detector more than once. So it's a waste of time, waste of CPU, and also has impacts on performance. I mean, you may duplicate tracks, which will then bring to a bias in the primary vertex coordinate, which is extremely important for favor tagging. So the idea here is to define this so-called super ROI, in which you basically are merging all this ROI into one single composite ROI in such a way you can perform tracking in this ROI only once, so you're actually avoiding all the problems that the previous approach would produce. So said so, then tracking is actually performed in two different stages. The first stage performs a fast track reconstruction using this super ROI. So this is an ROI which is extremely narrow in eta and phi, but has no constraint on the z. And it is used in order to reconstruct tracks for finding the primary vertex position. So you don't need so much precision on the tracks, but it is enough for having a precise measurement of the primary vertex position. After that, then you move to the second stage. This is called the precision tracking. And in this case, you are doing regional trackings, meaning that you are defining larger ROI around the jet axis, and you're adding the primary vertex constraint of this ROI. And this basically is why you can actually afford to define larger ROIs. The computational effort from tracking is quite huge, but the primary vertex constraint is quite strong one. So by doing so, you're actually able to resolve the combinatorics in a reasonable time and with reasonable CPU constraints, of course. And here you can see a few performance plots. You can see that on the top left, for instance, the override tracking efficiency is quite stable. However, the vertex tracking is less bit efficient than the precision tracking, for instance. So you have 98%, which is quite reasonable and enough for the identification of a primary vertex. And you can also see the resolution of the impact parameters, D0 and Z0 as a function of eta and also of PT. And you see that that is quite good. So this was one ingredient. When you actually have the jet ingredient, jet reconstruction and calibration. And the main change in run 2 was the introduction of a new way of calibrating jets, the so-called global sequential calibration, which was already mentioned earlier today, which use information from calorimeters and tracking. Actually, it comes in two different forms. One using only calorimeter information, and the other one using both calorimeter and tracking. The effect of this calibration is actually on the bottom right plot. You can see that the green curve is basically the jet without the GSC calibration. You can see that the turn-on is quite slow, but then if you keep adding information, then the curve goes steeper and steeper. So you move from adding calorimeter only information, that's the red curve, and then you go to the calorimeter plus tracking information. However, there is a problem. Tracking is expensive in CPU and time. So you can't afford to do it for all the jets. However, B jets are quite peculiar because they do need tracking anyway for flavor tagging. So that's why they are the only signature in run 2 at least, but can use both calorimeter and tracking information, and thus you have this huge improvement in terms of turn-ons of your triggers, and that's extremely promising. And then the final ingredient is flavor tagging itself. So the main point here that now in run 2, we've moved to use the same algorithm that I use offline, which was part of a major campaign of synchronization between the trigger environment and the offline environment. So now, instead of using, like in run 1, only specific taggers for doing flavor tagging, we are now using exactly the same algorithm used at offline level. For run 2, the recommended tagger was MV2, which was a BDT-based tagger. However, of course, there are several algorithms which I've already discussed in another presentation, so we'll not go further in details about the specific algorithm themselves. Another improvement in run 2 was actually obtained by changing the training sample of the algorithms. Usually, in the past, training sample was only composed from a TT-bar sample. And you can see from the bottom right plot that TT-bar is limited in statistics at IPT. So the higher you go in PT, the less statistics you have, and which means basically that the algorithm is not trained to distinguish properly between light jets or B jets, for instance, simply because there is not enough statistic for the algorithm to learn that. And this has been, let's say, recovered by simply changing the training algorithm and adding a mixture of both TT-bar and Z prime. So you can see that the Z prime, which is the red curve, actually adds a lot of statistic at high PT. And this way, what you end up with is improved performances of your taggers at high PT with almost unchanged performances at low PT. So this was extremely good. So you can see here that what I've told you so far basically translates in performance. So on the top left, for instance, you can see that during the years we have upgraded our performances. So you move from, for instance, 2015, in which we were using still the round 1 configuration. So the blue curve, we moved to MV2C10 trigger in 2017, which is the green. So you can see that we are getting closer and closer to the offline performance, which is the dotted purple line. And you can also see from top right that the performances of our taggers are extremely stable as a function of a pileup. And on the bottom also the effect of using an hybrid tuning, which was commissioned and used in 2018. This is for high PT, so you have to compare the red one, which is the hybrid curve, to the blue curve, which is the MV2C10, the default one. Then, of course, you have flavor tagging and you have BJ triggers, and obviously analysis, but relying on these triggers must apply scale factors in order to take into account for differences between data and Monte Carlo, and we do provide them. They are purchased scale factors, so you basically have to only make a geometrical matching between online jet and offline jet and see what taggers was used at online level, at offline level, and with what working point. And with this information, basically, you simply retrieve the correct scale factors that you have to apply to your jet, and that's basically done. And you can see from the bottom plots, for instance, on the right one, that the scale factors are compatible with one, so this is extremely good. And then
2 minutes, Carlos.
Oh, yes. Before going to the conclusion, then a little quick discussion about what happens in heavy ion collision data, because in here we are actually using BJ triggers. However, these are special triggers because obviously with all the activities that's happening in this kind of collision, you can simply use usual BJ triggers. The rate would be too high, would be too CPU expensive, especially from the tracking point of view. So in order to avoid this, we do have these muon jet triggers, which are basically triggers that require a geometrical match between a geometrically matched jet with a muon. So basically, you are only selecting jets which have within them a muon. In this way, you are basically able to provide a BJet enriched data, which are also used for calibration purposes, but basically are the only way for selecting events with BJets in this kind of collisions with heavy ions. You can see on the bottom some Turner curves of some of these triggers. So this is for frontal collisions, for instance. Then, okay, going to the conclusion that I gave you a quick overview of BJ triggers during run 2, and the focus was on the improvement that enhanced performance during run 2, which basically happened both in flavor tagging algorithms and training, as already mentioned, but there are also a lot of changes from different areas, as well as tracking and jet calibration. Of course, it is quite an extensive area we're talking about. And then quick overview of the budget scale factors, which analysis use, and then what happens when we run on AVION data. And yes, this was everything.
Thank you very much, Carlo. And congratulations for all the run to improvements in many different places. Are there questions for Carlo? I see no raised hands. Obviously, very clear. Thank you very much, Carlo, for your presentation.
You're welcome.
So we stay with Atlas. We have the Atlas Muon trigger design and performance. Yeah, by Yu Nakahama from Nagoya University.
Hello, can you see my slides?
We can, yeah. Good.
Okay, so I'll go ahead. So I'll be presenting the Atlas Muon trigger design and performance. So this is Yu Nakahama from the Nagoya University. Okay, so the outline of this talk is as follows. I'll start with the Atlas Muon trigger design, performance in run 2, and then finally improvements underway for run 3. Okay, so muon triggers at Atlas are essential for studying a variety of physics processes in both standard model measurements and new physics searches. So for instance, in wave physics, the latest Higgs to mu search and electroweak Suji search as examples. And they have been optimized during run 2 in order to provide a high efficiency while keeping the trigger rate low enough. Okay, so moving on to the Atlas Muon spectrometer. So the Atlas Muon spectrometer consists of 4 different subdetectors. So you can see here a side view of a core of muon spectrometer MS. So for the first readout for initial trigger decision, we have resistive plate chambers for barrel and thin gap chambers for end gap. And then for high resolution for precise tracking, we have the monitor drift tubes here and cathode strip chambers. And then toroidal magnets provide average magnitude field of 0.5 Tesla. And then you can see the coordinates here. All right, so moving on to the muon trigger system, which is 2-staged. Okay, so we have the level 1, L1, which use the first and coarse information, so hardware based. So here we require coincidence of hits in RPCs or TGCs. So here we start with the Atlas collision rate at 40 megahertz. And then we estimate the PT by a comparison to expected muon track within an infinite transverse momentum PT. And then we find the regions of interest, so RI, for further processing. And then here the latency is 2.5 microsecond. And then the output rate in total in a peak is 100 kilohertz at the Lebanon system, as you might have had already in the several Atlas trigger talks. And then high-level trigger, HLT, is software-based, which reduces the data amount required to be transferred or processed to our permanent storage with an average output rate of 1 kilohertz. So here we start with ROI defined at level 1, and then we do have a first reconstruction step followed by a precision reconstruction in the limited 8 and 5 regions. And then here the latency in average is 0.2 seconds. All right, so moving on to the each system. So I start with the Lebanon muon barrel trigger. So indeed, you could also see the talk, slides for details of the RPC and the Electron Muon trigger, barrier trigger. So here, RPC coincidence requirement depends on a high or lower PT. So here like that, which provide a 6 PT threshold in a total. And then there are a few upgrades in round 2. So for instance, additional chambers in the support structures increase the acceptance by 4%. So here, this plot shows the Electron Muon barrier trigger efficiency as a function of offline muon ether. So here, the yellow is before improvement, and then the after is colored in green. So for this specific additional region, so here you can see the improvement. So which is very good. So moving on to the end cap, Electron end cap trigger. Indeed, after this talk, we'll hear the interesting talk on this topic for the details by the Jupiter miner. So I can go very quickly here. So Electron muon rates in the third region were polluted by the low PT charged particles, so protons from outside of PT like this. And then indeed, the several upgrades were done in round 2. So here, coincidences with inner detectors are used to clean up these particles, which is a key here. So indeed, with the inner muon chambers placed before the toroid magnet in a coincidence, so here we can reduce the rate by 60% for our typical level 1 muon threshold around PT above 20 GeV. So here, this plot shows the rate as a function of the ether. So you can see the rate reduction before and after this upgrade compared to the green one. All right, and then further improvement with the extended value region of the tile calorimeter here was done. So here indeed the 20% rate reduction was achieved for this corresponding eta region with just efficiency loss below 1%. So very good. All right, so moving on to HLT. So here I would explain the default sequence. So we start with ROI provided by level 1 as said, and then we have the first MS standalone reconstruction where we measure PT by a lookup table. And then first track reconstruction follows in ID within ROI. And then we do have a combined fit of ID and MS tracks like this. And then we go with the high resolution reconstruction, which is offline-like. And then finally, we do have the option of isolation. Indeed, this is crucial for many physics analysis in Atlas because we can lower muon PT threshold and while keeping the reasonable rate. Okay, so moving on to the several improvements at HLT during round 2. So first, we tightened the isolation requirement in order to mitigate efficiency loss observed in a 2017 high pileup condition. So basically, the principle is that around the muon candidate, we define a PT-dependent isolation like in orange here, and the fractional cut is applied on a track PT sum in a cone. So indeed, we can distinguish the actual muon and also the other tracks. So indeed, by tightening such isolation requirement, we could keep the efficiency even at the high pileup around 80. So from 91 to 97%. So this is good. And then in the other improvement, CSC hits here were added in a first reconstruction to improve PT resolution. So here, this plot shows the PT basically resolution in the first muon algorithm as a function of PT, offline PT, and then you can see the improvement from red to blue points. All right, so moving on to the menu on page 10. So in the muon triggers, we do have the various combinations in the selections. So single muon, merge muon, muon plus something like lepton, jets, or photon. And indeed, the dimuon selections for the B physics analysis, like the dimuon invariant mass cut and the distance in R. And we also have specialized triggers for specific analysis, for instance, for the long-lived particles, such as late muon triggers and MS-only triggers. And then here, this plot shows the list of representative amperescale muon triggers. Maybe I can just highlight the main one. So 1 muon with PT threshold above 26 GeV at ICHEP and 20 GeV at level 1 with isolation. So here, indeed, we assign the almost 200 hertz here at ICHEP, and then level 1 at level 1 16 kilohertz. And then
2 minutes.
Yes, perfect, indeed. Okay, so now moving on to the trigger efficiencies. So trigger efficiency is measured using the dimuon events using the tag and probe method. And indeed, we see the excellent performance. For instance, at HLT, relative efficiency to level 1 is almost 100%. And we see the sharp turn on in PT for HLT. So these plots show the efficiency for barrier and end cap respectively. For HLT here, level 1, and also the HLT relative to level 1. And indeed, the efficiency losses are mainly coming from level 1 due to the heat efficiency and the geometry coverage. And then indeed, we see the higher efficiency in end gap than in barrier. Okay, then outlook a bit. So indeed, for level 1, we exploit the new detectors available for round 3. Indeed, you can hear the next talk for the very details. And then for HLT, we introduced the multi-threading technology to HLT software along with offline. Okay, then I reached my summary here on page 13. So muon triggers are essential to fulfill the Atlas physics program. So we had successful operations during round 2. Indeed, several upgrades and improvements were performed to handle round 2 challenges. And then which led to excellent performance during round 2. Indeed, the upgrade of the muon trigger system is underway for the coming round 3 period, both at level 1 and HLT. So thank you very much for your attention.
Thank you very much, Yu, for your presentation. Do we have questions for you? It's really an excellent overview of run 2, yeah. Jiri.
Maybe, yeah, just the question, by multi-trading, you mean this multi-trading Athena that was discussed yesterday?
Yeah, exactly. And over all the signatures in Atlas trigger.
Oh, okay. So will you profit also for the, you mentioned run 3, you are definitely also thinking about run 4. Will you profit for muon triggers also from the higher granularity of in a tracker, for example?
Yeah, I mean, we haven't done the detailed study yet, but most probably yes. Indeed, our aim is really to first, operate the multi-threading part, and then we can start developing the HLT muon part later. Yeah.
Okay, thank you.
Thanks, Jiri. So I guess Yunpi also should be ready for these questions. Yeah, he's our next speaker. Thank you very much, Yu. So we stay with Atlas Muon trigger for the next speaker. And we'll have Yunpi Maeda, and he will present the Atlas Level 1 NCAP Muon trigger for Run 3 from Kobe University, Japan.
Yeah. Hello, can you see my slide?
Yes, we can. Thank you.
Oh, okay, thank you. So hello. So my name is Junpei Maeda. So I'd like to present about the Atlas Level 1 NCAP Muon trigger for Run 3 on behalf of the Atlas collaboration. So first of all, so let me remind you the scheme of the Atlas Level 1 NCAP Muon trigger. As also mentioned in the previous talks by you, the Level 1 NCAP Muon trigger is a hardware-based trigger and is based on the thin gap chambers, TGC, on the muon big coil, which covers eta from 1.05 to 2.4. In front of the big coil, there is a toroidal magnet to bend muons, and we can measure the transverse momentum by the position deviation from the straight line using predefined lookup tables. The right plot shows the trigger efficiency for single muon of various thresholds as a function of transverse momentum in 2018. The primary single muon trigger in Run 2 was 20 GeV threshold called L1mu20. And the plateau efficiency achieved approximately 90% with stable operation. On the other hand, the NCAP trigger has an issue due to fake triggers. The slow positive charge particle, likely protons, are generated at the beam pipe or so, and are bent by the toroidal magnetic field, then pass through of the big coil. If we use only information from the TGC big coil, we cannot distinguish between the fakes and real muons, like blue and brown arrows. In order to use such fake triggers, we introduced coincidences with TGC inner stations called EI and FI, and also outermost cells of the tile calorimeter, so in Run 2. Since those detectors are located in front of the toroid magnet, the coincidence can remove fake triggers. So the right two plots show event count of L1mu20 as a function of eta, and the impact of such an inner coincidence of the rate point of view. For top one, the green area is removed by TGC EI FI coincidence, and the specific region from eta from 1.0 to 1.3 can be reduced by the coincidence with the tile calorimeter, as shown in the bottom plot. These events are almost fakes, so we can reduce the trigger rate significantly while we miss only 1% efficiency due to the cell boundaries of the calorimeter. Okay, so let's start the talk about Run 3. The main motivation for these upgrades are to detect fake triggers much more. The inner coincidence introduced in Run 2 was successful to reduce fake triggers, but still 50% of the trigger candidate is fake. The right plot is the trigger candidate as a function of eta, as similar as previous slide, and the color stack histogram is remaining candidate. And actually the blue is the fake, still fake. And moreover, so you can see the red area, which is lower PT muons below the defined threshold. So we will reduce such a low PT contaminations by improving the momentum resolution. So anyway, so the improvements, especially rate reduction of the level 1 muon trigger system are very important for various physics analyses, since our total budget of the level 1 rate is 100 kilohertz. So my presentation reports development of the new trigger processor called sector logic for Run 3 and the trigger algorithm with expected performances. Okay, so there are new muon detectors at the inner station from Atlas Run 3. The small foil, which had TGC FI chambers, will be replaced by the new small foil. So there are many talks in this session, and which consists of small strip TGC and micromegas. Moreover, the new RPC detectors will be added to the boundary region between the barrel and end cap in the 13 Azumi shallow angle region. So the new small foil coverage is much better than previous TGC FI detector. So the eta coverage which enables the inner coincidence can be extended from 1.8 to 2.4. Moreover, the precise measurement of the position and direction of muon segments on the new small foil gives us the improved PT resolution. So the inner coincidence between TGC big foil and the new detectors will more reduce the fake triggers and improve the PT resolution. But the new electronics is needed to handle all information from many detectors. So TGC, EI, new small foil, RPC, and tile calorimeter. So since 2014, so we have developed the trigger processor, so called sector logic, and those has been replaced during the current long shutdown period. Okay, so this photos show the new sector logic, so developed for the LAN 3 and so this equips FPGA and many optical transceivers, Ethernet port on the 9U VME board. So in this time, so we adapted the Xilinx Kintex 7 FPGA so for the trigger algorithm. This has enough multi-gigabit transceivers called GTX for inputs and outputs, and has 20 times larger resources with respect to the previous sector logic. So GTX will be used to receive the new detectors for the inner coincidences and to send muon candidates to the muon CTP interface. The bottom so 14 G-Link receivers are also equipped for signals from the TGC big foil and the tile calorimeter. So on the sector logic, so there is one Ethernet port for trigger data readout by software-based readout driver, which is also newly developed for this time. So for LAN 3, so 72 sector logic ports has been installed for the full Atlas Level 1 end-cap muon trigger system, and all new hardware have been produced and installed to the Atlas counting room by February this year. So the integration is completed before the Ceylon lockdown, and the commissioning is ongoing remotely. Okay, so from this page, so I saw some expected performance by the new system. And the first improvement is the charge identification. The end cap trigger system will have a capability of identifying muon charges. The charge information will provide benefits for several applications in the level 1 trigger. For example, the topological trigger system called L1 topo select low PT dimuons for epsilon decays by lower trigger rate with requiring opposite charges of 2 muons. So such a new identification so extends new possibilities of the Atlas flavor physics program. So the logic is based on our knowledge of bent direction by muon charge. And the center, so this figure so is a visualized example of the lookup table in the sector logic. So the estimated PT is decreasing from center to the top or bottom side, and the symmetric structure comes from opposite charges of each other. So just a white line so distinguish the charge between the positive and negative. So the light plots show the accuracy of the charge identification as a function of truth PT by simulation study. The blue point is the efficiency of lowest PT threshold with correctly identified charge, comparing the efficiency without charge identification by red. We found 98% accuracy up to 30 GeV is achieved, and the accuracy is of course degenerated with higher PT. But high PT muons are anyway taken by a single muon trigger, primary muon trigger. Okay, so we can also increase information from the sector logic to the later stage by high-speed optical links. In LAN 3, the number of candidates per sector will be changed from 2 to 4. So this is advantages for example, tau 2 3 mu lepton flavor biosystem physics, And also the threshold level can be increased from 6 to 15. So as comparing two plots, the smaller step of threshold level can improve the PT resolution taken by a certain threshold. Then the invariant mass resolution calculated in L1 topo can be also improved using such a fine granularity of the threshold. Okay, so finally, I'll show the impact of new small foil coincidence. There are several baseline ideas, but basically, we use the position and angle correlations between those detectors. The fine new small foil granularity will improve the PT resolution too. By this coincidence, the low PT candidates can be detected effectively. So by the left plot, bottom left plot, although the impact of the efficiency loss is only a few percent by new small foil segment finding efficiency. This right figure is the number of candidates taken by level 1 muon trigger. So yellow area can be reduced by new small foil coincidence. We can reduce the trigger rate of threshold for run to primary trigger level by about 45% by new small foil. Okay, so let me summarize. In order to cope with high event rate in Atlas Run 3, we need the upgrade of the Atlas level 1 end-cap muon trigger. Since Atlas will install new muon detectors such as the small foil for Run 3, the trigger system will take full advantage of the improved coverage and resolution. We have developed the new electronics called sector logic to handle information from the new detectors. Hardware installation has been completed before February this year. Baseline ideas of the trigger algorithm are being tested using simulations, and the new trigger logic shows a good performance. The output information for trigger decision are also increased by the new electronics, and we will have many possibilities to develop the dedicated trigger change using muon charts, improve the PT resolutions, and so on. So the single muon trigger rate of a threshold with a plateau at 20 GB for Run 3 is estimated using real data in Run 2. We expected 45% rate reduction with respect to Run 2 rate. The remaining bandwidths can present opportunities by other trigger items to extend the Atlas physics program for Run 3. Thank you very much.
Yeah, thank you very much. Excellent, excellent talk. Very clear. Are there questions?
Maybe I would have a question. If for the muon trigger, especially the end-cap muon trigger, if you would profit from the stronger toroidal magnetic field.
Oh, yeah. If we can make such a strong magnetic field, so it's much better for the
okay. So it would be much better. Okay. If it would be stronger.
I don't think such. It's no such.
Yeah. And the second question, it was not mentioned during the previous presentations that there will be also this high granularity timing detector in the end-cap part of Atlas for the high lume runs. So for Run 4.
Okay, so maybe it's helpful, but so actually, so for the high luminosity LHC, so the TGC big foil can read out data by the full granularity. So then not course direction. Then so we actually the expected trigger rate is much lower than the current one, and so we don't need to more improvement by the such thing.
Okay.
But of course it's nice. Maybe it's a nice idea. Yeah. Thank you.
Other questions for Jean-Pierre? Jean-Pierre, will these sector logic boards remain for Run 4, or is it just something for Run 3?
This is just used for Run 3. So Run 4, so we replace everything, all electronics. Yeah.
Okay. Thank you. Okay, we thank our speaker again.
Yes, thank you very much.
Yeah. So now we shift experiments, and we'll have Oscar Hartbricht from University of Hawaii, and he's going to present the status and performance of the Bell 2 DAC system. Oscar actually gave a presentation 2 days ago on another detector and a subdetector within Bell. So this is his second ICHEP presentation.
All right, thank you very much. So I will talk about the Bell2 DAQ system, as you said already. But of course, I need to start with Bell2 and the Super CAC-B machine. We finally are very happy to have reclaimed the luminosity, instantaneous luminosity world record back to Japan, back to KK, thanks to the excellent operation of the Super CAC-B machine people. We actually surpassed the world record by about 20% a few days after even. So this is quite great. We managed to accumulate about 74 inverse femtobarn in this combined runs of 2019 and 2020. But of course, our goal is to go much, much higher than that. We plan for about 50 inverse autobarns in the next 10 years. And this means even though we just got the world record, we will need to increase the instantaneous luminosity by about a factor of 30. I will not go through the whole detector here, how Bell2 is actually built up, but maybe one thing you can keep in mind for now is that the acronym for our pixel detector is PXD, because that will be interesting again in 2 or 3 slides. So the DAQ system is built out of many different components. We have a trigger and timing distribution, of course. We have a data readout, some event building, and some slow control. I will discuss all of them in this talk. But we also have a high-level trigger farm that was discussed in a talk just about an hour ago by Marcus. You can download the slides and click the link, then you will go to his talk. We also have some data storage and transfer services that were discussed by Matt in an earlier talk, I believe, in a different session. This talk is also linked here. So if you're interested in that, please check these out or check the recordings. So the trigger and timing distribution system is completely custom electronics that were built for Bell2 or were developed for Bell2 as these FTSW switches. That is an acronym for fast timing switch. What they do is they distribute the global clock, trigger information, injection signals, but even JTAG services from the master FTSW, which is shown on this diagram here on the left side, in a sort of tree-like fashion to all of the front ends, etc. And there's also, it's a bidirectional communication. Also the other way around, it will gather from connected front ends or whatever is connected to the system. It can gather readout statuses and busy statuses so that, for example, you can inhibit triggers if one of the front ends is temporarily busy or something like this. This is done, of course, as a cascaded tree. So we have many layers of these, up to 4 layers deep, up to 4 levels deep of these FTSW boards. They are connected between them via Cat7 cables, for example, up to 30 meters. You can also put multi-mode fibers, so all sorts of different connection modes are available. I think the longest that we have is 4 levels deep, has several 30-meter Cat7 lines and at least 120-meter fiber line for almost a microsecond. I think 620 nanoseconds latency total. Still, the clock distribution jitter is less or about 20-25 picoseconds, which is not really world-class, but it's better than anything where we would actually need it. We don't have any super fast timing detectors that rely on a clock distribution better than that. We could easily improve this if we would just not route the clock through the FPGAs, if that was needed. In terms of performance, especially over the past month, it was fairly stable. We had some operational issues with instabilities, but most of them could be traced to individual front-end hardware failures that were investigated and then will be fixed over the summer while we are shut down. And then hopefully this will be all done by October. In terms of data transfer, of course, that is maybe the most important part of a DAQ system. Told you already, keep this PXD acronym in mind because the pixel has an entirely separate readout. Marcus had more discussions on this in his talk, so I will not go through the details. I will just explain about the other subdetectors where we have a sort of unified system from the moment where the data leaves the front end. So each subdetector is responsible for their own front end electronics, but then they will send their data to these copper boards. I will explain what they do. Copper boards forward the data to these readout PCs, which then forward to the event builder and into the high-level trigger system and all these things. So these copper boards, copper again is an acronym for Common Pipeline Platform for Electronics Readout. These are custom VME, full-size VME modules originally designed for basically the DAQ upgrade of Bell 1. we still use them in Bell 2 in a slightly modified form, where we have these HSLB boards mounted to them, which are receivers for one fiber each. And these fibers are running a custom Bell 2 link protocol, which can run up to 2.5 gigabit roughly per second. In practice, no single fiber from a front end ever carries more than about 300 megabit. So we are never saturating the fiber capacity at all. These copper boards also receive the trigger and clock information from the centralized TTD system. And then they have an integrated Atom processor, which is Linux-based, and just reads the data from these fibers, packages them into an Ethernet packet, and sends it out via this gigabit Ethernet port. So in this way, the copper board is effectively our adapter from our custom hardware and custom fiber and custom protocols to standard TCP Ethernet packets. So everything downstream from the copper boards is all commercial off-the-shelf hardware, while the copper board itself is a custom board. We have about 200 coppers in action in Bell 2. They serve to about 650 Bell 2 links, so that is a large number of fibers. And then this data is packaged, I explained this already, and sent to these readout PCs. The readout PCs are simple commercial servers, just off-the-shelf servers. They receive this gigabit data from the coppers. They bundle the data from up to 9 coppers in total, calculate some more checksums, etc., but then just forward them to the event builder again via gigabit Ethernet. They also work as the network boot host for the coppers, because the coppers are actually diskless. So that is, and we have about 45 of these readout PCs in the whole thing. So just 200 coppers and VME crates plus 45 readout PCs, that is about 10 racks or so full of readout hardware that we need for this right now. Let's talk about slow control a little bit. Slow control is everything that is not event-based, all the process variables that are not event-based. So that is run control, detector status, environmental parameters, machine parameters, all of these things. So we have a rather hybrid system to distribute such process variables. We use NSM, which again is our own homebrew version of distributing variables and sharing memory between hosts, and EPICs, which I guess everybody uses. And we distribute tens of thousands of process variables throughout the network. Now the thing is, of course, as I guess every slow control system, we have hundreds of nodes and they are quite inhomogeneous. So many nodes are not controlled by the DAQ group at all. Not all of them are on the same network. So it's a very heterogeneous system. That gave us a lot of trouble, especially in the first part of our running. But then we started introducing continuous integration for the software and almost continuous deployment system for this whole slow control software, this whole framework. We built a largely automated build system that automatically builds new software releases for all target distributions in Docker containers. So we try to use more open source industry standard tools to automate these things. We have a central software distribution in our own localized CTMFS network that is inside the DAQ network. And that has increased the stability and the reliability and has decreased version share across different hosts considerably. We still have to work a little bit on integrating all of the non-DAQ hosts, so all the hosts that are sub-detector specific that the DAQ group doesn't really have access to, into the centralized deployments, but we're slowly getting there and we're making some progress over the summer. Monitoring has been another great step forward, especially over the past year or so. So we finally use Zabbix, which is an open source tool to monitor almost all individual hosts, which means we monitor that the most crucial processes are running, that the software versions are correct, and also like network traffic, disk I/O, memory consumption, all of these things. But then in addition, we can also monitor all the machines and their processes and their log outputs by setting up an Elasticstack system inside our DAQ network. So Elasticstack is kind of the combination of Elasticsearch, which is a very flexible database and search engine, Logstash, which is a very powerful ingestion pipeline. So you can just send logs to Logstash, and Logstash will parse and categorize them and send these entries to Elasticsearch and Kibana, which is an extremely powerful web-based visualization system where you can easily display and visualize all of these different log entries and errors and all these things that you just feed into the Elasticsearch database. This is extremely scalable. It's all open source. There's a huge community using it. So whenever we have a problem with this, we can find somebody who has had similar problems So this is just great using this. We had good experience predefining dashboards for subdetector experts, for DAQ experts, for the run coordinators, etc. So everybody can get their own projection of this data set to see what they need at a given moment in time. We were able to integrate automated alarm messages that automatically alert experts or control room shifters via Rocket Chat if something seems amiss. So this works very great. So we can sometimes diagnose problems before the shifters would otherwise see them. All of this, I think, has been a significant step in improving our overall reliability and having this system. So it's a great success in my opinion. So yeah, how did the DAQ operation actually look like in 2020? We were running throughout most of the whole pandemic time until early July, when we were planned to shut down anyway. If you want to know more details how we actually pulled this off, Matsuoka-san gave a very nice talk that was about this quite a bit. So you can click this also here at ICHEP, you can find his talk. Our overall data taking efficiency, that means luminosity delivered to the luminosity actually recorded, was about 85%. And these missing 15% are roughly equal parts issues requiring expert intervention. For example, a whole sector of our muon system went offline for a while and nobody knew what was going on. So we even had to do an emergency access, or the experts had to do emergency access and fix things for several hours. Well, that cost us about, I mean, that was one of the kinds of incidents that cost us about 5% in total. 5% more are lost due to issues that can simply be fixed by restarting the run. So in this case, you usually don't even have to call an expert. You just restart the run and well, then things work. Of course, this is logged and then people can look at it afterwards to hope it doesn't happen again. Then we lose about 5% due to our injection trigger veto. That is just that since we are running an online continuous injection scheme in the accelerator, every time a new bunch is injected, it will be quite noisy for a while. So for a short time, every time this bunch comes around, it is masked off, which loses us about 5% of the data because the backgrounds are still fairly high. But still, compared to 2019, especially, we had many days in 2020 without any significant loss due to DAQ and detector troubles. So this is a huge step forward, even though 85% is clearly not where we want to end up, right? We need to be way above 95% ultimately, but we're slowly getting there. Also, maybe just to mention this, even though we're only running at about 3% of our design luminosity right now, we run at about 20% of design trigger rate because we can afford it, right? We can just keep our trigger lines wide open and exercise the system a little bit. So eventually we will have to tighten up the trigger lines, but for now we can afford it and we just run at full trigger bandwidth.
Let's go 1 minute. Yeah.
Okay, good. We have a DAQ upgrade project. The copper system explained this is quite old and will be difficult to maintain over the lifetime of Bell 2. It's old Atom CPUs. It's almost impossible to find replacement parts, etc. The data rate should be fine the way it is, but it will not, I mean, it will be quite marginal. So there must be an upgrade. There was a selection process, but we decided to go with the PCIe 40 boards that Alice and LHCb will also use. We will need only 19 of these cards to replace all of our 10 racks of current readout hardware, and then they will be in dedicated hosts that will just have a 10 gigabit output to the event builder through new switches. So going from 10 racks to maybe half a rack in total after all. We hope to roll this out already by September to use this in the physics run that is starting in October. We have test benches for this at KK. We have it in Hawaii. So far, the development of this was almost not influenced or hindered by COVID travel restrictions. But I fear we might start feeling this now for integration tests, because there we might really suffer from not being able to travel as much as we would want to for this. We will see how this goes. Anyway, to summarize, I think 2020 was a good year for Bell 2 and for the Bell 2 DAQ system. We made quite some progress in stability overall. We have this huge undertaking of this DAQ upgrade in front of us. Developments are way underway. Full integration tests are starting now, and we will see how this goes. But we still are quite confident that we can do full conversion of 2 of our subdetectors already to this new upgrade infrastructure already for the next beam period in October. That's all. Thanks.
Thanks very much. Questions for Oscar? Yeah.
Okay. Hi, thank you very much for a nice presentation and also for the list of all different, let's say, open softwares. This is always useful to see. Also, thanks for changing the background as you promised to more Hawaii style. And,
yeah, a little bit more Hawaii style.
Yeah, it's good. So I have one question. How you are actually measuring the temperature and especially relative humidity at Bell detector? Because you mentioned also this data flow control.
Okay, so each system, I mean, okay, I mean, every system can do whatever they want and they can broadcast whatever they want. I can tell you for the top system, of course, we have temperature sensors all over our front ends. Each front end board has at least 5 temperature sensors, and we're just broadcasting the values of those. But it's a sub-detector specific thing. I don't think we have, I think each sub-detector measures what they deem measurable, and then everybody can use this data.
Yeah, okay.
I know we also have relative humidity measurement inside of the top front ends, but I don't know what kind of sensor that is.
Yeah, because I'm especially interested in these relative humidity sensors because there are almost no relative humidity sensors that would be radiation hard. So I'm just curious what you are using.
Okay, so for the top front end, I can tell you radiation hardness is not a big problem. I mean, we get some neutrons, but it's not tough. I really don't know what the more inner detectors are doing, but I can try to find out and send you an email after.
Okay, it will be probably some optical fibers, and there are some changes in the spectrum. This is what is using at least in Atlas, I think. Whatever, that's fine.
I have no idea, to be honest.
Okay.
I think pose it on the Mattermost, Jury, because at CMS we use those optical fibers, but also other sensors. So yeah, one of the experts I'm sure can answer. Yeah, I also want to thank you for sharing all that monitoring infrastructure. We use some of these Elasticsearch monitoring web tool based things in CMS as well, and they're extremely flexible. Thanks. Okay, so now we're going to get deeper into data quality monitoring. We'll have a talk from CMS, from Andres.
Oh, can you hear me?
And yeah, from Vilnius University. So he will present the data quality monitoring software for the whole CMS experiment. He'll give us an overview, yeah.
Yes, can you see my slides and can you hear me?
We can see your slides. They're not yet full screen.
Yes, they will be. They will be in a second, and you should see me right now on the video. Is that correct?
We see you on the video. Okay, perfect.
Okay, so we are ready to go. So hello, everyone. My name is Andrus. I'm on behalf of the DQM team, and I will be giving you a presentation on the data quality monitoring software systems for the CMS experiment at the LHC. So, CMS data quality monitoring, or DQM for short, is the subgroup within the PPD, or Physics and Performance and Dataset organization, which basically bridges the gap at CMS between the online computing and the offline computing. So the three things that you see outlined on the slide are the main responsibilities of the DQM team. So first of them is the online data quality monitoring, where the goal is to provide live monitoring information for shifters and detector experts so that they can quickly react on the issues that unexpectedly occur while the detector is running and the data is being taken. Second thing is offline data quality monitoring and data certification, or DC for short, where the goal is to distinguish whether the data is good or bad and to determine which data can be later used for the further physics analysis. And the third thing is release validation. Release validation is the process in which we verify whether the new software releases that are being tested are producing correct results and they're working in a predictable way, and whether they can be used for further data taking or not. So the main output of DQM is these histograms, or internally we call them the monitor elements, or MEs for short. And a monitor element is usually a 1D or 2D distribution of some observable value within the CMS detector. So they can be, for example, 2D occupancy maps or efficiency distributions or some other physics distributions, like you can see on the slide on the right side of the slide. You can see a sample of the cluster charge distribution. And all monitor elements that DQM produces, they are accumulated per run, while some of them are also available per lumisection. And up to LS2, we didn't really have good and reliable tools to work with the per lumisection plots, although we are now providing these tools, and more on that, I will cover that in a few minutes. And I know that this can be a little bit different coming from experiment to experiment, so I would like to clarify the terminology that lumisection for CMS is 23 seconds of data taking, and this unit is atomic. So we either take the full lumisection or we discard the full lumisection. And also this unit of time is constant, so we cannot shrink the length of the lumisection or expand it. It's always 23 seconds. And a run is an arbitrary number of lumisections. It can range anywhere from 1 to basically 1,000, or sometimes even more than that. So this is how the DQM system roughly looks like in the context of the rest of the CMS data processing pipeline. Obviously, this is not the full picture. This is more like the zoomed in version to highlight the DQM parts of the system. And within CMS, the data quality monitoring system is a central one, and it's used by all of the subsystems. And the DQM components are highlighted in gray here, so that you can see them. And now I will cover basically every single component one by one. So it all starts, the DQM data is being produced in the DQM framework, which is a part of the main CMSSW, main CMS event processing framework, which is called CMSSW. And the DQM framework within it is responsible for transforming CMS events into the histograms or the monitor elements that I showed before. And the white boxes above, the highlighted DQM boxes in the scheme over here, they all represent data reconstruction. And so first data is being reconstructed, and then it's fed into the DQM system, which with the help of DQM framework produces these monitor elements. The monitoring code itself is produced by the subsystems and subsystem experts. Centrally, at DQM, we provide just framework and tools for them to be able to easily transform CMS event data into monitor elements. Now, the way the DQM processing works in online and in offline is a little bit different. So in the online, DQM code is being executed on dedicated machines that are situated on site of the experiment, which is Point 5 in Cessy in France. And HLT, which is our high-level trigger, provides us with basically 1/10 of the full HLT data that we do DQM processing on, and the rest of the data is sent for offline processing. And after offline processing, then it's the final data that will later be used for physics research. And in the online, each client or each subsystem runs on their own process, which adds flexibility for us to selectively include or exclude subsystems. And also online DQM has a very important role of producing these snapshots of every monitor element of an ongoing run for the system, for the subsystem experts and shifters to be able to see the state of the detector at any given point in time. In the offline code, the DQM code is pretty much the same, very similar, and it's running together, bundled together with the rest of the CMS event processing. It's also running not only with offline reconstruction, but also as part of Monte Carlo simulation or release validation, and it's being executed in a parallel way on thousands of machines and thousands of CPU cores running on dedicated computing sites. And we recently did quite a lot of work modernizing the internal DQM framework, making it more readable and more maintainable. We cleaned up the code a lot. The API for our users didn't change at all. It's more of an internal change, but now after the change, the code is way more maintainable and way more readable. Next up, we have the DQM GUI, which is the central tool for DQM. It's already used directly by our users, and it basically receives the root files containing monitor elements that were produced in the previous processing step, and it provides a web interface for these monitor elements to be visually explored by our users. And the online GUI also has a very important job of accepting snapshots of these monitor elements of an ongoing run to, again, provide the quick and prompt feedback at any given in time for the experts and the shifters. And being a central tool, it also provides a set of APIs for other systems and other services to integrate into and to actually make use of the DQM data. We had this tool, the DQM GUI tool, working for approximately past 10 years basically, and it was if not the most, probably one of the most stable and one of the most reliable tools of the entire DQM software suite. But after 10 years, it obviously starts to show some signs of age. So currently we are working on the new version of the tool, and you can see the screenshot of the new one on the slide. It has never been used for data taking, the new version of it. It's currently being developed. It's already actually fully working and in the final stages of development and integration. It significantly reduces the complexity of the code of the tool itself. It also makes sure that the underlying root files that are containing the monitor elements that we display in the tool are available. The root files are available for any specific and deeper inspection, and this is a very welcome change according to our users. Also, due to the architectural choices that we made when making the tool, the new instance of the tool can be launched in basically a matter of seconds, and that instance will contain full data, which means that the tool can be scaled horizontally to cope with a high demand. And also the deployment is much easier now. It comes bundled. It will come bundled together with the main CMS event processing framework, CMSSW, and checking out the release of CMSSW is pretty easy, and most people at CMS have experience doing that. So deployments will be basically a few bash commands. And also, very importantly, it provides the higher granularity data. So previously, the previous GUI never had support for per lumisection higher granularity data, and the new GUI does have support for per lumisection data, which is not only useful for detector experts to debug their issues, but also useful for the machine learning studies that are ongoing right now. And the result of that might provide some insights about the quality of the data on higher granularity per lumisection basis. Next up, we have the Run registry, which is a web service that aggregates certification information, and it also provides a certain set of APIs that are used to produce this final set of data that is complete and ready to be used for physics analysis. Internally, we call that the golden JSON. And for the past 2 years, we've been hard at work modernizing this tool and essentially providing a new version of it. We upgraded it for maintainability and usability. And also along the way, we added new features like support for flagging lumisections of runs. And it's been already used for production workloads, and it's still being worked on, although it's in the very final stages of being commissioned. Next up, we have the HDQM, or historic DQM, which is a tool that allows to monitor DQM trends or DQM quantities over long periods of time. So it extracts a single value of a DQM monitor element, DQM histogram, CME of a histogram, or some other property, and it plots a bunch of these values as a function of a run number, or as a function of time, we can say. And this tool is very useful when debugging these slow cooking issues where the performance of certain components of the detector degrades slowly over time. Then talking about the users of DQM, they are highlighted here on the slide. So firstly, we have the shifter that is constantly monitoring the DQM monitor elements coming out. And in case they observe any issues, they immediately contact respective subsystem experts to dig deeper and to eliminate the issue. Then we have the release validators, which are monitoring DQM monitor elements and comparing them to the old ones to make sure that the new versions of the software releases are behaving correctly and producing correct results. And also we have shifters and data certification experts using our tools to distinguish whether the data is good or bad, and which data can further be used for the physics analysis. And currently, this process is done on per run basis mostly, although our ongoing machine learning studies might simplify their work a little bit and provide data certification information on per lumisection run value. Also, detector experts are using our tools, all variety of combinations of our tools to debug their issues with their respective subdetectors. Now, talking about some numbers.
1 minute, and Andres, 1 minute.
Okay. Yep. Now, talking about the numbers of the CMS DQM. So we estimate that all DQM per run data adds up to 100 terabytes of DQM root files containing histograms. And per lumisection data adds up to roughly 100 terabytes per year, which is already an order of magnitude increase. And in the offline DQM GUI, we provide some 55 billion distinct monitor elements for our users, and they were produced after processing of roughly 1 billion different events by the DQM framework. And in the online, we have to cope with a stream of 1 megabyte at 100 hertz, which is essentially 100 megabytes per second worth of data to be processed in the online mode. In terms of the future plans, we are anticipating to finalize the development and integration of the new DQM GUI. It's an overall upgrade, including both the front end and the back end, and we are planning to deploy the offline version of the tool in the containerized Kubernetes environment for it to be able to be scaled horizontally. Also, we are anticipating to complete the work on the new run registry that has been under development for the past 2 years. And also, we are looking forward to integrate some machine learning-based feedback into our data certification process. To conclude, we are happy in general about the performance and the general state of affairs within DQM during the run 2, and we have currently a few tools that are in the commissioning stage, and we are seeking new ideas and developments, especially on the machine learning side. And with the current developments essentially approaching the end, we are confident that all DQM systems are ready to undertake the challenges of the upcoming run 3. That's it for me. If you have any questions, I would be happy to answer them.
Thank you very much, Andres. Clearly a huge amount of work and all that infrastructure. Does anybody have any questions?
Is just the web application, or you have something also like a standalone application?
No, it's a web application. It's not a standalone application. It's a web application. The old one was the web application as well as the new one.
Okay. And what is the language? Is the ISO Python or is a set of tools?
Yes. So it's mostly, the new one is mostly Python, although we have still some components basically directly lifted from the old GUI, especially the rendering, the root rendering code and the display plugins. They are still C++, still raw root basically C++ code. Okay,
you are not using any like commercially available or free but already available software. It's custom made everything.
Well, I mean, it's all Python and it's all, what do you mean, commercially available?
Yeah, no, not like a high-level tool that would, so you are programming just using Python and C++.
Yes, that's true. Yes, that's true.
Okay.
The web server it's all async.io Python code. So the web server is async.io HTTP, AIO HTTP. That's the sort of the main dependency that we have. Mostly actually the root dependencies that we have, we had to implement the root parts or root IO actually ourselves. So we're not using PyRoot or RootPy or any of these wrappers or frameworks for root or re-implementations in Python for root. We are basically had to roll out our own code, mainly because all of these frameworks they don't allow for partial reads, and every request to every image reads the image directly from the root files. So we really need to have a partial read support. So actually, a lot of the root code is re-implemented by us completely. So,
okay.
So yeah, so that's the thing.
Yeah, thank you.
Thank you.
Andres, you mentioned quite a lot about data certification and run registry. For us non-experts, what are the challenges to basically make these interfaces, I don't know, easy for the experts to use and certify their data?
Well, it's actually quite a lot of work. So, we have currently connected the developers of this tool. It wasn't me who developed it, so maybe they can give a better overview. But from what I see, the challenges were the basically the communication with the people and sort of the feedback, collection of the feedback, and how they are sort of finding out how they are actually using our tools, finding out what they really want to achieve, what they really want to do with our tools, and sort of adapting to their needs and finding out the common ground between the different subsystems within the collaboration. So I would say these were the most sort of the coordination and the feedback from the users were the most challenging part of coming up with the tool.
just as Andrew said, it's basically like an iteration.
Yeah, please repeat because we lost you on the network.
No, I was just saying that just as Andrew said, it was just feedback and iteration and run registry and yeah.
Okay, thank you. So you're dealing with a large number of sub-detector, let's say, clients with different needs.
Different needs, exactly.
Okay. Okay, well done. A lot of infrastructure here.
Yep.
Okay, and you have to, with dependencies on root and the CMS software, as you mentioned.
Exactly.
Maybe I just mentioned to Jiri, in the other parts of CMS monitoring that are not as dependent on CMS software and on root, and there we have more flexibility to use other tools.
Okay.
But this is really very, 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 very connected to the normal CMS software.
Exactly. Well, probably mainly because this is the sort of a central tool used by basically everyone. DQM in general provides the central service for basically every subsystem within the collaboration.
Okay. Any other questions for Andres? Okay. Well, thank you again. And this is the end of the session. And I think that Jiri will like to inform us of the next parts of the session, the poster session. Yeah.
Okay, so thank you very much again. Thank you for all the nice presentations. We were slightly longer than expected, but yeah, I think that we had a beautiful program. Also, this is the end of parallel sessions actually, so thank you very much again. A lot of work, a lot of talks. And now we will continue with the third poster session. Actually, we are already quite significantly late, more than 30 minutes, but I would say we can still have something like 7 minutes coffee break. So we can meet here at 2:10 p.m. Prague time. Yeah, so in roughly 7 minutes, and we will start with the poster session. Everybody is of course invited to this poster session. So I hope that we will have a nice discussion. So I hope that everything is clear. Are there any questions? If not, so see you in 7 minutes roughly.
Okay, thank you very much, everyone.